I also think she'll be able to settle if she doesn't have a metal bar in the middle of the thing.
Yeah. What's wrong with it, but yes.
Yeah, but once it was there, she couldn't do anything about it.
Right. Should we take her bed out of there?
Yeah, I think so. Girlie, you can't keep chewing everything that's in there, though, because you're going to kill yourself with a blockage.
The level in Lake Mead, the largest water reservoir in the United States formed by the Hoover Dam, reached yet another.
Yeah, well, she should have thought of that before she tries to destroy the house. Oh. Do you feel good? Try this. Here, try this. One piece. Try one piece.
Did she eat it?
No, I'm just holding 2 pieces of food now.
Well, don't you look silly?
Oh, there she ate it now. Is this one? What's this one? Yeah.
I was thinking about that, how we should mentally stimulate her in the morning before she goes in the crate, but I was like, oh, but she's not food driven. So I can't give her like a cigar or anything.
You give her a cigar?
Yeah. The rolled up food.
Oh. Yeah.
I showed Colleen, Christine, I forget how, but someone mentioned that they're like, yeah, I heard you could do that. I was like, yeah, that's what we literally did. I think it's Colleen, and she's like, wait, does it work? And I found the video of Joshy sniffing around.
Yeah.
I was like, yeah, look, here. And we were talking about how good mental stimulation is for them versus physical, and even Christina was like, oh yeah, I never thought of that. I didn't know.
Yeah.
Yeah, I mean, she's had small, low energy dogs her whole life, so.
Yeah.
I'm not surprised.
Yeah, dogs need to, they gotta use their brains.
Yeah.
Even you, Mandy.
I would like you to use your brain too, but all you have in your brain is cuddles. I mean, nothing personal. You're smart.
Paw? Mandy, paw?
You diversify, you know? Sorry.
Oh, that's fine. Okay, well, the camera's on and uncovered, so.
And uncovered, okay.
Yeah.
Because I might slide it and cover it.
Yeah.
Now that I know.
Good
paw. Where it's at.
Good paw. She's got so much fur, though, that, I don't think that she needs a bed to, A, be warm, or B, be comfortable in there.
Yeah, I mean, she's not going to enjoy the bed anyhow.
Yeah. Do you want me to?
On tile.
Yeah. Do you want me to put her in?
Sure.
Mandy, here. Come here. Can you go in the crate? Mandy, crate.
She needs to eat.
Oh, yeah. Here, Mandy, eat. Mandy, eat crate.
Mandy, don't eat crate.
Okay, well. Come in. Hey. No, you gotta want to eat more than you want to pet me.
She wants to pet you.
She keeps reaching out her paw. Hi. Okay. Here. Eat some food. Eat some food.
My hair is just full of lice. And I look at it and you can see all the guys crawling around.
Yeah.
They've had meetings.
I don't know.
No tax. Mandy, go eat. And drink. Drink some, but go drink more.
I'm mimicking her. Stop copying me. Here. Hey, come eat. Come here. Come on. Here. Get a chunk of food. You want a chunk of food? Here, eat a chunk of food. Chunk of food? Chunk of food. Well, I gotta go to work, so best of luck to you.
You're in the crate with the food?
Yeah.
I guess no.
She's not gonna eat
I would
them.
have to open it to get it, the bowl that I thought in, so I'll leave it.
Just call me Mindy. Is?
Leave it.
Alright. Have fun.
Thanks, my boy. I'll leave it. Have a good green blue day. Wait, can I come here? Oh, now she eats.
Of course.
Pants too. Do this. Just don't want me in it, really. Yeah, the boomer would put you in it, but
Good girl. Good eating. Okay, love you.
love you.
Drive safe and fast. Sandy, don't eat the house.
You okay? You gotta chew your food, man. That someone's gone. Oh my god. Your treats faded? No. That's too bad. I might have some. No! Yeah, this is. It's covered in dog hair. That's what it is. Mini crate. Come crate. Crate. Oh, good crate. Good crate. Good girl. Yeah. No. I'm sorry. Girl. Right today.
All-time
I'm gonna
low
rewatch
of
the Reservoir one.
175 feet or 53 meters below full, a level that hasn't been seen since the lake was first filled in the 1930s. Rusted debris, sunken boats, and even even human remains have surfaced from beneath the receding water level. And Lake Mead doesn't stand alone. In fact, it's just a drop in the bucket. Many of the largest water reservoirs in the western United States are at critically low storage, with the summer of 2022 only just getting started. Lake Powell, upstream of Lake Mead on the Colorado River, is at its lowest level on record. Lake Oroville, of the enormous spillway failure fame, and Lake Shasta, two of California's largest reservoirs, are at critical levels. The combined reservoirs in Utah are below 50% full. Even many of the westernmost reservoirs here in Texas are very low going into summer. People use water at more or less a constant rate, and yet Mother Nature supplies it in unpredictable sloshes of rain or snow that can change with the seasons and often have considerable dry periods between them. If the sloshes get too far apart, we call it a drought. And at least one study has estimated that the past 2 decades have been the driest period in more than 1,000 years for the southwestern United States, leading to a so-called mega drought. Dams and reservoirs are one solution to this tremendous variability in natural water supply. But what happens when they stop filling up? Or in the case of one lake in Oklahoma, what happens when they never fill up in the first place? I'm Grady, and this is Practical Engineering. On today's episode, we're talking about water availability and water supply storage reservoirs. This video is sponsored by Brilliant, the best way to learn math and science through problem solving. More on them later. The absolute necessity of water demands that city planners always assume the worst case scenario. If you have a dry year or even a dry day, you can't just hunker down until the rainy weather comes back. So the biggest question when developing a new supply of water is the firm yield. That's the maximum amount of water the source will supply during the worst possible drought. Here's an example to make this clearer. Imagine you're the director of public works for a new town. To keep your residents hydrated and clean, you build a pumping station on a nearby river to collect that water and send it to a treatment plant where it can be purified and distributed. This river doesn't flow at a constant rate. There's lots of flow during the spring as mountain snowpack melts and runs off, but the flow declines over the course of the summer once that snow has melted and rain showers are more spread out. In really dry years, when the snowpack is thin, the flow in the river nearly dries up completely. In other words, the river has no firm yield. It's not a dependable supply of water in any volume. Of course, there is water to be used most of the time, but most of the time isn't enough for this basic human need. So what do? One option is to store some of that excess water so that it can keep the pumps running and the taps flowing during the dry times. But the amount of storage matters. A clear well at a water treatment plant or an elevated water tower usually holds roughly 1 day's worth of supply. Those types of tanks are meant to smooth out variability and demands over the course of a day. And I have a video on that topic. But they can't do much for the reliability of a water source. If the river dries up for more than a day at a time, a water tower won't do much good. For that, you need to increase your storage capacity by an order of magnitude, or 2. That's why we built dams to create reservoirs that, in some cases, hold trillions of gallons or tens of trillions of liters at a time. Incredible, almost unimaginable volumes. You could never build a tank to hold so much liquid, but creating an impoundment across a river valley allows the water to fill the landscape like a bathtub. Dams take advantage of Mother Nature's topography to form simple yet monumental water storage facilities. Let's put a small reservoir on your city's river and see how that changes the reliability of your supply. If the reservoir is small, it stays full for most of the year. Any water that isn't stored simply flows downstream as if the reservoir wasn't even there. But during the summer, as flows in the river start to decrease, the reservoir can supplement the supply by making releases. It's still possible that in those dry years, you won't have a lot of water stored for the summer, but you still have more than zero, meaning your supply has a firm yield, a safe amount of water you can promise to deliver even under the worst conditions, roughly equal to the average flow rate over the course of a dry year. Now let's imagine you build a bigger dam to increase the size of your reservoir so it can hold more than just a season's worth of supply. Instead of simply making up a deficit during the driest few months, now you can make up the deficit of 1 or more dry years. The firm yield of your water source goes up even further, approaching the long-term average of river flows, and completely eliminating the idea of a drought by converting all those inconsistent sloshes of rain and snow into a perfectly constant supply. Beyond this, any increase in reservoir capacity doesn't contribute to yield. After all, a reservoir doesn't create water, it just stores what's already there. Of course, dams do more than merely store water for cities that need a firm supply for their citizens. They also store water for agriculture and hydropower that have more flexibility in their demand. Reservoirs serve as a destination for recreation, driving massive tourism economies. Some reservoirs are built simply to provide cooling water for power plants. And many dams are constructed larger than needed for just water conservation, so they can also absorb a large flood event even when the reservoir is full. Every reservoir has operating guidelines that clarify when and where water can be withdrawn or released and under what conditions. And no two are the same. But I'm explaining all this to clarify one salient point. An empty reservoir isn't necessarily a bad thing. Dams are expensive to build. They tie up huge amounts of public resources. They are risky structures that must be vigilantly monitored, maintained, and rehabilitated. And in many cases, they have significant impacts on the natural environment. Put simply, we don't build dams bigger than what's needed. Empty reservoirs might create a negative public perception. Dried up lake beds are ugly, and the bathtub ring around Lake Mead is a stark reminder of water scarcity in the American Southwest. But not using the entire storage volume available can be considered a lack of good stewardship of the dam, and that means reservoirs should be empty sometimes. Why build it so big if you're not going to use the stored water during periods of drought? Storage is the whole point of the thing. Except there's one more thing to discuss. Engineers and planners don't actually know what the worst case scenario drought will be over the lifetime of a reservoir. In an ideal world, we could look at thousands of years of historical stream flow records to get a sense of how long droughts can last for a particular water body. And in fact, some rivers do have stream gauges that have been diligently collecting data for more than a century, but most don't. So when assessing the yield of a new water supply reservoir, planners have to make a lot of assumptions and use indirect sources of information. But even if we could look at the long-term historical record as the basis of design, there's another problem. There's no rule that says the future climate on Earth will look anything like the past one. And indeed, we have reason to believe that the long-term average stream flows in many areas of the world, along with many other direct measures of climate, are changing. In that case, it makes sense to worry that reservoirs are going dry. Like I said, reservoirs don't create water. So if the total amount delivered to the watershed through precipitation is decreasing over time, so will a reservoir's firm yield. That brings me to the question of the whole video. What happens when a reservoir runs out of water? It's a pretty complicated question, not only because water suppliers and distributors are relatively independent of each other and decentralized, capable of making very different decisions in the face of scarcity, but also because the effects happen over a long period of time. Most utilities maintain long-term plans that look far into the future for both supply and demand, allowing them to develop new supplies or implement conservation measures well before the situation becomes an emergency for their customers. Barring major failures in government or public administration, you're unlikely to turn on your tap someday and not have flowing water. In reality, water availability is mostly an economic issue. We don't so much run out as we just use more expensive ways to get it. Utilities spend more money on infrastructure like pipelines that bring in water from places with greater abundance, wells that can take advantage of groundwater resources, or even desalination plants that can convert brackish sources or even seawater into a freshwater source. Alternatively, utilities might invest in advertising and various conservation efforts to convince their customers to use less. Either way, those costs get passed down to the ratepayers and beyond. For some, like those in cities, the higher water prices might be worth the cost to live in a climate that would otherwise be inhospitable. For others, especially farmers, the increased cost of water might offset their margins, forcing them to let fields fallow temporarily or for good. So, while drying reservoirs might not constitute an emergency for most individuals, the impacts trickle down to everyone through increased rates, increased costs of food, and a whole host of other implications. That's why many consider what's happening in the American Southwest to be a quote-unquote slow-moving train wreck. In 2019, all the states that use water from the Colorado River signed a drought contingency plan that involves curtailing use, starting in Arizona and Nevada. Those curtailments will force farmers to tap into groundwater supplies, which are both expensive and limited. Eventually, irrigated farming in Arizona and Nevada is a thing of the past. there's no question that the climate is changing in the American Southwest, and years continue to be hotter and drier than any time in recorded history. It can be hard to connect cause and effect for such widespread and dramatic shifts in long-term weather patterns, but I have one example of an empty reservoir where there's no question about why it's dry. In 1978, the U.S. Army Corps of Engineers completed Optima Lake Dam across the Beaver River in Oklahoma. The dam is an earth embankment 120 feet or 37 meters high and over 3 miles or 5 kilometers long. The Beaver River in Oklahoma had historically averaged around 30 cubic feet or nearly a cubic meter per second of flow. The river had a flood, sending huge volumes of water downstream. However, during construction of the dam, it became clear that things were rapidly changing. It turns out that most of the flows in the Beaver River were from streams, areas where groundwater heats up to the surface. Over the 1960s and 70s, pumping groundwater for cities and agriculture reduced the level of the aquifer in this area, slashing stream flow in the Beaver River as it did. The result was that when construction was finished on this massive earthen dam, the reservoir never filled up. Now, Optima Lake Dam sits mostly high and dry in the Oklahoma Panhandle, never having reached more than 5% full, as a monument to bad assumptions about the climate and a lesson to engineers, water planners, and everyone about the challenges we face in a drier future. Drought seems really simple when you're just looking at the level of a reservoir, but I hope this video helps you appreciate the technical complexity in developing and managing a water supply for a large area that involves hydrology, geology, meteorology, climatology, and of course, a lot of civil engineering. In fact, I found through everything I look at all the best and most important projects, combining expertise and knowledge of a lot of different fields of study, and the way you get exposed to those different fields, even like reading or watching videos, is by doing the thing, coding the program, by building projects. That's why I'm so thankful to have Brilliant as the sponsor of today's video. Brilliant is a learning platform for science, technology, engineering, and math that's super interactive. There are courses on logic, computer science, math, and my favorite is this one called The Physics of the Everyday. It just pulls back the scientific curtain on aspects of the world that isn't learned about in grade. For example, one of my favorite obsessions, the weather. If that sounds interesting to you, go try Brilliant yourself, completely free at brilliant.org/practical engineering. You don't pay anything to sign up, and the first 200 people that use the link will get 20% off the annual premium subscription. Thanks for watching, and let me know what you think. One of my viewers sent me this shot of some interesting equipment at the top of an electrical distribution pole. Can you name that infrastructure? Pause the video here if you want to make a guess. Some of the most common faults on the electrical grid are completely temporary. Lightning strikes are gone in an instant, and tree limbs often fall off the line after they fall across them. Instead of sending a linesperson to reset the circuit breaker, it's much easier to let the circuit breaker reset itself. So-called reclosers are small breakers on the grid that can automatically sense faults and disconnect small areas to protect the system. But they also automatically re-energize a line after a fault to test if it was just a temporary issue, potentially reducing the duration and extent of outages. If there's still a problem, the recloser will lock out and notify the utility so they can send someone to fix it. Want to win a free copy of my new book all about infrastructure you can see? Make a social media post like this one and include the hashtag engineering in plain sight. In December 2019, the city of Fort Lauderdale, Florida, experienced a series of catastrophic eruptions in a critical wastewater transmission line, releasing raw sewage into local waterways and neighborhoods. Recognizing the need for improvements to their aging infrastructure, the city embarked on a plan to install a new pipeline to carry sewage from the Coral Ridge Country Club pumping station across 7 miles or 12 kilometers to the Lohmeyer wastewater treatment plant. But just drawing a line on a map hides the enormous complexity of a project like this. Installing an underground pipeline through the heart of a major urban area while crossing 3 rivers is not a simple task. Underground utilities are usually installed by a technique known as trenching. In other words, we excavate a trench down from the surface, place the line, backfill the soil, and repair whatever damage to the streets and sidewalks remains. That type of construction is profoundly disruptive, requiring road closures, detours, and pavement repairs that never quite seem as nice as the originals. Trenches are also dangerous for the workers inside, so they have to be supported to prevent collapse. Beyond the human risk, in sensitive environmental areas like rivers and streams, trenching is not only technically challenging, but practically unachievable because of the permits required. In fact, trenching in urban areas to install pipelines these days is for the birds. When the commotion of construction must be minimized, there are many trenchless technologies for installing pipes below the ground. One of those methods helped Fort Lauderdale get a 7-mile-long sewer built in less than a year and a half, and is used across the world to get utility lines across busy roadways and sensitive water courses. I'm Grady, and this is Practical Engineering. On today's episode, we're talking about horizontal directional drilling. This video is sponsored by CuriosityStream and Nebula. More on them later. If you've ever seen one of these machines on the side of the road, you've seen a trenchless technology in action. Although there are quite a few ways to install subsurface pipelines, telecommunication cables, power lines, and sewers without excavating a trench, only one launches lines from the surface. That means you're much more likely to catch a glimpse. Like laparoscopic surgery for the earth, horizontal directional drilling, or HDD, doesn't require digging open a large area like a shaft or a bore pit to get started. Instead, the drill can plunge directly into the Earth's surface. From there, horizontal directional drilling is pretty straightforward, but it's not necessarily straight. In fact, HDD necessarily uses a curved alignment to enter the Earth, travel below a roadway or river, and exit at the surface on the other side. Let me show you how it works, and at the end, we'll talk about a few of the things that can go wrong. The first step in an HDD installation is to drill a pilot hole, a small diameter borehole that will guide the rest of the project. A drill rig at the surface has all the tools and controls that are needed. These rigs can be tiny machines used to get a small fiber optic line under a roadway, or colossal contraptions capable of drilling large diameter boreholes for thousands of feet at a time. As such, many of the details of HDD vary across projects, but the basic steps and equipment are all the same. As the drill bit advances through the earth, the rig adds more and more segments of pipe to lengthen the drill string. Through this pipe, drilling fluid is pumped to the end of the string. Drilling fluid, also known as mud or slurry, serves several purposes in an HDD project. First, it helps keep the drill bit lubricated and cool, reducing wear and tear on equipment and minimizing the chances of a tool breaking and getting stuck in the hole. Next, drilling fluid helps carry away the excavated soil or rock, called the cuttings, and clear them from the hole. Finally, drilling fluid stabilizes and seals the borehole, reducing the chance of a collapse. I have here an acrylic box partly full of sand, a setup you're probably quite familiar with if you follow my channel. Turns out a box of sand can show a lot of different phenomena in construction and civil engineering. Compared to soils that hold together like clay, sand is the worst case scenario when it comes to trying to keep a borehole from collapsing. If I pull away the support, the simulated borehole face caves in no time. If I add groundwater to the mix, the problem is even worse. Pulling away the support, the wall of my borehole doesn't stand a chance. Let me show you how drilling fluid solves this problem. I'm mixing up a handcrafted, artisanal batch of drilling mud, a slurry of water and bentonite powder. This is a type of clay created by volcanic ash that swells and stays suspended when mixed with water. It's pretty gloopy stuff, so it gets used in cosmetics and even winemaking, but it's also the most common constituent in drilling fluids. If I add the slurry to one side of the demo, you can see how the denser fluid displaces the groundwater. It's not the most appetizing thing I've ever put on camera, but watch what happens when I remove the rigid wall. The drilling fluid's able to support the face of the tank, preventing it from collapsing. In addition to supporting the tank, the drilling fluid seals the surface of the borehole to reduce migration of water into or out of the interface. In most HDD operations, drilling fluid flows in through the drill string and back out of the borehole, carrying cuttings along toward the entry location where it's stored in a tank or a containment tank for later disposal and reuse. So far, HDD follows essentially the same steps as any other drilling into the earth, but that first D is important. Horizontal directional drilling means we have to steer the bit. The drill string has to enter the subsurface from above, travel far enough through a river or road to avoid impacts, evade other subsurface utilities or obstacles below the ground, and exit the subsurface on the other side of that location. I don't know if you've ever tried to drill all night. You'll never be able to curve the bit around an object. So how is it possible in horizontal directional drilling? There are really two parts to steering a drill string. Before you can correct the course, you need to know where you are in person, and there are two ways to do it. One option is a walk-over locating device that can use the position and depth of a drill bit from the surface. The transmitter behind the drill string sends a radio signal that can be picked up by a handheld receiver. Other options include wireline or gyro systems that use magnetic fields or gyroscopes to keep track of the bit's location as it travels below the subsurface. Once you know where the bit is, you can steer it to where you want it to go. I've made up a batch of agar, which is a translucent gel made from the cell walls of algae. I tried this first in the same acrylic box, but the piping hot jelly busted the steam and pouring out into my bathtub, creating a huge mess. So you'll have to excuse the smaller glassware demo. My simulated drill string is just a length of wire. There are two things to keep in mind about directional drilling. Number one, although they seem quite rigid, drill pipes are somewhat flexible at length. If I take a short length of this wire and try to bend it, it's pretty difficult, but a longer segment deflects with no problem. And number two, you don't have to continuously rotate the drill string in order to advance the borehole. You can just push on it, forcing the bit through the soil. My wire pushes through the auger without much force at all, and a drill string can be advanced through the soil in a similar way, especially when lubricated with water or drilling fluid. The real trick for steering a drill string is the asymmetric bit. Watch what happens when I put a bend on the end of my wire and advance through the auger. It takes a curved path, following the direction of the bend. If I rotate the wire and continue advancing, I can change the direction of the curve. The model drill string is biased in one direction because of the asymmetry, and I can take advantage of that bias to steer the bit. I can steer the string left, then rotate and advance again to steer the bit to the right. I'm a little bit clumsy at this, but with enough control and practice, I could steer this wire to any location within the auger, avoid obstacles, and even have it exit at the surface wherever I want. This is exactly how many horizontal directional drills work. The controls on the rig show the operator which way the bit is facing. The drill string can be rotated to any angle, called clocking, then advanced to change the direction of the borehole. Sometimes a jet nozzle at the tip of the bit sprays drilling fluid to help with drilling progress. If the nozzle is offset from the center, it can help create a steering bias like the asymmetric bit. Just like the Hulk's secret is that he's always angry, a directional drill string secret is that it's always curving. The rig operator's only steering control is the direction the drill string curves. And hey, if that sounds like something you'd like to try for yourself, my friend Dan Shipman over at the Coding Training channel built a 2D horizontal directional drilling simulator. We did it! Horizontal directional drilling! This is an open source project, so you can contribute features yourself, but it's also really fun if you just want to play a few rounds. If you're into coding or wanting to get started, there is no better way than working through all the incredible and artistic examples Dan comes up with for his coding challenges. Go check out his video on HDD after this one and tell him I sent you. Once the drill string is headed in the right direction, it can just be continuously rotated to keep the bit moving in a relatively straight line. The pilot hole for an HDD project is just an exercise in checking the location and adjusting the clock position of the drill string over and over until the drill string exits on the other side, hopefully in exactly the location intended. But not all soil conditions allow for a drill string to simply be pushed through the subsurface. Rocky conditions in particular make steering a drill rig challenging. An alternative to simply ramming the bit through the soil is to use a downhole hydraulic motor. Also known as mud motors, these devices convert the hydraulic energy from the drilling fluid being pumped through the string to rotate a drill bit that chews through soil and rock. This allows for faster, more efficient drilling without having to rotate the whole drill string. The housing of the mud motor is bent to provides steering bias, and the drill string can be clocked to change the direction of the borehole. Once the pilot hole exits on the other side, it has to be enlarged to accommodate the tight hookup. That process is attached to the drill string from the exit hole and pulled to installed. Contractors the pipe to be installed in the borehole lined up on rollers behind the pipe is attached to the remaining assembly, and the whole mess is pulled with tremendous force through the borehole toward the rig. Finally, it can be connected with both ends to the surface. That's how things work when everything goes right. But there are plenty of things that can go wrong with horizontal direction drilling. Parts of the drill string can break and get stuck in the pilot hole. Drilling can inadvertently impact other subsurface utilities or underground structures. The pipeline can get stuck or damaged on board. The controversial Mariner East 2 pipeline in Pennsylvania experienced a litany of environmental problems during its construction between 2017 and 2022. Most of those problems happened on HDD segments of the line and involved inadvertent returns of drilling fluid. That's the technical term for the situation when drilling fluid exits a borehole at the surface instead of circulating back to the entrance. Inadvertent returns in the Mariner East 2 line created water quality issues in nearby wells, led to sinkholes in some areas, and spilled drilling fluid into sensitive environmental areas. The pipeline owner was fined more than $20 million over the course of construction due to violations of the permit, and was still in legal battles and extreme public opposition. Project to date. Which is awesome because you can access the photos from the website and similar services. Nebula is a completely ad-free streaming service built by and for independent creators like Windover Productions, Real Engineering, and me. It's a way for us to try new ideas and longer videos that might not work well on ad-supported platforms like YouTube. My videos go live there the day before they go on YouTube. And one of my favorite parts of Nebula is re-watching some of my favorite creators' back catalogs of videos without any ads. And we're super excited to continue our partnership with Curiosity, a service with thousands of documentaries and nonfiction titles and pretty much every subject you can imagine. Curiosity Stream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and if you add them all up, it would be hundreds of dollars a month. That's why this bundle is such an awesome deal. You get access to 2 platforms, Nebula and Curiosity Stream, for less than $15 a year. I have kids, so when we have the TV on in the house, I want to make sure it's something that expands their minds. Curiosity Stream has a huge library of kid-friendly content, like this series that covers every single national park in the U.S. This is the stuff that used to be on TV when I was a kid, and it's so good. Plus, watch Sam from Windover Productions try to break the law while evading his production team in the Nebula exclusive series, Crime Spree. This bundle is a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. A fan of the channel sent me this photo of a locked equipment cabinet with a scientific instrument sticker on the outside. Can you name that infrastructure? Pause the video here if you want to make a guess. In the US and around the world, various local, state, and federal governments, plus universities, maintain networks of earthquake monitoring stations. Some sometimes called seismographs or accelerographs. Recording the strength and timing of strong ground motion is super important. First, it helps us create and update building codes so that offices and homes are built to the level and strength necessary to withstand earthquakes that might happen in different areas. These instruments are also used for emergency response because they can help focus resources where shaking was strongest in the immediate aftermath of an earthquake. They're also installed in buildings, bridges, dams, and other structures so that engineers can use the data after an earthquake to assess the structure's safety. Construction is something you probably either love or hate, depending on your commute or profession. Obviously, as a civil engineer, it's something I think a lot about. And over the past 6 years of reading emails and comments from people who watch practical engineering, I know that parts of heavy construction are consistently misunderstood. Also, I talk a lot about failures and issues in my videos because I think those stories are worth discussing. What affects all you ever hear about the civil engineering and construction industries can be forgiven for having an incomplete perspective of how things really work. So I combed through YouTube comments and emails over the past few years and pulled together a few of the most common misconceptions. I'm Brady, and this is Practical Engineering. In today's episode, we're debunking some myths about construction. This video is sponsored by Brilliant, the best way to learn math and science through problem solving. More on them later. If you're one of those people who hate construction, this is probably a frustrating image. One guy running the excavator and everyone else just standing around watching. It seems like a familiar scene, especially when the project's schedule is dragging along. But looks can be deceiving. Think of it this way. Contractors are running an extremely risky business on relatively thin margins. In most cases, they already know how much money they'll be paid for a project, so the only way to make a profit is to carefully manage expenses. And what's their biggest expense? Labor. A worker standing around with nothing to do is the first thing to get cut from a project. Individual laborers might be paid hourly, but their employers are paid by the contract and have every incentive to get the job done as quickly and efficiently as possible. So why do we see workers standing around? There are a few reasons. Firstly, construction is complicated. Honestly, it's a logistical nightmare to get materials, subcontractors, tools, equipment, and workers in the right place at the right time. Almost every task is sequential, which means anything that doesn't line up perfectly affects the schedule of everything else. Construction is a hurry up and wait operation, and the waiting is often easier to spot than the hurry. Most of the folks you see on a construction site, whether they're standing around or not, have been or will be hustling for most of the day. Which leads me to my second point. Construction is hard work. Anyone working in the trades will tell you that it's a physically demanding job. You can't just show up at 6 a.m., run a shovel for 10 hours, go home, and do it again the next day. You need breaks if you're working hard. Standing around is often as simple as that. Workers resting from a difficult task. Plus, a person with a shovel isn't that useful when you have a tracked excavator on site that can do the work of 20. So the laborers you see outside of machines are often doing jobs that are adjacent to the actual work, like running tools, directing traffic, or docking. That leads me to my third point. Not everyone on a construction site is a tradesperson. Keeping an eye on things is an actual job, and in some cases it's more than one. Inspectors are often on site to make sure a contractor doesn't misinterpret a design or build something incorrectly. An engineer may be on site to answer questions on projects. And trust me, you don't want us anywhere near the capital of Kramer. Safety spotters are sometimes required to keep workers out of dangerous situations. Plus, engineers and supervisors are on site to ensure these folks are doing necessary jobs that might look just like standing around if you're not familiar with the roles. Construction software often knows unlike any other job. The confirmation bias makes it easy to pass by construction site in a car and notice the people who aren't actually performing the task or ignore the ones who aren't. So, construction workers stepping in around the water cooler, talking about it on YouTube channel, and start a rumor that this is so lazy. Secrets possessed by the ancient Romans that have since been lost to the sands of time. It's not true, really. I mean, the ancient Roman concrete used in some structures did have some interesting and innovative properties And the Romans did invest significantly in the durability of their streets and roads, but I think the Roman engineer would be astounded to learn that most modern highways stand at hundreds of thousands of trucks that can weigh upwards of 2,000 pounds before being replaced. And I think the Roman engineer might be if they were to see a modern concrete skyscraper. There are a few reasons why it seems the Romans had us outclassed when it comes to structural longevity. First, there's survivor bias. We only see the structures that lasted these past 2,000 years, and not the vast majority of buildings and facilities which were destroyed in one way or another. Second, there's the climate. I haven't personally been to the parts of the world surrounding the Mediterranean Sea, but I hear most of them are quite nice. Cycles of freezing and thawing are absolutely devastating to almost every part of a constructed environment. The ancient Romans were in an area particularly well suited to making long-lasting concrete structures, especially compared to the frozen wastelands that some other of Earth's denizens call home. Finally, there's just a difference in society and government. Ancient Rome was wildly different from modern countries in a lot of ways, but particularly in how much they were willing to spend on infrastructure and how they were willing to treat laborers. Modern concrete mixes and roadway designs are far superior to those of ancient Rome, but our collective willingness to spend money on infrastructure is different too. I think a lot of the feedback I get on Roman construction is based on the extremely pervasive sentiment that we just don't build stuff like we used to. It's an easy shortcut to equate quality with longevity, especially for infrastructure projects where we aren't directly involved in managing the costs. I regularly have people tell me we shouldn't use reinforcing steel in concrete because when it corrodes, it decreases the lifespan, which is completely true. But also, unreinforced concrete is essentially just brick. And not to disparage masonry, but there's a lot it can't do in structural engineering. A lot of people even go so far as to accuse engineers of using planned obsolescence, the idea that we design things with an intentionally limited useful life. And I don't know anything about consumer goods or devices, but at least in civil engineering, those people are exactly right. We always think about and make conscious decisions regarding lifespan during the design of a project. But it's not to be nefarious or create artificial job security. It's because, in simplistic terms, the capital cost of a construction project and its lifespan exist on either side of a spectrum, and engineers, by necessity, have to choose where a project sits between the two. Will you build a bridge that's inexpensive but will have to be replaced in 25 years? Or will you spend twice the money for more concrete and more steel to make it last for 50? We make this decision constantly when we pay for things in our own lives, choosing between alternatives that have various costs and benefits. But it's much more complicated to draw that line as the steward of tax dollars for an entire population. That's why engineering exists in the first place. With an unlimited budget, my 2-year-old could design a bridge that carries monster trucks over the English Channel for 1 million years. Engineers compare the relative costs and benefits of design decisions from start to finish and meet project requirements, protect public safety, and do so with the limited available resources. Part of that is evaluating alternatives like the cheap bridge versus the expensive bridge, plus their long-term maintenance and replacement costs to see which one can best meet the project goals. In that case, planned obsolescence means being a good steward of public money, which is always benefit by not gold plating when it's necessary so that funding can be used when it needs most. There's a story about legendary astronaut John Glenn being asked by a reporter about what it felt like to be inside the Mercury capsule on top of an Atlas LV-3B rocket before takeoff. He reportedly said he felt exactly how one would feel sitting on top of 2 million parts, all built by the lowest bidder on a government contract. And indeed, most construction projects are contracted using bids, and regulations require that public entities award the contract to the lowest bidder. Those rules are in place to make sure that the taxpayer is getting the most value for their money, but it doesn't necessarily mean that our infrastructure projects suffer in quality as a result. Most construction projects are bid using a set of drawings and a book of specifications that includes all the detail necessary to build them. An engineer, architect, or both has gone to great lengths to draw and specify exactly what a contractor should build, often to the tiniest details about products, testing, and procedures. You can see for yourself. Just Google your city or state plus standard specifications and scroll through what you find to get a sense of how detailed contract documents can be. We go to that level of detail in defining the project before construction so that it can be let for bidding with the confidence that an owner will end up with essentially the same product at the end of construction, no matter which contractor wins the job. Bidding on contracts is a tough way to win work, by the way. Imagine if on January 1st, your employer gave you a list of all the tasks that needed to be complete by the end of the year, and you had to guess how many hours it would take. And if you guessed a higher number than your coworker, you got fired. And if you guessed lower than the actual number of hours it took, too bad. You only got paid for the hours you guessed. It might incentivize you to look for innovative ways to get your job done more efficiently, but admittedly, it might also encourage you to cut corners and ignore opportunities to add value where it's not explicitly required. Many public entities are moving away from contracting using the lowest bidder model for types of procurement that allow them to recognize and award other measures of value than just cost, like innovation, schedule, and past experience. These alternative delivery methods can help foster a more collaborative relationship between the owner, contractor, and designer, making the construction process smoother and more efficient. But the lowest bidder model is still used around the world because it generally rewards efficient use of public funds. After all, John Glenn did make it safely to space, became the first American to orbit the Earth, and came back with no issues on those 2 million parts provided by the lowest bidders. If you've ever played Minecraft, you know that at a certain depth below ground, you reach an impenetrable layer of voxels called bedrock. And indeed, in most parts of the world, geologic layers do get firmer and more stable the farther down you go. Engineers often take advantage of this fact to secure tall buildings and major structures using deep foundation systems like driven or drilled piles. Bedrock is such a familiar concept that it's easy to look at the world through Minecraft-colored glasses and assume there's always and everywhere some firm layer below but not too far from the surface of the Earth. And all tall buildings and structures must sit atop it. But the real world is a little more complicated than that. Different geologic layers may be considered bedrock depending on whether you're a well driller, foundation designer, pile driver, or geology textbook author. There's no strict definition of bedrock, and there are vast spectrums of soil and rock properties that might make stable foundations depending on the loading and environmental conditions. In engineering especially, there doesn't always exist a firm geologic layer at a reasonable depth below the surface of the Earth our buildings and structures can be attached to. And even if there is, that may not be the most cost-effective way to meet design requirements. There may be shallow foundation concepts that are appropriate and much cheaper depending on the situation. There's a famous parable about a wise man who built his house on the rock, but not every wise man can afford a piece of property on the rocky side of town, especially in today's real estate market. Civil engineers don't always have the luxury of founding structures on the most stable of subgrades. So we've come up with foundations that keep structures secure on sand, silt, clay, and even floating on water. When the rain comes down and the streams rise and the winds blow and beat against our structures, they almost always remain standing, no matter what the geology is below. Building infrastructure is such a cool confluence of technical fields combining engineering, public administration, construction management, and a whole lot of skilled trades. I think one of the easiest shortcuts to success in school, your career, or just life in general is finding opportunities to mix and match areas of expertise like this. In niches, there are riches, as they say. But it's hard to gain technical knowledge in outside industries. That's why I'm thankful for Brilliant, sponsor of today's video, for providing interactive courses in topics that interest, like this one about using logic to debunk false information. Sound familiar? My videos give a 1,000-foot overview of many parts of engineering, but maybe you're watching one of my videos and thinking, this is for me, this is what I'm interested in. Brilliant gives you the ability to dive into math and science topics so you can really learn them and get ahead in your studies or your career. The website is beautifully designed and they put a ton of effort into finding the best ways to help you gain technical knowledge and skills. Learn to think like a scientist, engineer, or construction manager completely free at brilliant.org/practical engineering. You don't pay anything to sign first 200 people to use the link will get 20% off and annual premium subscription. Again, it's completely free to sign up. The link is in the description. Thank you for watching. And let me know what you think. If you pay attention to the spillways at dams, you might notice they sometimes use this zigzag shape. Can you name that infrastructure? Pause the video here if you want to make a guess. A structure that lets water pass over the top is called a weir. Unlike a spillway with a gate, a weir doesn't offer any control over the flow of water once it's built. So engineers put a lot of thought into getting the size and shape of the structure just right. The amount of flow that moves over a weir is related both to the height of the water over the crest and the total length of the structure. Engineers are always trying to minimize the size of the spillway or dam to reduce its cost without sacrificing the amount of water that can be discharged. The best engineering strategy is to fold the weir in a zigzag, providing more length with a smaller footprint. Weirs that use triangular or trapezoidal shapes are called labyrinth weirs, and those that use square circles are called piano weirs. In 2015, some unusual things happened on the construction site in British Columbia, Canada. Work Safe BC, the provincial health and safety agency, posted a summary of the event on YouTube. A steel caisson had been installed to hold back soil while the lift station was being constructed. One worker on the site was suddenly pulled into a sinkhole and the bottom of the caisson blew out. The cause of the incident was related to groundwater within the soils below the site. We don't all have to live in fear of the ground opening up for more people, but engineers who design subsurface structures do have to consider the impact that groundwater can have. The solutions to subsurface problems are almost always hidden from public view, so you might never even know they're there. This video is intended to shed some light on those invisible solutions, including what could have been done to prevent that incident in BC. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about how groundwater affects structures. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. Groundwater has always been a little mysterious to humanity since it can't easily be observed. It also behaves much differently than surface waters like rivers and oceans, sometimes defying expectations, as I've shown in a few of my previous videos. One of the most important places where groundwater shows up in civil engineering is at a dam. That's because groundwater flows from high pressure to low pressure, and a dam, at its simplest, is just a structure that divides those two conditions. And what do you know? I've got an acrylic box in my garage full of sand to show these concepts in real life. You can imagine this soil sits below the base of the dam, and I can adjust the water levels on either side of the structure to simulate how groundwater will flow. Blue dye placed in the sand helps show the direction and speed of water movement below the surface. A higher level on the upstream side creates pressure, driving water in the subsurface below the dam to the opposite end of the model. I'll be the first to say it. This is not the most mind-blowing revelation. You probably could have predicted it without the fancy model, but to a civil engineer, this is not an inconsequential phenomenon, and for a couple of reasons. First, water seeping below a dam can erode soil particles away, a phenomenon called piping. Obviously, you don't want part of your structure's foundation to be stolen from underneath it, and piping can create a positive feedback loop where failure progresses rapidly. I have a whole video on piping that you can check out after this one. The second negative effect of groundwater is less obvious. In fact, until around the 1920s, dam engineers didn't even take it into account, leading to the demise of many early structures in history. The engineering of a dam is largely an exercise in resisting hydrostatic pressure. Water in the reservoir applies an enormous force to the upstream face of a dam, and if not designed properly, that force can cause the dam to slide downstream or overturn. The hydrostatic force is actually pretty simple to approximate. Pressure in a fluid increases with depth, so you get a triangular distributed load. Once you know that load, you can design a structure to resist it. And there are a lot of ways to do that. One of the most common types of dam just uses its own weight for stability. Gravity dams are designed to be heavy enough that hydrostatic forces can't slide them backwards or turn them over. But to the dismay of those early engineers, pressure from the reservoir is not the only destabilizing force on a dam. Take a look at this pipe I've included in the model that shows the water level between the two boundaries. If the base of the structure was below the water level shown here, the groundwater would be applying pressure to the bottom, counteracting its weight. We call this uplift pressure. Remember that the only reason gravity dams stay put is because of their weight. So you can see how having an unanticipated force, effectively subtracting some of that weight, would be a bad thing. Many times these gravity dams have failed because this uplift force is affected by engineers. Of the underlying points of the concrete structure itself. The flow of groundwater is affected by soil properties, the geometry of the dam, water level, upstream, downstream, even subsurface heat. How these factors affect the pressure can be pretty challenging to predict, but engineers do have to predict. After all, they can't control the dam, most of the outcome, of course, can but we can still use flow nets to demonstrate a few of the ways engineers do cutoff walls can still reduce the volume. Downstream side. The flow of groundwater is described with a fairly simple formula known as Darcy's law. Besides the permeability of the soil, the only other factor controlling the speed water flows is the hydraulic gradient, which consists of the difference in pressure over the length of the flow path. By adding a cutoff wall, I didn't change the difference in pressure between one side of the model and the other, but I did increase the length of the flow path water had to take below the dam, reducing the hydraulic gradient. I can sketch a flow net over the model to make this clearer. The black lines are equipotentials. They connect areas of equal pressure. The blue lines show the directions of flow. Without a cutoff, the flow paths are shorter, and thus the equipotential lines are closer together. With a cutoff wall, the equipotential lines are spread out. That means both the volume of seepage and the uplift pressure at the base of the structure have been reduced. Cutoff walls on dams have a long history of use, and nearly all large gravity dams have at least some kind of cutoff. It could be as simple as excavating a wide area of the dam's foundation before starting on construction. And that's a popular choice because it gives engineers a chance to observe the subsurface conditions and make sure there are no faults or problems before the dam gets built. Another option is to excavate a deep trench and fill it with grout, concrete, or a slurry of impermeable clay. For smaller or temporary structures, sheet piles can be driven into the subsurface and cut off. One final option is to inject high-pressure grout. Again, the effect is subtle, but the uplift pressure monitor is showing a slight decrease in pressure. Gradient by shortening the flow paths, so there's actually more seepage happening than there would be without the drain. However, because the drains are installed with filters, vertical drains into the foundation, and some even use pumps to depress the groundwater level. I've been using dams as the main example of managing groundwater flow, but lots of other structures have similar issues. Retaining walls and temporary shoring have to contend with groundwater challenges, including caissons, which are watertight chambers sunk into the earth to hold back soil during construction. Remember the worker I mentioned in the intro? He was on a site near a caisson. It's typical to dewater a structure like this, meaning the water is pumped out, creating a dry area for construction crews to work. Let's take a look at how this works in the model. I'm simulating the act of pumping water out of the caisson by draining out of the model at the bottom of the structure. When a caisson is dewatered, it's essentially working like a dam, separating an area of high pressure from low pressure within only a short distance between them. And as you know, distance matters when it comes to groundwater because the shorter the flow path, the greater the hydraulic gradient, and thus the higher the volume and velocity of seepage. If you look closely, you can see the sand boiling up as the seepage exits the soil into the bottom of the caisson. This elevated pressure in the subsurface and high velocity of flow means that the soil particles themselves aren't being strongly held together. All it takes is a little agitation for the soil to liquefy and flow into the bottom of the caisson, creating a sinkhole that can easily swallow anything at the surface. One way of mitigating this hazard is dewatering the soil outside the caisson. Construction crews use well points, small, evenly spaced wells and pumps to draw water out of the soil so it can't seep to areas of lower pressure. Caissons can also be driven deeper into the subsurface, creating a condition similar to a cutoff wall on a dam. They can even go deep enough to reach an impermeable layer, creating a better seal that prevents water from flowing in through the bottom. Thankfully for that worker in DC, his colleagues were able to rescue him before he was consumed by the earth. Next time you see a dam, retaining wall, caisson, or any other subsurface construction, there's a good chance that engineers have had to consider how groundwater will affect the stability. Even though you'd never know they're there, some combination of drains and cutoffs were probably installed to keep the structure and the people around it safe and sound. Speaking of sounds, here's the peaceful sound of a napping toddler while my wife and I prepare a home-cooked meal from the sponsor of this video, HelloFresh. HelloFresh has kid-friendly recipes for picky eaters, but this one's just for us. The meals take about 30 minutes to prepare, which is perfect for nap time because it's really hard to film yourself preparing lunch while chasing a toddler at the same time, especially when the photographer is 9 months pregnant. But our little helper just couldn't stand to be left out of the fun, so he woke up early anyway. Yes. HelloFresh also has different plans to meet your various nutritional or dietary goals like pescatarian, fit and wholesome, or vegetarian, which is what we usually get. It's a perfect way to make a change or try something new. And this is not just us being mean, by the way. He really loves lemons. And here's the most important thing. HelloFresh meals are delicious. We've done this for quite a while now, and there isn't a single recipe that we haven't enjoyed. Actually, we got invited to a party at the last minute, so we ended up combining the portions of this meal and bringing it to share. And it was a huge hit.
I said zigzag. Oh, that's pretty good.
Go try it yourself at HelloFresh.com, and if you use code PRACTICAL16, you'll you'll get up to 16 free meals plus 3 surprise gifts. I wouldn't recommend it if I didn't think you would love it. That's HelloFresh.com and use my code Practical16. Thank you for watching and let me know what you think. If you drive over a bridge at a major river or even a small creek, you're likely to see an equipment enclosure like this one nearby. Can you name that infrastructure? Pause the video here if you want to make a guess. Water is both one of our most important resources and one of the most destructive natural forces. So keeping track of the flow in rivers and streams is of critical importance to protect lives and property against flooding and ensure adequate water supply for the future. In the U.S., stream gauges are used to collect stream flow data over time. They're often installed on bridges next to major waterways. Most stream gauges actually measure the water level in a river using a pressure sensor, then convert that to the flow rate with some math. And you can take a look at all this data online at the USGS website. If you'd like to win a free copy of my new book, make a social media post about infrastructure like this one and include the hashtag Engineering in Plain Sight. More details at the link in the description. If you do much highway driving, you may come across a truck like this with some funny sensors hanging off the front or back. Can you name that infrastructure? Pause the video here if you want to make a guess. It might not always seem like it, but roadway owners put a lot of effort into making sure the pavement surface provides a smooth ride. We even have a measure of ride quality called the International Roughness Index, or IRI. It can be measured with a simple straight edge on the road, but these days we often use instruments called inertial profilers. It consists of lasers and accelerometers to keep track of a roadway's roughness. When a road's being resurfaced, pavement engineers check the IRI with a profiler to make sure it isn't too bumpy. If the roughness is too high, a grinder is used to smooth out the major bumps. Profilers are sometimes used as a tool for monitoring pavement condition over time, so you might see one of the spots on the highway measuring the roughness. Make sure you got a smooth ride. When the COVID-19 pandemic was just getting started, learning from the major cities, state health department, and federal agencies involved built out data dashboards to access online to check case counts and trends. Public health officials could constantly be heard asking everyone to flatten the curve, that curve being a graph of infection rates over time. But how do you get such a graph? By and large, our measure of the pandemic came through individual case counts, confirmed with laboratory testing, and reported to a data clearinghouse like the local public health department or the CDC. There was a lot of confusion about testing, positivity rates, how that information applies to the greater population, and how to measure the disease. The limitations of individual testing, including shortages, reporting delays, and unequal access to health care, made public health decisions extremely challenging. Much of the controversy surrounding mask mandates and stay-at-home orders was provoked by the disconnect between what we could reliably measure and the reality of the pandemic on the ground. Public health officials were constantly on the lookout for more indicators that could help inform decisions and manage the spread of disease. One of these measures didn't really show up in the online data dashboards, but it was and continues to be used as a broad measure of infection rates in cities. It's a topic that combines public health, epidemiology, and infrastructure that didn't get much coverage in the news. And there are both some interesting privacy implications and some really fascinating applications on the horizon. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about wastewater surveillance for public health. This video is sponsored by Brilliant, the best way to learn math and science through problem solving. More on them later. If you are unfamiliar with the inner workings of a modern municipal wastewater collection system, boy do I have the playlist for you. But if you don't want to watch 5 of my other videos before you watch this one, I can give you a 1-sentence rundown. Wastewater flows in sewers, primarily via gravity, combining and concentrating as it continues to a treatment plant where a number of processes are used to rid it of contaminants so it can be reused or discharged back into the environment. Just like a watershed is an area of land that drains to a specific part of the river or stream, a sewershed is an city that drains to a specific wastewater treatment plant. The largest sewer systems include hundreds of thousands or even millions of people. All of these waste flows to a single facility designed to be Wastewater treatment plants regularly collect samples of incoming sewage to characterize various constituents and their strengths. After all, you have to know what's in the wastewater to track whether or not it's been sufficiently removed at the other end of the plant. In the early days of sewage treatment, sampling consisted only of measuring the basic contaminants such as nutrients and suspended solids. But as our testing capabilities increased, it slowly became easier and less expensive to measure other impurities, sometimes known as contaminants of emerging concern. These included pharmaceuticals, pesticides, personal care products, and even illicit drugs. It didn't take too long to realize that tracking these contaminants was not only a tool for wastewater treatment, but also a source of information about the community within the sewershed, the gathering of which is a notoriously difficult challenge in the field of public health. Rather than coordinating expensive and arduous survey campaigns where many people aren't always truthful anyway, or going through the hoops of privacy laws to gather information from healthcare providers, we can just take a sample of sludge from the bottom of a clarifier, send it off to a lab, and roughly characterize in hours or days the dietary habits, pharmaceutical use, and even cocaine consumption of a specific population of people. If you're a public health researcher or public official, that is a remarkable capability. To quote one of the research papers I read, wastewater is a treasure trove of biological and chemical information. Think about all the stuff that gets washed down the drain and all the things you consume that might create unique metabolites that find their way out the other side of your excretory system. Although wastewater surveillance is a relatively new field of study, we're already able to measure illicit and illicit drugs, cleaning and personal care products, and even markers of stress, mental health, and diet. That's a lot of useful information that can be used to monitor public health, but one particular wastewater constituent took center stage starting in early 2020. Of course, for decades, we've tracked pathogens in wastewater to make sure they aren't released into the environment in treatment plant effort. But the COVID-19 pandemic created a vacuum of information on virus concentrations that had never been experienced before. We realized early in the pandemic that the SARS-CoV-2 virus is shed in the feces of most infected people. Even before widespread tests for the virus were available, many public health agencies were sampling the wastewater in their communities as a way to track the changes in infection rates over time. Realizing the importance of coordinating all these separate efforts, many countries created national tracking systems to standardize the collection and reporting of virus concentrations in sewage. In the U.S., the CDC launched the National Wastewater Surveillance System in September of 2020, complete with its own logo and trademark title. Let me know if you think I should try to license the design for my merch store. Individual communities can collect and test wastewater for SARS-CoV-2 and then submit the data to the CDC for a process called normalization. Virus concentrations go up and down with infections, but they also go up and down with dilution from non-sewage flows and changes in population. For example, in sewer sheds with large event venues or seasonal tourism. Normalization helps correct these factors so that comparison with virus and among communities is eliminated. There are some serious benefits from tracking wastewater surveillance. It's a non-intrusive way to monitor traffic that's really different from access to healthcare or even other infections that take them out. Next, orders of magnitude less expensive than individuals. Nearly 80% of U.S. households are served by a much more complicated precipitation counts come well after the onset of infection, so wastewater surveillance can provide the first clue of a COVID-19 spike, sometimes by several days. Finally, now that vaccination programs are widespread and there is significantly less testing being carried out, wastewater surveillance is a great tool to keep an eye out for a resurgence in COVID-19 infection, and it can even be used to monitor for new variants. Of course, wastewater surveillance has some limitations too, the biggest one being accuracy. The science is still relatively new, and there are lots of confounding variables to keep in mind. In addition to changes in dilution from other wastewater flows and sewership population mentioned before, the quantity of viruses shed varies significantly between individuals and even over the course of any one infection. Right now, wastewater surveillance just isn't accurate enough to provide a count of infected individuals within a population. So it's mostly useful in tracking whether infections are increasing or decreasing and by what magnitude. There are also some ethical considerations to keep in mind. That term surveillance should at least prick up your ears a little bit. Monitoring the constituents in wastewater at the treatment plant averages the conditions for a large population. But what if samples were taken from a lift station that serves a single apartment complex, school, or office building? What if a sample was taken from a manhole on the street right outside your house? Could the police department use the data to deploy more officers to neighborhoods where illicit drugs are found in the sewage? Could a city or utility provider sell wastewater data to private companies for use in research or advertising? That's a lot of hypotheticals, but I wouldn't be surprised to see a Black Mirror episode where some tech company provides free trash and sewer service just to collect and sell the data from each household. If you wanted to open a new coffee shop, how much would you pay to learn which parts of town have the highest concentrations of caffeine in the sewage? Maybe it would be called Brown Mirror. The truth is that public health professionals have put a tremendous amount of thought into the ethics and privacy concerns of wastewater surveillance. But, as with any new field of science, there are still a lot of questions to be answered. One of those questions is, what comes next in this burgeoning field of wastewater surveillance, where public health researchers have access to a literal stream of data? There are many measures of public health that can be valuable to policymakers and health officials, including stress levels, changes in mental health, and the prevalence of antimicrobial resistant bacteria, one of the greatest human health challenges of our time. Of course, all the work that went into standardizing and building out capabilities of tracking infections will certainly give us a leg up on resurgences of COVID-19 or any future new virus, heaven forbid. My weather report already has a lot more information than it did 20 years ago, including pollen counts of various allergy-inducing tree species, air pollution levels, and UV ray streams. We might soon see infection rates of the various diseases that spread through community populations to help individuals, planners, and public officials make better informed decisions about our health. Sewers were one of the earliest and most impactful advents of public health in urban areas, and it's exciting that we're still finding new ways to use them to that end. Wastewater surveillance requires a whole bunch of technical fields combining engineering, public health, and epidemiology. I think one of the easiest shortcuts to success is finding opportunities to mix and match areas of expertise like this. In niches, there are riches, as they say, but once you're out of school, it's much harder to gain technical knowledge in different industries. That's why I'm thankful for Brilliant, the sponsor of today's video, for providing interactive courses and topics that interest me, like this one about illicit drugs and wastewater. Sound familiar? My videos give a 1,000-foot overview of many parts of engineering, but maybe you're watching one of my videos and thinking, this is for me, this is what I'm interested in. Brilliant gives you the ability to dive into math and science topics so you can really learn them and get ahead in your studies or career. The website is beautifully designed, and they put a ton of effort into finding ways to help you gain technical knowledge and skills. Learn to think like a scientist, engineer, or epidemiologist completely free at brilliant.org/practical engineering. You don't pay anything to sign up, and the first 200 people that use the link will get 20% off an annual premium subscription. Again, it's completely free to sign up. That link is in the description. Thank you for watching, and let me know what you think. If you go peeking underneath bridges, you're likely to find a variety of interesting structural connections like this. Can you name that infrastructure? Pause the video here if you want to make a guess. Bearings transfer loads of a bridge's superstructure to the substructure. They literally bear the bridge's weight. Girders can't sit directly on supports below because bridges move. Superstructure forms and vibrates with traffic loads, expands under the glaring sun, and shrinks when it cools down. Without isolation of the substructure, these movements build up stress and potentially cause structural members to fail. Most modern bridges use elastomeric pads on their own or inside steel bearings super and substructure. But many boulders use cool-looking roller or rocket bearings to provide freedom of movement for I have two sections in my new book dedicated to bridges. If you'd like to win a free copy, social media post about it. Like this one, water flows in the soil and rock below our that the movement of groundwater is so secret, occult, and that it couldn't be regulated by law. Even now, the rules that govern groundwater and places are still well behind our collective knowledge of hydrogeology. So it's no surprise that misconceptions abound around water below the ground, and yet roughly half of all drinking water and irrigation water used for crops comes from underneath the surface of the earth. You can't really look at an aquifer, but you can look at a model of it around. And at the end of the video, I'll test out some of the latest technologies in aquifer architecture. I'm Brady, and this is Practical Engineering. In today's episode, we're talking about groundwater and wells. This video is sponsored by More on them later. Not all water that falls as precipitation runs off into lakes and rivers. Some of it seeps down into the ground through the spaces between soil and rock particles. Over time, this infiltrated water can accumulate into vast underground reservoirs. A common misconception about groundwater is that it builds up in subterranean caverns or rivers. Although they do exist in some locations, caves are relatively rare. Nearly all groundwater exists within geologic formations called aquifers that consist of sand, gravel, or rock saturated with water just like a sponge. It just so happens you're watching the #1 channel on the internet about dirt, and there are a lot of interesting things I can show you about how aquifers behave. I built this acrylic tank in my garage to illustrate some of the more intriguing aspects of groundwater engineering. I can fill it up with sand and add blue dye to create two-dimensional scenarios of various groundwater conditions. It also has ports in the back that I can open or close to drain various sections of the model. And on both sides, there's a separation that simulates a boundary condition on the aquifer. Water can flow through these dividers along their height. Most of the shots you'll see of this have been sped up because, compared to surface water, groundwater flows quite slowly. Depending on the size of soil or rock particles, it can take a very long time for water to make its way through the sinuous paths between the sediments. The property used to characterize this speed is called hydraulic conductivity, and you can look up average values for different types of soil online if you're curious to learn more. In fact, different geologic layers affect the presence and movement of groundwater more than any other factor, which is why there's so much variability in groundwater resources across the world. Like all fluids, groundwater flows from areas of high pressure toward areas of low pressure. To demonstrate this, I can set the left boundary level a little higher than the one on the right. This creates a pressure differential across the model so water flows from left to right through the sand. I added dye tablets in a few spots so you can see the flow. This is a simple example because the pressure changes linearly through a consistent material. But any change in these conditions can add a lot of complexity. In purely mathematical terms, you can consider this model a 2D vector field because the groundwater can have a different velocity, that is, direction and speed, at any point in space. Because of this, there are a lot of really neat analogies between groundwater and other physical phenomena. My friend Grant of the 3 Blue 1 Brown YouTube channel has an excellent video on vector field mathematics if you want to explore them further after this. We often draw a bright line between groundwater and surface water resources like rivers and lakes because they behave so differently. But water is water. It's all part of the hydrologic cycle, and many surface waters have a nexus with groundwater resources, meaning that changes in groundwater may impact the volume and quality of surface water resources and vice versa. Let me show you an example. In the center of my model, I've made a cross-section of a river. The drain at the bottom of the channel simulates water flowing along the channel, in this case, leaving my model. If I turn on the pumps to simulate a high water table in the aquifer, the groundwater seeps into the river channel and out of the model. The dye traces show you how the groundwater moves over time. If you encounter a situation like this in real life, you might see small springs, wet areas of the ground, and during the winter, even icicles along slopes where the groundwater is becoming surface water before your eyes. Likewise, surface water in a river can flow into the earth to recharge a local aquifer. I've reconfigured my model so the pump is putting water into the river and the outer edges of the reservoir are drained, simulating a low water table. Some of the water in the river flows back out of the model through the overflow drain, showing that while not all the water in the river seeps into the ground, some does. You can see the dye traces moving from the river channel into the aquifer formation, transforming from surface water into groundwater as it does. As you can see, surface water resources are often key locations where underground aquifers are recharged. This is all fun and interesting, but much of groundwater engineering has more to do with how we extract this groundwater for use by humans. That's the job of a well, which at its simplest is just a hole into which groundwater can seep from the surrounding soil. Modern wells utilize sophisticated engineering to provide a reliable and long-lasting source of fresh water. The basic components are pretty consistent around the world. First, a vertical hole is bored into the subsurface using a drill rig. Steel or plastic pipe called casing is placed into the hole to provide support so that loose soil and rock can't fall into the well. A screen is attached at the depth where water will be withdrawn, creating a path into the casing. Once both the casing and screen are installed, the annular space between them and the borehole must be filled. Where the well is screened, this space is usually filled with gravel or coarse sand called the gravel pack. This material acts as a filter to keep fine particles of the aquifer formation from entering the well through the screen. The space along the unscreened casing is usually filled with clay, which swells to create an impermeable seal, so that shallow groundwater, which may be lower quality, can't travel along the annular space into the screen. Wells use pumps to deliver water that flows into the casing up to the surface. Shallow wells can use jet pumps that draw water up using suction like a straw. But this method doesn't work for deeper wells. When you drink through a straw, you create a vacuum, allowing the pressure of the surrounding atmosphere to push your beverage upward. However, there's only so much atmosphere available to balance the weight of a fluid in a suction pipe. If you could create a complete vacuum in a straw, the highest you could draw a drink of water is around 10 meters or 33 feet. So deeper wells can't use suction to bring water to the surface. Instead, the pump must be installed at the bottom of the well so that it can push water to the top. Some wells use submersible pumps where the motor and pump are lowered to the bottom. Others use vertical turbine pumps where only the impellers sit at the bottom, driven by a shaft connected to a motor at the surface. All that pumping does a funny thing to an aquifer. I can show you what I mean in the model. As water is withdrawn from the aquifer, it lowers the level near the well. The further away from the well you go, the less influence it has on the level in the aquifer. Over time, pumping creates a cone of depression around the well. This is important because one well's cone of depression can affect the capacity of other wells and even impact nearby springs and rivers if connected to the aquifer. Engineers use equations and even computer models to estimate the changes in groundwater level over time based on pumping rate, recharge, and local geology. One fascinating aspect of deeper aquifers is that they can be confined. My model isn't quite sophisticated enough to show this well, but I can draw it for you. A common situation is that an aquifer exists at an angle to the ground surface. It can recharge in one location, but becomes confined by a less permeable geologic layer called an aquitard. Water flowing into a confined aquifer can even build up pressure, so that when you tap into the layer with a well, it flows readily to the surface, called an artesian well. It can happen in oil reservoirs as well, which is why you occasionally see oil wells blow out. A part of the construction of wells that I didn't mention yet is the top. A well creates a direct path for water to come out of an aquifer, and if not designed, constructed, and maintained properly, it can also be a direct path into the aquifer for contaminants on the surface. In my model, I can simulate this by dropping some dye into the well to represent an unwanted chemical spilled at the surface. Say some rainwater enters too, washing the contaminant through the well into the aquifer. Now, as groundwater naturally moves in the subsurface, it carries a plume of contamination along as well. You can see how this small spill could spread out in an aquifer, contaminating other wells and ruining the resource for everyone. So wells are designed to minimize the chances of leaks. The uppermost section of the angular space is permanently sealed, usually with cement grout. In addition, the casing is often extended above the surface with a concrete pad extending in all directions to prevent damage or infiltration to the well. We've been talking so much about how to get water out of an aquifer, but there are some times where we want to do the reverse. Injection wells are nothing new. Deep below ground can be a convenient and out-of-the-way place to dispose of unwanted fluid, including sewage, mining waste, salt water, and CO2. But until recently, it hasn't been a place to store a fluid with the intent of taking it back out at a later date. Aquifer Storage and Recovery, or ASR, is a relatively new technology that can help smooth out variability in water resources where the geology makes it possible. Large-scale storage of water is mostly restricted to surface water reservoirs formed by dams that are expensive and environmentally unfriendly to construct. With enough pressure, water can be injected through a well into an aquifer. You can see on my model that introducing water to the well causes the level of the aquifer to rise over time. Eventually, this water will flow away, but as I mentioned, groundwater movement is relatively slow. In the right aquifer, you won't lose too much water before the need to withdraw it comes again. Taking advantage of the underutilized underground seems obvious, but there are some disadvantages too. You need a Goldilocks formation where water won't flow away too fast, but is also not so tight that it takes super high pressure for injection. You also need a geologic formation that is chemically compatible with the injected water to avoid unwanted reactions and bad taste. Of course, you always have cost, and ASR systems can be expensive to operate because the water has to be pumped twice, once on the way in and again on the way out. Finally, you can have issues with speed. In many places, the surplus water that needs to be stored comes during a flood, massive inflows that arrive over the course of a few hours or days. A dam is a great tool to capture floodwaters in a reservoir for later use. Injection wells, on the other hand, move water into aquifers too slowly for that. They're more appropriate where surplus water is available for long durations. For example, one of the few operating ASR projects is right here in my hometown of San Antonio. When water demands fall below the permitted withdrawals from our main water source, the Edwards Aquifer, we take the surplus and pump it into a different aquifer. If demands rise above the permitted withdrawals, we can make up the difference from the ASR. You can add more injection wells to increase the speed of recharge, but above a certain pressure, some funny things start to happen. Underground formations break apart and erode in a phenomenon called hydraulic fracturing, or just fracking. Breaking apart underground formations of rock and soil has been a boon for the oil and gas industry, but just like the Texas groundwater in 1904, the regulation of fracking is mired in confusion and controversy, in no small part because it happens below the surface of the earth, hidden from public view. I'll save those details for a future video. And if you're eager to see the next practical engineering episode as soon as possible, you should know that my videos go live on Nebula before they're released here on YouTube. Nebula is a completely ad-free streaming service built by and for your favorite independent creators like Windover Productions, Real Engineering, and me. It's a way for us to try new ideas and longer videos that might not work well on advertising-supported platforms like YouTube. And we're super excited to continue our partnership with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and if you add them all up, it would be hundreds of dollars a month. That's why this bundle is such an awesome deal. You get access to 2 platforms, Nebula and CuriosityStream, for less than $15 a year. I love space exploration, and CuriosityStream has a bunch of excellent documentaries on the topic, including this one on building the James Webb Telescope that recently launched. Or watch Sam from Windover Productions try to break the law while evading his production team in the Nebula exclusive series Crime Spree. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. This is a photo I took on a walk near my house. It might look like a mess of transmission wires, but there's something slightly special about this tower. Can you name that infrastructure? Pause the video here if you want to make a guess. This transmission tower is a tension structure, and you can tell because the insulators are in line with the conductors, pulling them horizontally. Most electrical transmission towers are suspension structures, where each conductor hangs vertically from a single insulator. The forces they have to withstand are mostly just the vertical loads from gravity. But anytime a transmission line reaches a dead end or needs to turn a different direction, the conductors create an unbalanced horizontal force on the tower. So a tension structure has two sets of strain insulators supporting each conductor in both directions, with a jumper in between. The tower itself is often much stronger because the forces are greater. You can usually see the difference in the thickness of the steel members between a suspension and tension structure. Since 2011, the Russian energy corporation Gazprom and a group of large investors have been working on one of the longest and highest capacity offshore gas pipelines in the world. The Nord Stream 2 is a pair of large diameter natural gas pipelines running along the bottom of the Baltic Sea from the Russian coast near St. Petersburg to the northern coast of Germany near Greifswald. Planning, design, and construction of Nord Stream 2 was mired in political controversy, not only because of climate-related apprehensions over new fossil fuel infrastructure, but also over concerns that the pipeline could be used as a geopolitical weapon by Russia against other European countries. Still, construction began in 2016 and finished 5 years later at the end of 2021. As the German government worked towards certifying the pipeline to begin operation, Russia launched a military invasion of Ukraine. This unjustified and unconscionable attack on a sovereign nation has received widespread international condemnation, followed up with a military sanctions on Russia and Ukraine. Part of the response included Germany halting the certification of this divisive $10 billion measure. As of this video, the invasion of Ukraine is ongoing, and international relations between Russia and most of the world are unlikely to improve anytime soon. The U.S. put sanctions on the company in charge of the pipeline and senior officers. The project's website has been taken offline, and most of the employees have been fired. These circumstances raise plenty of questions. How do you install a pipeline at the bottom of the Baltic Sea? Why is this line so important to geopolitics? And what does the future hold for what may be the world's most controversial infrastructure project? I'm Grady, and this is Practical Engineering. Today's episode is talking about international oil and gas firms. The project has a long, complex, and controversial history. This video highlights planning phase for the pipeline involved detailed underwater surveys. World War I where possible, the pipeline was routed around these conditions. It had to be detonated in place, and this was done. The contractors used bubble curtains around each explosion to mitigate the noise impacts on marine life. The logistics of producing so much pipe was also a huge challenge. The pipe sections used for the Nord Stream 2 were about 1,150 millimeters, or 45 inches in diameter, and 12 meters, or 40 feet long. They started out as steel plates that were rolled into pipe sections, welded, stretched, beveled, and inspected for quality. An interior epoxy anti-friction coating was applied to minimize the pressure losses in the extremely long line. Then an exterior coating was applied to protect against corrosion in the harsh saltwater environment. And the entire project required manufacturing of 100,000 of these pipe sections. The average doubling the weight of each pipe from 12 to 4 to help resist buoyancy underwater currents over time. It also provided transport after weight coating, the pipes were shipped to storage yards along the coast, and within large pipe lay vessels working in the Baltic Sea. These pipe lay vessels were floating factories employing hundreds of workers each, and the Nord Stream 2 project had up to 5. On the large vessels, the basic process for pipe laying was first to weld two pipe sections together to create what's called a double joint. These welds got a detailed inspection, and if they passed, the double joint moved to a central assembly line connected to the main pipe string. There you got more welding and inspection. If everything checked out, a heat shrink sleeve was placed around each weld, and then polyurethane foam poured into a mold between the concrete coating to further protect against corrosion while allowing the pipe string to flex during placement. Once complete, the vessel could advance a little further along the route while lowering the pipeline into its final position. This was a 24/7 operation, and some of these pipe lay vessels could complete 3 kilometers in a day. In many locations, they could just lay pipe directly on the seabed. It was smooth enough to keep the line from deflecting too much and soft enough to avoid damage to the pipe. However, that wasn't the case along the entire route. In some shallow waters where the pipelines were exposed to hydrodynamic forces like waves and currents, the lines were placed in excavated trenches and backfills. There were also many that were rugged enough to create free sand and unsupported pipe. All pipe vessels were deployed ahead of the pipe position to fill the sections with rock and gravel to provide a smoother path along the seabed for the line. Finally, at locations where the Nord Stream 2 lines would cross other sections of the power this amount of infrastructure as well. At the German rainfall, the pipe was tunneled on shore to these devices launched a second pipeline along with gas turbines for the entire 1,200 kilometers. Scanned for problems like corrosion or mechanical damage and collect data that can be downloaded when they reach the end of the line in Germany. Installing but a serious challenge is that has already been installed along the most impressive application of the entire project, the above water separate pipelines carefully installed on the sea tie them together. First, divers installed buoyancy tanks to each end to make them alongside of the tie-in vessel attached to each pipe and lifted their ends above the waterline. These ends didn't have a concrete weight coating to make them lighter and able to be cut to the exact length needed. The pipes were cut and beveled, welded, tested, and coated for corrosion protection. Finally, the tie-in vessel could lay the complete pipe back down on the seafloor, forming a small horizontal arc off the main alignment where divers removed the buoyancy tank and detached the crane. The Nord Stream 2 required several above-water tie-ins during construction. It seemed simple enough, but each one took about 3 weeks to complete. The final AWTI was completed in September 2021, marking the end of construction of the Nord Stream 2. Although Europe's in the midst of a major transition away from fossil fuels to renewable sources, the demand for natural gas is still high. Nord Stream 2 would also allow more Russian gas to bypass Ukraine, depriving it of the transit fees it gets from gas lines through its borders. As early as 2016, politicians in various countries around the world were coming out in opposition to the project. They were stopped Nord Stream 2 U.S. President Biden wished that in mid-2021 approved U.S. regulations, but the Russian invasion of Ukraine changed everything. The U.S. immediately reimposed the sanctions, and Germany froze certification of the project. The Nord Stream 2 company has been mostly silent so far, but there aren't many good outcomes of spending $10 billion on design and construction of a pipeline that can't be used. Most news sources appear to agree that they are completely insolvent and have fired all their employees. In addition, most of the non-Russian companies involved in the project have already written off their investments and walked away. This simple pipeline highlights the tremendous complexity of infrastructure and geopolitics. It can be extremely difficult for a normal citizen to know what they stand to gain or lose from a project like this. We want cheap energy, we want warm homes during the winter, but we don't want the global climate to change, and we definitely don't want the current conditions guided towards the future. In some ways, Putin's invasion of Ukraine the U.S. no choice. There's a lot of uncertainty right now how the constitution and what the world will look like in the next 7 years. This incredible advancement in engineering, logistics, and maritime construction will ever be anything more than a tube of concrete and steel at the bottom of all the maybe that's for the best. Thank you for watching, and let me know what you think. I live here in San Antonio, and if you look around town, you'll start to notice tiny especially at parks and golf courses. That color has a special meaning in plumbing. Can you name that infrastructure? Pause the video here if you want to make a guess. These purple pipes carry recycled water, a friendly term for treated domestic wastewater that keeps wastewater is clean and green, but it's more than just enough to water the grass or add to a river to supplement its flow. Instead of discarding it, San cross connections with the drinking water supply, and San Antonio's recycled water system is one of the largest in the nation. I have a whole chapter in my new book, Engineering in Plain Sight, dedicated to water infrastructure. If you'd like to win a free copy, make a social media post about infrastructure like this one and include the hashtag Engineering in Plain Sight. More details at the link in the description. I'm on a mission to show the world how engrossing human management of sewage can be. And in fact, we followed the flow of domestic wastewater through sewers, lift stations, and primary treatment in videos on Instagram. We watched probably the most misguided thing I've ever done with a video. So I got to thinking about other ways to use co-op and there's one obvious equivalent of making alcoholic drinks. So I got a couple of gallons of apple cider and don't revive, whether by law or by choice, I promise you'll enjoy seeing the similarities and differences between cleaning up domestic wastewater and the ancient art form of fermenting beverages. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about secondary wastewater treatment and a little bit about home brewing, too. This video is sponsored by HelloFresh, America's #1 meal kit. More on them later. You probably don't think about cellular biology when you consider civil engineering. Even though we're made of cells just like everything else, we're associated more with social, time, and nitrogen, phosphorus, and other compounds. You can't just release this stuff into a creek, river, or ocean because the microbes already in the destination water, like bacteria and algae, will respond by out of water. At the molecular scale, nutrients are much harder to separate from sewage than other contaminants. Like domestic wastewater, making a fermented beverage starts with concentration in brewing is pretty simple. Dissolved sugars increase the density or specific gravity of the liquid. This class tool is called a hydrometer, and it floats upright when suspended in a liquid. Just like a ship higher in seawater than it does in fresh water, a hydrometer floats to a different height depending on the density of the fluid. The more sugar, the higher the hydrometer rises. On the other hand, characterizing the strength of sewage is equally as important, but a little more complicated. For one, not all nutrients change the density of a fluid. More importantly, there are a lot more of them than just sugar, and they can all exist at different strengths. So rather than trying to separate all the complexities, we usually just measure what matters most. How much dissolved oxygen would organisms steal from the water to break down the nutrients in the sample? The technical term for this is biochemical oxygen demand, or BOD. In general terms, treatment plant operators measure the amount of oxygen dissolved in a sewage sample before setting it aside for a 5-day period. During that time, critters in the sample will eat up some of the nutrients, robbing the dissolved oxygen as they do. The difference in oxygen before and after the 5 days is the BOD. Once you know your initial concentration of nutrients, whether sugars or other stuff, you can work on a way to get them out of there. In both sewage and brewage, we expropriate tiny biological buddies for this purpose. In other words, we use them to our advantage. Wastewater treatment plants rely primarily on bacteria, with some protozoa as well. There are a myriad of secondary treatment processes used around the world, but one is more common than all the rest, and it has the best name too: activated sludge. After the primary treatment of removing solids from the flow, wastewater passes into large basins where enormous colonies of microorganisms are allowed to thrive. At the bottom of the basins are diffusers that bubble prodigious quantities of air up through the sewage, dissolving as much oxygen as possible into the liquid and maximizing the microorganisms' capacity to consume organic material. This combination of wastewater and biological mass is known as mixed liquor, but that's just a coincidence in this case. Either way, you definitely don't want to be drinking too much of it. Fermentation of an alcoholic beverage, the process where sugars are converted to ethanol, works a little bit differently. First, the microorganisms doing the work in fermentation are yeast. These are single-celled organisms from the fungus kingdom, in some ways similar, but in many ways quite unlike the bacteria and protozoa in a wastewater treatment plant. In fact, brewers work pretty hard to keep equipment clean and sanitized so that bacteria can't colonize the brew. The foam you see in processes is air. Except at the very beginning, when the yeast are first expanding their population, fermentation is an anaerobic process. That means it happens in the absence of oxygen. A wastewater treatment plant adds air to speed up the process. However, yeast exposed to oxygen stop producing alcohol, so the vessel is usually sealed to minimize the chances of gas. The bubbles you see are carbon dioxide that the yeast create in addition to the ethanol. The airline lets the carbon dioxide in so it can build up pressure without letting terrible contaminants out. My cider started by volume. However, just like the outflow from an activated sludge, it's not quite ready to drink. But the basics are pretty simple. Most solid particles, including microorganisms, are denser than water and thus will sink. But they sink slowly, so you have to keep the liquid still for this type of separation to work well. Wastewater treatment plants use settling tanks called clarifiers that send the mixed liquor slowly from the center outward so that it drops the sludge of microorganisms to the bottom of the ledge, leaving clear oxygen passed over a weir round the tank. Similarly, you can see a nice layer of mostly dead yeast on the bottom of my fermentation vessel, typically called the lees or probe. Homebrewers use a process called racking, which is just siphoning the liquid from the fermentation vessel while leaving the solids behind. In both cases, these microorganisms are not all dead. That's where the activated sludge comes from. A rotating arm in the clarifier pushes the sludge to a center hop. From there, it's collected and returned to the aeration, which receives the next colony that will treat the wastewater in generally ready to be safely released into a nearby watercourse, and my tummy respectively. However, there are some final tasks that may be wanted or needed in both cases. As you can see, my heart I'm not going to carbonate it in this video, but that is an extra step that many cider makers and most beer brewers take. I will add an enzyme that helps clear up the haze from the unfiltered apple juice. It doesn't make it taste any different, but it does look a lot nicer. Like the finishing steps of home brewing, many wastewater plants use tertiary treatment processes to target other pollutants that bugs could get. Depending on where the effluent is going, standards might require more purification than primary and secondary treatment can achieve on their own. In fact, wastewater treatment plants have been experiencing a relatively dramatic shift over the past few decades as they treat sewage less like a waste product and more like an asset. After all, raw sewage is 99.9% water, and water is a valuable resource to cities. In places with water scarcity, it can be cost-effective to treat municipal wastewater beyond what would typically be required so that it can be reused instead of discarded. A few places across the world have potable reuse, also known as toilet to tap, where sewage is cleaned to drinking water quality standards and reintroduced to the distribution system. Wichita Falls, Texas, and the International Space Station are notable examples. However, most recycled water isn't meant for human consumption. Plenty of uses don't require potable water, including industrial processes and the irrigation of golf courses, athletic fields, and parks. Many wastewater treatment plants are now considered water reclamation plants because instead of discharging effluent to a stream or river, they pump it to customers that can use it, hopefully reducing demands on the potable water supply as a result. In many countries, purple pipes are used to distinguish non-potable water distribution systems, helping to prevent cross connections. And sometimes you'll see signs like this one to prevent people from getting sick. On the other hand, practical engineering's effervescent effluent, when enjoyed responsibly, is perfectly safe to drink. With them before, HelloFresh sponsored this video for converting cooking from a chore into one of our favorite ways to spend family time together. We're even trying out a new kitchen stool for our little help.
I wonder if you're going to regret leaving that
A little less than eager for the baby, something that's soon to be twice as big for us. So we love that HelloFresh meals come together quickly. We even have options for 20-minute meals and low prep because anyone with a toddler knows how hard it is. My wife is not so approving of all of my methods.
Except for doing nice.
We also have options for family-friendly meals, pescatarian, vegetarian, and more. So it's a really nice way to jumpstart a change in your diet or just try something new. Jack Byer is an aerospace photographer traveling to Texas regularly to shoot the SpaceX Starship tests. He sent me these photos of strange concrete pipes sticking vertically from the ground. Can you name that infrastructure? Pause the video here if you want to make a guess. These are irrigation standpipes that help regulate the pressure and flow from canals or pumps into the underground pipelines that deliver water to fields. They serve as a small tank to store water, a place for gates that can control the flow, a place where air can escape from underground lines, and surge tanks to absorb spikes in pressure that could damage the pipes. Look for them in areas like California's Central Valley and the lower Rio Grande River Valley of Texas. I have a whole chapter in my new book, Engineering in Plain Sight, dedicated to water infrastructure. If you'd like to win a free copy, make a social media post about infrastructure like this one and include the hashtag Engineering in Plain Sight. More details at the link in the description. I'm standing in front of a pair of water towers near my house in San Antonio. If you've seen my video on water towers, or you just know how they work, they might look a little odd to you. It's not only unusual that there are two tanks right next to each other, but that they're completely different heights. This difference is a little hint that there's something more interesting below the surface here. Some engineering achievements are visibly remarkable. It's easy to celebrate the massive projects across the world. River dams and the Golden Gate bridges, but it's just as easy to overlook the less notable infrastructure all around it. So many ideas to know that I'm In today's episode, I misguidedly chose the coldest day of the year to film my first on-location video here in my home city to talk about a few of my favorite parts of the constructed environment. Luckily, the drone footage was taken on a sunnier day. You may have guessed already that these two towers aren't connected to the same water distribution system. If they were, water would just drain out of the upper tank and overflow the lower one. San Antonio actually has a second system that takes recycled water from sewage treatment plants and delivers it to golf courses, parks, and commercial and industrial customers throughout the city. Treated wastewater isn't clean enough to drink, but it's more than clean enough to water the grass or use in a wide variety of industrial processes. So, instead of discarding it, treat it as a delivering it to customers that can use it. That reduces the demand on potable water supply, which is scarce in this part of Texas. Some people notice the tumbling pipe system because recycled water pipes have a nice lavender shade, differentiating them from any cross connection. San Antonio actually has one of the largest recycled water delivery systems in the country. This water tower is one of the biggest used to supply and demand recycled water around. Unefficient historic landmark in San Antonio. It may just look like a typical concrete wall, but the almost dam is one of the most important This restoration was built in 1927 after a massive flood demolished much of downtown. A roadway along the top of the dam had electric lights and was a popular diving destination with nice views. The roadway since was replaced by a more hydraulic I have a special connection with this dam because I worked as an intern on a rehabilitation project at the engineering firm hired to design the repairs. The project involved the installation of about 70 post-tension anchors to stabilize the dam against extreme loads from flooding. Each anchor was drilled through the structure and grouted into the rock below. Then a massive hydraulic jack was used to tension the strands and lock each anchor off at the top to stitch the dam to its foundation like gigantic steel rubber dams. The contractor even had to use a special drill rig to fit underneath the highway bridge. San Antonio's in the heart of flash flood out in Texas. Allowing floodwaters to bypass the most vulnerable developed areas and saving hundreds of millions of dollars in property damages from flooding. When in use, floodwaters in the tunnel flow down up a vertical shaft and come out here at the flood control tunnel outlet on the Missouri to the San Antonio River. Under normal conditions, there are pumps that can recirculate river water through the tunnel, keeping things from getting stagnant and providing a fresh supply of water to flow through the downtown river wall. This part of the San Antonio River, south of downtown, is one of my favorite places because it's a perfect example of how urban and natural areas can coexist. When you think about infrastructure and construction, you typically think about concrete, steel, and hard surfaces, but this part of the San Antonio River was included in one of the largest ecosystem restoration projects in the U.S. Before the project, This was your typical, ugly, channelized urban river, but now it's been converted to a much more natural state, with native vegetation and its original meandering path. But the project didn't only improve the habitat along the river, it also included recreational improvements to make this stretch a destination for residents and tourists. For example, these grade control structures help keep the river from eroding downward, but they also feature canoe shoes, so you can paddle the river without interruptions. There are several new parks along the river, including Confluence Park, home to this beautiful pavilion made of concrete pedals. Most importantly, there's a continuous, dedicated hike and bike trail along the entire stretch. Everyone knows about the Alamo because of the famous battle, but there are actually 5 Spanish missions established in the early 1700s along the San Antonio River. The sites together are now a historic national park and a UNESCO World Heritage Site. You can tour the missions to learn about the history of Spanish colonialism and interwoven cultures of Spain and the indigenous people of Texas and Mexico. The Mission Reach Trail provides a connection to all the missions and a bunch of other interesting destinations along the river, including parks, public art, and my favorite spots, the historic and modern water control infrastructure projects. So far, all the structures I've shown you have been water related. That's my professional background, but we could do similar deep dives just here in San Antonio about the power grid, highways, bridges, telecommunications, and even construction projects. And preferably on warmer days, we could do similar field guides in every urban area around the world. In fact, that's the premise of my new book, Engineering in Plain Sight, an illustrated field guide to the constructed environment. I've been working so hard on this project for the past few years, and I'm thrilled to finally tell you about it. Just like there are written guides to birds, rocks, and plants, Engineering in Plain Sight is a field guide to infrastructure that provides colorful illustrations and accessible explanations of nearly every part of the constructed world around us. It's essentially 50 new practical engineering episodes crammed between 2 covers. Imagine if you could look at the world through the eyes of the engineers who designed the infrastructure you might not even be noticing in your everyday life. I wrote this book with the goal of transforming your perspective of the built environment, and I think once you read it, you'll never look at your city the same again. You can explore it like an encyclopedia, picking pages in no order, or treat the sites of your city's infrastructure like a treasure hunt and try to collect them all. The book comes out in August, but I would love if you pre-order your copy right now because in the world of books, pre-sales are the best way to get the attention of bookstores and libraries. If you pre-order directly from the publisher, you'll get a discount off the regular price, and you can pre-order signed copies directly from my website that come with an exclusive enamel pen as a gift. Pre-ordering is the only way to get your hands on this custom pen that was designed by the book's illustrator. Use the link in the description to find all the pre-order locations. And one more thing, between now and when the book publishes, I'm going to be posting some short explainers about interesting infrastructure on all my social media channels, and I want to encourage you to do the same. I'll be sending 5 signed copies of my new book and my favorite social media posts about infrastructure that use the hashtag Engineering in Plain Sight. Check out the link below for more information. And from the bottom of my heart, thank you for watching, and let me know what you think. This is the Stickney Water Reclamation Plant in Chicago, the largest wastewater treatment plant in the world. It serves more than 2 million people in the heart of the Windy City, converting all their showers, flushes, and dirty dishwater, plus the waste from countless commercial and industrial processes, into water safe enough to discharge into the adjacent canal, which flows eventually into the Mississippi River. It all adds up to around 700 million gallons, or 2.5 billion liters of sewage each day, and the plant can handle nearly double that volume on peak days. That's a lot of Olympic-sized swimming pools, and in fact, the aeration tanks used to biologically treat all that sewage almost look like something you might do a lap or 2 in, even though there are quite a few reasons you shouldn't. However, flanking those big rectangular basins are rows of circular ponds and smaller rectangular basins that have a simple but crucial responsibility in the process of treating wastewater. We often use chemicals, filters, and even gigantic colonies of bacteria to clean sewage on such a massive scale. But the first line of defense in the fight against dirty water is usually just gravity. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about settlement for water and wastewater treatment. This video is sponsored by Wellfund. More on them later. This video is part of a series on municipal wastewater handling and treatment. Rather than put out a single video overview of treatment plants, which many other channels have already masterfully done, we're taking a deep dive into a few of the most interesting parts of converting sewage into clean water. Check out the wastewater playlist linked in the card above if you want to learn more. The job of cleaning water contaminated by grit, grime, and other pollutants is really a job of separation. Water gets along with nearly every substance on Earth. That's why it's so useful for cleaning, and a major part of why it does such a good job carrying our waste away from homes and businesses and sewers. But once it reaches a wastewater treatment plant, we need to find a way to separate the water from its inhabitant wastes so it can be reused or discharged back into the environment. Some contaminants chemically dissolve into the water and are difficult to remove at municipal scales. Others are merely suspended in the swift and turbulent flow and will readily settle out if given a moment of tranquility. That's the trick that wastewater treatment engineers use as the first step in cleaning wastewater. Once it passes through a screen to filter out sticks and rags, sewage entering a wastewater treatment plant's first step, or primary treatment, is the simple process of slowing the wastewater down to allow time for suspended solids to settle out. How do you create such placid conditions from a constant stream of wastewater? You can't tell people to stop flushing or showering to slow down the flow. Velocity and volumetric flow are related by a single parameter, the cross-sectional area. If you increase this area without changing the flow, the velocity goes down as a result. Basins used for sedimentation are essentially just enormous expansion fittings on the end of the pipe, dramatically increasing the area of flow so the velocity falls to nearly zero. But just because the sewage stream is now still and serene doesn't mean impurities and contaminants instantly fall to the bottom. You gotta give them time. How much time is a pretty important question if you're an engineer because it affects the overall size of the basin and thus it affects the cost. Particles falling out of suspension quickly reach a terminal velocity, just like a skydiver falling from a plane. That maximum speed is largely a function of each particle's size. And I have a demonstration here in my garage to show you how that works. I think it's intuitive that larger particles fall through a liquid faster than smaller ones. Compare me dropping a pebble to a handful of sand. The pebble reaches the bottom in an instant, while the smaller particles of sand settle out more slowly. Wastewater contains a distribution of particles from very small to quite large, and ideally we want to get rid of them all. As an example, I have two colors of sand here. I sifted the white sand through a fine mesh, discarding the smaller particles and keeping the large ones. I sifted the black sand through the same mesh, this time keeping the fine particles and discarding the ones retained by the sieve. After that, I combined both sands to create a gray mixture, and we'll see what happens when we put it into a column of water. This length of pipe is full of clean water, and I'm turning it over so the mixture is at the top. Watch what happens as the sand settles to the bottom of the pipe. You can see that, on the whole, the white sand reaches the bottom faster, while the black sand takes longer to settle. The two fractions that were previously blended together separate themselves again just from falling through a column of water. Of course, physicists have used sophisticated fluid dynamics with partial differential equations to work out the ideal settling velocity of any size of spherical particle in a perfectly still column of water based on streamlines, viscosity, gravity, and drag forces. But we civil engineers usually just drop them in water and time how quickly they fall. After all, there's hardly anything ideal about a wastewater treatment plant. As water moves through a sedimentation basin and individual particles fall downward out of suspension, they take paths like the ones shown here. Based on this diagram, you would assume that depth of the basin would be a key factor in whether or not a particle reaches the bottom or passes through to the other side. Let me show you why settling basins defy your intuitions with just a tiny bit of algebra. You've got a particle coming in on the left side of the basin. It has a vertical velocity, that's how fast it settles, and a horizontal velocity, that's how fast the water is moving through the basin. If the time it takes to fall the distance d to the bottom is shorter than the time it takes to travel the length L of the basin, the particle will be removed from the flow. Otherwise, it will stay in suspension past the settling basin. That's what we don't want. As I mentioned, the speed of the water is the flow rate divided by the cross-sectional flow area. That's the basin's width times its depth. Since both the time it takes for a particle to travel the length of the basin and the time it takes to settle to its bottom are a function of the basin's depth, the term cancels out, and you're left only with the basin's length times width. In other words, its surface area. That's how we measure the efficiency of a sedimentation basin. Divide the flow rate coming in by the surface area, and you get a speed that we call the overflow, or surface loading rate. All the particles that settle faster than the overflow rate will be retained by the sedimentation basin, regardless of its depth. Settlement is a cheap and efficient way to remove a large percentage of contaminants from wastewater, but it can't remove them all. There are a lot more steps that follow in a typical wastewater treatment plant, but in addition to being the first step of the process, settlement is also usually the last one as well. Those circular ponds at the Stickney plant in Chicago are clarifiers used to settle and collect the colonies of bacteria used in the secondary treatment process. Clarifiers are just settlement basins with mechanisms to automatically collect the solids as they fall to the bottom. The water from the secondary treatment process, called mixed liquor, flows up through the center of the clarifier and slowly makes its way to the outer perimeter, dropping particles that form a layer of sludge at the bottom. The clarified water passes over a weir so that only a thin layer farthest from the sludge can exit the basin. A scraper pushes the sludge down the sloped bottom of the clarifier into a hopper where it can be collected for disposal. Settlement isn't only used for wastewater treatment. Many cities use rivers and lakes as sources of fresh drinking water, and these surface sources are more vulnerable to contamination than groundwater. So they go through a water purification plant before being distributed to customers. Raw surface water contains suspended particles of various materials that give water a murky appearance called turbidity and can harbor dangerous microorganisms. The first step in most drinking water treatment plants is to remove these suspended particles from the water. But unlike the larger solids in wastewater, suspended particles creating turbidity in surface water don't readily settle out. Because of this, most treatment plants use chemistry to speed up the process. I have a little demo of that set up here in the studio. I have 2 bottles full of water that I've vigorously mixed with dirt from my backyard. One will serve as the control, and the other as a demonstration. The reason these tiny soil particles remain suspended without settling is that they carry an electrical charge. Therefore, the particle repels its weight, fighting the force of gravity and preventing them from getting too close to each other. Chemicals coagulate to neutralize the electric charges, so tiny particles can no longer pumps and pipes against damage, with canals to keep them from silting, in fish hatcheries, mining, farming, and a whole host of other processes that create or rely on dirty water. The science of sedimentation and settlement is hopefully are intimidated by the world of investing. It seems complicated, like there's so much to learn and keep track of, especially when the stakes are your own savings. But time is your biggest asset when investing. Wealthfront simplifies investing and walks you through the process of building and managing a portfolio based on your risk tolerance. All you need is a few minutes. $5,000 in assets for free for life. Give it a try today at the link in the description. Supporting our sponsors helps support US and Canada. It was the most significant power outage ever in North America, with an economic impact of over $1 240-page report on all the technical causes of the event that I'll try to summarize here. Even though this is kind of an older story and many of the tough lessons have already been learned, it's still a nice case study to explore a few of the more complicated and nuanced aspects of operating the electric grid, essentially one of the world's largest machines. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the Northeast Blackout 2003. Nearly every aspect of modern society depends on a reliable supply of electricity, and maintaining this reliability is an enormous technical challenge. I have a whole series of videos on the basics of the power grid if you want to keep learning after this, but I'll summarize a few things here. And just to note before we get too much further, when I say the grid in this video, I'm really talking about the Eastern Interconnection that serves the eastern two-thirds of the continental U.S., plus most of eastern Canada. There are two big considerations to keep in mind concerning the management of the power grid. One, supply and demand must be kept in balance in real time. Storage of bulk electricity is nearly non-existent, so generation has to be has effects on the entire system, some of which can be unanticipated. Finally, we should summarize how the grid is managed. Each individual grid is an interconnected network. Monitored flows over transmission lines to keep them from overloading, prepared for emergencies, and made long-term plans to there were smaller reliability coordinators who performed the day-to-day grid management and oversaw control areas. August 14th was a warm summer day. It started out fairly ordinary in the U.S. Before any major outages began, conditions on the electric grid, especially in northern Ohio and eastern Michigan, were slowly degrading. Temperatures weren't unusual, but they were high, leading to an increase in electrical demand from air conditioning. In addition, several generators in the area weren't available due to forced outages. Again, not unusual, the Midwest Independent System Operator, or MISO, the area's reliability coordinator, took all this into account in their forecast and determined that the system was in the green and could be operated safely. But three relatively innocuous events were followed by a series of transmission line outages outside of MISO's area. Reliability coordinators received lots of real-time data about the there's a lot of validation, but there's a lot of More specifically, it couldn't converge on a solution. The state estimator was saying, "Sorry, all the data you keep starting around into another tool called a real-time contingency analysis, or RTCA, that takes the estimated state and does a variety of what-ifs. What would happen if this generator tripped? What would happen if this transmission line went offline? What would happen if the load increased over here? Contingency analysis is critical because you have to stay ahead of the game when operating the grid. Their guidelines require that each control area manage its network to avoid cascading outages. That means you have to be to ensure that you're operating within guidelines at any point in time. You run simulations of those contingencies, make sure the grid would survive, and meet those RTCAs, which was usually run after every major change in grid conditions, sometimes several times per day, was offline on August 14th, up until around 2 minutes before the start of the cascade. That means you couldn't see the vulnerability out there, issuing warnings for their control area operators, including First Energy, the operator of a control area in northern Ohio, in Toledo, Akron, and Cleveland. That afternoon, First Energy was struggling to maintain adequate voltage within their area, although their conditioners use induction motors that spin in a magnetic field using coils of wire inside. Inductive loads do a fun thing to the power on the grid. Some of the electricity used to create the magnetic field isn't actually consumed, but just stored momentarily and then returned to the grid. Each time the current switches direction, it's 125 per second. This causes by dividing bulk power into two parts: real power, measured in watts, and reactive power, measured in bar. On hot summer days, grid operators need more reactive power to balance the increased inductive loads of the system caused by millions of air conditioners running simultaneously. Real power can travel long distances on transmission lines, but it's not economical to import reactive power from far away because transmission lines have their own inductance that consumes the reactive power as it travels along. With only two running generators within the community area, First Energy receives a lot of real power from other areas. That's what ultimately we're still getting on their part of the grid and power to go around. The capacitor rings are often used to help bring current and voltage back into sync, providing power. However, First Energy was out of service on the 14th. Another option is to overexcite nearby power so that they create more reactive power, and that's just what First Energy did. At the East Lake coal-fired plant on Lake Erie, operators amplified units to the grid, trying to get as much reactive power as they could. Fortunately, around 1:30 in the afternoon, first thing to go was the alarm system designed to notify operators when equipment had problems. This probably doesn't need to be said, but alarms are important in grid operations. People in the control room don't just sit and watch the voltage and current levels as they move up and down over the course of the day. Their entire workflow is based on alarms that show up on screen on change notifications so they can respond. All the data was coming in, but the system designed to get an operator's attention was stuck
These are only the 345 kilovolt lines, but there are lower voltage transmission lines in the area as well. Transmission lines heat up as they carry more current due to resistive loss, and that's exacerbated by heat up, they expand and lower the ground at around 80 o'clock. Power the Harding Chamberlain transmission line, a key asset for supporting power conveyors, sagged into a ceiling, creating a short circuit. The relays monitoring current on the line recognized the fault immediately and tripped it offline. Operators in the First Energy Control Room had no idea it happened. They started getting phone calls from customers and power plants saying voltages were low, but they discounted the information because it couldn't be corroborated on their end. By this time, their IT staff knew about the particular issues, but they hadn't communicated it to the operators, who had no clue their alarm system was down. With the loss of Harding Chamberlain, the remaining transmission about half an hour after the first fault, and the offline as well. First thing staff was troubleshooting the computer issues, but still had no idea the staff had meaningful the reliability of their state estimate issues were also behind on realizing the occurrence and consequences of these outages. First Energy operators were now getting phone call after phone call asking about the situation while being figuratively in the dark. Call transcripts from that day tell a scary story. The meter on the main transformer is bouncing around pretty good. I've got a relay trip up here, so I know something ain't right, said one operator at a nearby nuclear power plant. A little later, he called back. I'm still getting a lot of voltage spikes and swings on the generator. I don't know how much longer we're going to survive. A minute later, he calls again. It's not looking good. We ain't going to be here much longer, and you're going to have a bigger problem. An operator in the First Energy Control Room replied, nothing seems to be updating on the computer. I think we've got something seriously fixed. With two key transmission lines out of service, a major portion of the electricity powering the Cleveland area had to find a new path into the city. Some of it was pushed onto the less efficient 138 kilovolt system, but much of it was being carried by the Star South Canton line, which was now carrying more than its rated capacity. At 3:40, a short 10 minutes after losing Hannah Juniper, the Star South Canton line tripped offline when it too sagged into a tree in short circuit. It was actually the third time that day the line had tripped, but it was equipped with circuit breakers called reclosers that would energize the line automatically if the fault had cleared. But the third time was the charm, and the Star South Canton line tripped and locked out. Of course, First Energy didn't know about the first two trips because they didn't see an alarm, and they didn't know about this one either. They had started sending crews out to substations to get boots on the ground and try to get a handle on the situation, but at that point, it was too late. With Star South Canton offline, flows in the lower capacity 138 kilovolt lines in Cleveland increased significantly. It didn't take long before they too started tripping offline one after another. Over the next half hour, 16 138 kilovolt transmission lines faulted, all from sagging low enough to contact something below the line. At this point, voltages had dropped low enough that some of the load in northern Ohio had been disconnected, but not all of it. The last remaining 345 kV line into Cleveland from the south came from the Samus power plant. The sudden changes in current flow through the system now have this line operating at 120% of its rated capacity. Seeing such an abnormal and sudden rise in current, the relays on the Star Samus line assumed that a fault had occurred and tripped the last remaining major link to the Cleveland area offline at 4:05 p.m., only an hour after the first incident. After that, the rest of the system unraveled.
With no remaining connections to the Cleveland area from the south, bulk power coursing through the grid tried to find a new path into this urban center. First, overloads progressed northward into Michigan, tripping lines and further separating areas of the grid. Then the area was cut off to the east. With no way to reach Cleveland, Toledo, or Detroit from the southwest or north, a massive power surge flowed east into Pennsylvania, New York, and then Ontario in a counterclockwise path around Lake Erie, creating a major reversal of power flow in the grid. All along the way, relays meant to protect equipment from damage saw these unusual changes in power flows as faults and tripped transmission lines and generators offline. Relays are sophisticated instruments that monitor the grid for faults and trigger circuit breakers when one is detected. Most relaying systems are built with levels of redundancy so that lines will still be isolated during a fault, even if one or more relays malfunction. One type of redundancy is remote backup, where separate relays have overlapping zones of protection. If the closest relay to the fault, called Zone 1, doesn't trip, the next closest relay will see the fault in its Zone 2 and activate the breakers. Many relays have a Zone 3 that monitors even farther along the line. When you have a limited set of information, it can be pretty hard to know whether a piece of equipment is experiencing a fault and should be disconnected from the grid to avoid further damage, or just experiencing an unusual set of circumstances that protection engineers may not have anticipated. That's especially true when the fault is far away from where you're taking measurements. The vast majority of lines that went offline in the cascade were tripped by Zone 3 relays. That means the Zone 1 and 2 relays, for the most part, saw the changes in current and voltage on the lines and didn't trip because they didn't fall outside of what was considered normal. However, the Zone 3 relays, being less able to discriminate between faults and unusual but non-damaging conditions, shut them down. Once the dominoes started falling in the Ohio area, it took only about 3 minutes for a massive swath of transmission lines, generators, and transformers to trip offline. Everything happened so fast that operators had no opportunity to implement interventions that could have mitigated the cascade. Eventually, enough lines tripped that the outage area became an electrical island, separated from the rest of the eastern interconnection. But since generation wasn't balanced with demand, the frequency of power within the island was completely unstable, and the whole area quickly collapsed. In addition to all the transmission lines, at least 265 power plants with more than 508 generating units shut down. When it was all over, much of the northeastern United States and the Canadian province of Ontario were completely in the dark. Since there were very few actual faults during the cascade, re-energizing happened relatively quickly in most places. Large portions of the affected area had power back on before the end of the day. Only a few places in New York and Toronto took more than a day to have power restored, but still, the impacts were tremendous. More than 50 million people were affected. Water systems lost pressure, forcing boil water notices, cell service was interrupted, all the traffic lights were down. It's estimated that the blackout contributed to nearly 100 deaths. Three trees and a computer caused a major part of North America to completely grind to a halt. That's not an example of the complexity of the power grid. I don't know what is. If you ask anyone working in the power industry on August 15th whether the entire northeast U.S. and Canada would suffer a catastrophic loss of service the next day, he would have said no way. Who understood the fragility of the power grid, then there were even experts sounding alarms about the impacts of deregulation and the vulnerability of transmission networks. But this was not some big storm. It wasn't even a peak summer day. It was just a series of minor contingencies that all lined up just right to create a catastrophe. Today's power grid is quite different than it was in 2003. The bilateral report made 46 recommendations about how to improve operations and infrastructure to prevent a similar tragedy in the future, many of which have been implemented over the past nearly 20 years. But it doesn't mean there aren't challenges and fragilities in our power infrastructure today. Current trends include more extreme weather, changes in the energy portfolio as we move toward variable sources of generation like wind and solar, growing electrical demands, and increasing communications between loads, generators, and grid controllers. Just a year ago, Texas saw a major outage related to extreme weather and the strong nexus between natural gas and electricity. I have a video on that event if you want to take a look after this. I think the 2003 blackout highlights the intricacy and interconnectedness of this critical resource we depend on. And I hope it helps you appreciate the engineering behind it. Thank you for watching, and let me know what you think. This is the Crossness pumping station in London. Its ornate architecture and elaborate ironwork belie its original, somewhat disgusting purpose: to lift raw sewage from London's southern outfall, the lowest point in one of London's biggest sewers, up to the ground surface where it could be discharged directly into the Thames River. Of course, we don't typically release raw sewage into waterways anymore, and Crossness has long been decommissioned after newer treatment works were built in the 1950s. It's now in the process of being restored as a museum you can visit to learn more about the fascinating combined history of human waste and Victorian engineering. But even though we have more sophisticated ways to treat wastewater before discharging it into streams and rivers, there's one thing that hasn't changed. We still use gravity as the primary way of getting waste to flow away from homes and businesses within the sewers below ground. And eventually we need a way to bring that sewage back up to the surface of the earth. But that's not as easy as it sounds. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about sewage lift stations. This video is sponsored by HelloFresh, America's #1 meal kit. More on them later. I have a video all about the engineering of sewers, and today we're following that wastewater one more step on its smelly journey through a typical city. You can go check out that video after this if you want to learn more, but I'll summarize it quickly here. Most sewers flow by gravity from each home or business toward a wastewater treatment plant. They're installed as pipes, but sewers usually flow only partly full, like smelly water slides or underground creeks and rivers. This is convenient because we don't have to pay a monthly gravity bill, and it almost never gets knocked out during a thunderstorm. It's a free and consistent force that compels sewage downward. But because Earth's gravity only pulls in one direction, sewers must always slope, meaning they often end up well below the ground surface, especially toward their downstream ends. And that can be problematic. Here's why. Sewers are almost always installed in open excavations, also known as trenches. This might seem obvious, but the deeper a trench must be dug, the more difficult, dangerous, disruptive, and ultimately expensive construction becomes. In some cases, it just stops being feasible to chase the slope of a sewer farther and farther below the ground surface. A good alternative is to install a pumping station that can lift raw sewage from its depth back closer to the surface. Lift stations can be small installations designed to handle a few apartment complexes or massive capital projects that pump significant portions of the city's total wastewater flow. A typical lift station consists of a concrete chamber called a wet well. Sewage flows into the wet well by gravity, filling it over time. Once the sewage reaches a prescribed depth, a pump turns on, pushing the wastewater into a specialized sewer pipe called a force main. You always want to keep the liquid moving swiftly in pipes to avoid the solids settling out, so this intermittent operation makes sure that there are no slow trickles during off-peak hours. The sewage travels under pressure within the force main to an uphill manhole where it can continue its journey downward via gravity once again. Another important location for lift stations is at the end of the line. Once wastewater reaches its final destination, there are no magical underground sewage outlets. Septic systems get rid of wastewater through leach fields that infiltrate the subsurface, but they're designed for individual buildings and aren't feasible on a city scale. That would require enormous areas of land to get so much liquid to soak into the soil, not to mention the potential for contamination of the groundwater. Ignoring for now the fact that we need to clean it up first, we still need somewhere for our sewage to go. In most cases, that's a creek, river, or the ocean, meaning we need to lift the sewage up to the surface of the earth one last time. Rather than build wastewater treatment plants as underground layers like Stinky superheroes mainly pump clean water. It's much easier just to lift the raw sewage up to the surface. Pretty gross stuff, sewage, pump, and that comes with some challenges. We often think of sewage as its grossest constituent, human excrement, poop. But sewage is a slurry of liquids and solids from a wide variety of sources. Lots of stuff ends up in our wastewater stream, including soil, soap, hair, food, wipes, grease, and trash. These things may make it down the toilet or sink drain and through the plumbing in your house, but in the sewer system, they can conglomerate into large balls of grease, rags, and other debris, sometimes called pigtails or fatbergs by wastewater professionals. In addition, with many cities putting efforts into conserving water, the concentration of solids in wastewater is trending upward. Conventional pumps handle liquids just fine, but adding solids in the stream increases the challenge of lifting raw sewage. Let me show you what I mean with this demonstration I set up in my garage. This is a small submersible pump designed for moving water out of basements or pools. It's nothing fancy, just an electric motor with a small impeller inside a molded plastic case. I took off the screen so we can really see how much it can handle. The submersible pump moves clear water just fine. Toilet paper is no issue even for the small pump. It can break apart the paper with no problem. It can even manage small suspended solids like these plastic balls. The particles stay in solution, forming a slurry, similar to raw sewage. However, larger solids in the stream can easily clog the pump. Anything bigger than the spaces in the impeller just won't make it through, and clogging really becomes a problem with stringy debris. These are quote-unquote flushable wipes. They may make it past the toilet, but you can easily see why these type of wipes are a problem in a wastewater stream. I really don't feel like pouring a bunch of grease in my demonstration here, but I'm sure you can imagine how congealed fats and oils would only exacerbate the problem of clogging this pump. It's clear that appropriately sized centrifugal pumps can handle certain types and sizes of suspended solids just fine. Sewage pumps are designed for the extra wear and tear. The impellers have fewer vanes to avoid snags, and the openings are larger so that solids can freely move through them. Different manufacturers have proprietary designs to minimize obstructions to the extent possible, but no sewage pump is clog-proof. Especially with today's concentrated wastewater full of wipes that have been marketed as flushable, clogs at lift stations can be a daily occurrence. Removing a pump, clearing it of debris, and replacing it is a dirty and expensive job, especially if you have to do it frequently. Most lift stations have an alarm when the level gets too high, but if a clog doesn't get cleared fast enough, raw sewage can back up into houses and businesses or overflow the wet well, potentially exposing humans and wildlife to dangerous biohazards. A seemingly obvious solution to the problem of clogging is to use a screen in the lift station wetlands to prevent trash from reaching the pump. But screens have a limitation; they can clog up too. By adding a screen, you've traded pump maintenance for another kind of maintenance, removing and hauling away debris. Smaller lift stations with bar or basket screens can get away with maybe a once-a-week visit from a crew to clean them. Larger pump stations often feature automatic systems that can remove solids from the screen into a dumpster that can be hauled to a landfill every so often. Sometimes using a screen is an effective way to protect against clogging, but it's not always convenient, especially because it creates a separate waste stream to manage. For example, if a lift station is remote where it's inconvenient to send crews for service and maintenance, you might prefer that all the solids remain in the wastewater stream. After all, treatment plants are specifically designed to clean wastewater. They have better equipment and consistent staffing, so it often just makes sense to focus the investments and time and effort at the plant rather than individual lift stations along the way. In these cases, there's another option for minimizing pump clogs: grinding the solids into smaller pieces. There's a nice equivalent to a lift station grinder that can be found under the sinks of many North American homes: the garbage disposal. This common household appliance saves you the trouble and smell of putting food scraps into the wastebasket. It works like a centrifugal pump with a spinning impeller, but it also features a grinding ring consisting of sharp blades and small openings. As the impeller spins the solids, they scrape against the grinding ring, shearing into smaller pieces that can travel through the waste plug. My garbage disposal can handle all of the solids I tested with the submersible pump with no issues with clogging. The wipes gave it a little trouble, but it was still able to chew them up. Some lift stations feature grinding pumps that are remarkably similar to under-sink garbage disposal. Others use standalone grinders that simply chew up the solids before they reach the pumps. Grinders are often required at medical facilities and prisons where fibrous solids are more likely to find their way into the wastewater stream. Large grinders are also used where storm drains and sewers are combined because those systems see heavier debris loads from rainwater runoff. A grinder is another expensive piece of equipment to purchase and maintain at a lift station, but it can offer better reliability, fewer clogs, and thus decreased maintenance costs. Of course, clogging is not the only practical challenge of operating a sewage lift station. When you depend on electromechanical equipment to provide an essential service, you always have to plan for things to go wrong. Lift stations usually feature multiple pumps so they can continue operating if one fails. They often have backup generators so that sewage can continue to flow even if grid power is lost. Another issue with lift stations is air bubbles getting into force mains and constricting the flow. Automatic air release valves can purge force mains of these bubbles, but venting sewer gas into populated areas isn't usually a popular prospect. Although our urban lives depend on sewers to carry waste away before it can endanger public health, reminders that they exist are usually unwelcome. Hopefully this video breaks that convention to help you understand a little about the challenges and solutions of managing wastewater to keep your city clean and safe. It's time for everyone's favorite segment of me trying to cook while my wife tries to capture that on video. We're not expert chefs or foodies, but cooking is one of our favorite ways to spend time together. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night, or date afternoon in this case. Our little helper likes to open the box, and he tried to quality test the ingredients early this time, but I promise they're usually washed before going into anyone's mouth. Then he's out for nap time so we can goof around in the kitchen and cook lunch.
Sound effects, please.
HelloFresh even has options for 20-minute meals, easy cleanup, and low prep so you can take advantage of life's little windows for eating well. They also have options for family-friendly meals, pescatarian, vegetarian, and more, so it's a really nice way to jumpstart a change in your diet if that's one of your goals for the new year. The pre-portioned ingredients means there's less prep and less food waste, and the packaging is already recycled content, and most of it's recyclable as well.
That looks lovely.
Go try it yourself at HelloFresh.com. If you use code PRACTICAL16, you'll get up to 16 free meals plus 3 surprise gifts. Let us know in the comments who rolled the better burrito. That's HelloFresh.com and use my code PRACTICAL16. Thanks, HelloFresh, and thank you for watching. Let me know what you think. When we bought our house several years ago, we fell in love with every part of it except one, the foundation. At 75 years old, we knew these old piers were just about finished holding this old house up. This year, we finally bit the bullet to have them replaced. Any homeowner who's had foundation work done can commiserate with us on the cost and disruption of a project like this. But homes aren't the only structures with foundations. It is both a gravitational necessity and a source of job stability to structural and geotechnical engineers that all construction, great and small, sits upon the ground. And the ways in which we accomplish such a seemingly unexceptional feat are full of fascinating and unexpected details. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about foundations. This video is sponsored by CuriosityStream and Nebula. More on them later. There's really just one rule for structural and geotechnical engineers designing foundations. When you put something on the ground, it should not move. That seems like a pretty straightforward directive. You can put a lot of stuff on the ground and have it stay there. For example, several years ago, I optimistically stacked these pavers behind my shed with the false hope that I would use them in a landscaping project someday, but their most likely future is to sit here in this shady purgatory for all of eternity. Unfortunately, buildings and other structures are a little different. Mainly, they're large enough that one part could move relative to the other parts, a phenomenon we call differential movement. When you move one piece of anything relative to the rest of it, you introduce stress. And if the stress is greater than the inherent strength of the thing, that thing will pull itself apart. It happens all the time, all around the world, including right here in my own house. When one of these piers settles or heaves more than the others, all the stuff it supports tries to move too. But door frames, drywall, and ceramic tile work much better and last much longer when the surrounding structure stays put. There are many kinds of foundations used for the various structures in our built environment. But before we dive into how they work, I think it will be helpful to first talk about what they're up against, or actually down against. Of course, buildings are heavy, and one of the most important jobs of a foundation is to evenly distribute that weight into the subsurface as downward pressure. Soil isn't infinitely strong against vertical loads. It can fail just like any other component of a structural system. When the forces are high enough to shear through soil particles, we call it a bearing failure. The soil directly below the load is forced downward, pushing the rest of the soil to either side, eventually bulging up around the edges. Even if the subsurface doesn't full-on shear, it can still settle. This happens when the particles are compressed more closely together, and it usually takes place over a longer period of time. I have a video all about settlement that you can check out after this. So, job number one of a foundation is to distribute the downward force of a structure over a large enough area to reduce the bearing pressure and avoid shear failures or excessive settlement. Structural loads don't just come from gravity. Wind can exert tremendous and rapidly fluctuating pressure on a large structure, pushing it horizontally and even creating uplift like the wing of an airplane. Earthquakes also create loads on structures, shifting and shaking them with very little warning. Just like the normal weight of a structure, these loads must also be resisted by a foundation to prevent it from lifting or sliding along the ground. That's job number two. Speaking of the ground, it's not the most hospitable place for many building materials. It has bugs like termites that can eat away at wooden members over time, reducing their strength. It also has moisture that can lead to mold and rot. My house was built in the 1940s on top of cedar piers. This is a wood species that is naturally resistant to bugs and fungi, but not completely immune to them, as you can see. So, job number three of a foundation is to resist the effects of long-term degradation and decay that come from our tiny biological neighbors. Another problem with the ground is that soil isn't really as static as we think. Freezing isn't usually a problem for me in central Texas, but many places in the world see temperatures that rise and fall below the freezing point of water tens or hundreds of times per year. We all know water expands when it freezes, and it can do so with prodigious force. When that happens to subsurface water below a structure, it can behave like a jack to lift it up. Over time, these cycles of freeze and thaw can slowly shift or raise parts of a structure more than others, creating issues. Similarly, some kinds of soil expand when exposed to moisture. I also have a video on this phenomenon, so you have two videos to watch after this one. Expansive clay soil can create the same type of damage as cycles of freeze and thaw by subtly moving a structure in small amounts with each cycle of wet and dry. So job number four of a foundation is to reach a deep enough layer that can't freeze or that doesn't experience major fluctuations in moisture content to avoid these problems that come with water in the subgrade below the structure. Job number five isn't necessarily applicable to most buildings, but there are many types of structures, like bridges and retaining walls, that are regularly subject to flowing water. Over time, or sometimes over the course of a single flood, the water can create erosion, undermining the structure. Many foundations are specifically designed to combat erosion, either with hard armoring or by simply being installed so deep into the earth that they can't be undermined by quickly flowing water. Job number six really applies to all of engineering. Foundations have to be cost effective. Could the contractor who built my house in the 1940s have driven twice as many piers, each one to 3 times the depth? Of course it can be done, but with some minor maintenance and repairs, this one lasted 75 years before needing to be replaced. With the median length of home ownership somewhere between 5 and 15 years, few people would be willing to pay more for a house with 500 years of remaining life in the foundation than they would for one with 30. I could have paid this contractor to build me a foundation that will last hundreds of years, but I didn't. Engineering is a job of balancing constraints, and many of the decisions in foundation engineering come down to the question of how can we achieve all the first 5 jobs I mentioned without overdoing it and wasting a bunch of money in the process. Let's look at a few ways. Foundations are generally divided into two classes, deep and shallow. Most buildings with only a few stories, including nearly all homes, are built on shallow foundations. That means they transfer the structure's weight to the surface of the earth, or just below it. Maybe the most basic of these is how my house was originally built. They cut down cedar trees, hammered those logs into the ground as piles, laid wooden beams across the top of those piers, and then built the rest of the house atop the beams. Pier and beam foundations are pretty common, at least in my neck of the woods, and they have an added benefit of creating a crawl space below the structure, in which utilities like plumbing, drains, and electric lines can be installed and maintained. However, all these individual, unconnected points of contact with the earth leave quite a bit of room for differential movement. Another basic type of shallow foundation is the strip footing, which generally consists of a ribbon or strip of concrete upon which walls can sit. In some cases, the floor is isolated from the walls and sits directly on a concrete slab atop the subgrade. But strip footings can also support floor joists, making room for a crawl space below. For sites with strong soils, this is a great option because it's simple and cheap. But if the subgrade soils are poor, strip footings can still allow differential movement because all the walls aren't rigidly connected together. In that case, it makes sense to use a raft foundation, a completely solid concrete slab that extends across the entire structure. Raft foundations are typically concrete slabs placed directly on the ground, usually with some thickened areas to provide extra rigidity. They distribute the loads across a larger area, reducing the pressure on the subgrade, and they can accommodate some movement of the ground without transferring the movement into a structure, essentially riding the waves of the earth like a raft on the ocean, hence the name. However, they don't have a crawl space, which makes plumbing repairs much more challenging. One issue with all shallow foundations is that you still need to install them below the frost line. That is the maximum depth to which water in the soil might freeze during the harshest part of the winter, in order to avoid frost heaving. In some parts of the contiguous United States, the frost line can be upwards of 8 feet or nearly 2.5 meters. If you're going to dig that deep to install a foundation anyway, you might as well just add an extra floor to your structure below the ground. That's usually called a basement, and it can be considered a building's foundation, although the walls are usually constructed on a raft or strip footings as described above. As a structure's size increases, so do the loads it imposes on the ground, and eventually it becomes infeasible to rely only on soils near the surface of the earth. Tall buildings, elevated roadways, bridges, and coastal structures often rely on deep foundations for support. This is especially true when the soils at the surface are not as firm as the layers farther below the ground. Deep foundations almost always rely on piles, which are vertical structural elements that are driven or drilled into the earth, often down to a stronger layer of soil or bedrock. And there are way more types than I could ever cover in a single video. Piles not only transfer loads at the bottom, called in-bearing, but they can also be supported along their length through a phenomenon called skin friction. This makes it possible for a foundation to resist much more significant loads, whether downward, upward, or horizontal, within a given footprint of a structure. One of the benefits of driven piles is that you install them in somewhat the same way they'll be loaded in their final configuration. There's some efficiency there because you can just stop pushing the pile into the ground once it's able to resist the design loads. There is a problem with this, though. Let me show you what I mean. This hydraulic press has more than enough power to push this steel rod into the ground. And at first, it does just that. But eventually, it reaches a point where the weight of the press is less than the bearing capacity of the pile, and it just lifts itself up. Easy, you might think. Just add more weight. But consider that these piles might be designed to support the weight of an entire structure. It's not feasible to bring in or build some massive weight just to react against to drive a pile into the ground. Instead, we usually use hammers, which can deliver significantly more force to drive a pile with only a relatively small weight. The problem with hammered piles is that the dynamic loading they undergo during installation is different from the static loading they see once in service. In other words, buildings don't usually hammer on their foundations. For example, if a pile can withstand the force of a 5-ton weight dropped from 16 feet or 5 meters without moving, what's the equivalent static load it can withstand? That turns out to be a pretty complicated question. And even though there are published equivalencies between static and dynamic loads, their accuracy can vary widely depending on soil conditions. That's especially true for long piles where the pressure wave generated by a hammer might not even travel fast enough to load the entire member at the same moment in time. Static tests are more reliable, but also more expensive because because you either have to bring in a ton or thousands of tons of weight to put on top, or you have to build additional piles with a beam across them to give the test rig something to react against. One interesting solution to this problem is called statnamic testing of piles. In this method, a mass is accelerated upward using explosives, creating an equal and opposite force on the pile to be tested. It's kind of like a reverse hammer, except unlike a hammer where the force on the pile lasts only for a few milliseconds, the duration of loading in a statnamic test is often upwards of 100 or 200 milliseconds. That makes it much more similar to a static force on the pile, without having to bring in tons and tons of weight or build expensive reaction piers just to conduct a test. I'm only scratching the surface or subsurface of a topic that fills hundreds of engineering textbooks and the careers of thousands of contractors and engineers. If all the earth was solid rock, life would be a lot simpler, but maybe a lot less interesting too. If there are topics in foundations you'd like to learn more about, add a comment or send me an email and I'll try to address it in a future video. But I hope this one gives you some appreciation of those innocuous bits of structural and geotechnical engineering below our feet. Hey, thanks for sticking around to the end of this video. You know how this works because you probably watch a lot of videos about science and engineering to the end just like I do. You probably also don't enjoy watching ads like this one, which is great because Nebula doesn't have it. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Wendover Productions, and a bunch of others, including me. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. My videos go live there the day before they publish here with no ads or sponsorships. And we're super excited to continue our partnership with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and all those monthly subscriptions can be tough to keep track of. That's why this bundle is such an awesome deal. CuriosityStream's taking 26% off an annual plan. That makes it only $15 for an entire year of access to thousands of thought-provoking documentaries on CuriosityStream and everything on Nebula as well. I love watching the European Inventor Awards that showcase the coolest new inventions each year on CuriosityStream. Or watch the Nebula exclusive series Logistics of D-Day by my friend Brian at Real Engineering. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a great video. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. This video is sponsored by Warby Parker. More on them later. In February 2017, the world watched as the main spillway on one of the largest dams in the world suffered a catastrophic failure, prompting a series of events that led to the evacuation of nearly 300,000 people downstream and hundreds of millions of dollars damaging to critical water. I made a video about the failure of the Orville Dam spillway in California after the about why the structure failed, summarizing their 600-page report. There wasn't enough time in that first video to cover the spillways after the event was over. I got flooded with requests to cover the repairs, and I love a good construction conversation. How do you rebuild the biggest spillway in the world after a catastrophic failure, knowing that the next flood season is right around the corner? The answer might surprise you. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about rebuilding the Orville Dam spillways. Oroville Dam in Northern California is the tallest dam in the United States. It was built in the 1960s, creating one of California's keystone reservoirs to smooth out the tremendous variability in rain and snowfall from their climate of hot, dry summers and flood-prone winters. The dam itself is a massive earthen embankment. To the northwest is the main spillway, also known as the Flood Control Outlet, or FCO spillway. At the top are radial gates to control control the flow. They release water into the enormous concrete chute before it passes through gigantic dentings that disperse the flow as it crashes into the Feather River below. It's nearly impossible to convey the scale of this structure, which could fit 8 American football fields with room to spare, or more than 150 tennis courts. Beyond is the emergency spillway, a concrete weir set a foot above the maximum operating level to provide a backup path for water to leave the reservoir during extreme flood events. If you want more detail about the failure, I encourage you to go back and watch that video after this. I do want to summarize the damages here because you can't really grasp the magnitude of the reconstruction project without an appreciation for how profoundly ruined this event left the spillways of Oroville Dam. Just about all but the upper section of the main spillway chute was wholly destroyed. The flows that broke free from the chute scoured the hillside around and below the structure, washing away concrete and eroding an enormous chasm as deep as 100 feet or 30 meters in some places. At the emergency spillway, overflows had similarly scoured the hillside, creating erosional headcuts that traveled upstream, threatening the safety and stability of the structure, in total, more than 1 million cubic meters of soil and rock were stripped away, much of which was deposited into the Feather River below the dam. Both spillways were rendered totally incapable of safely discharging future flood flows from Lake Oroville. Even before the event was over, the California Department of Water Resources, or DWR, was planning for the next flood season, which was right around the corner. Having the tallest dam in the United States sitting crippled and unable to pass flood flows safely, with the rainy season only 6 months away, just wasn't an option. As soon as the extent of the situation was revealed, DWR began assembling a team and plotting the course for recovery. Rather than try to handle all the work internally, DWR contracted with a wide range of consultants from engineering firms across the country and partnered with federal agencies, namely the Corps of Engineers and Bureau of Reclamation, who both have significant knowledge and experience with major water resources projects. In March, less than a month after the incident started, and well before it was close to over, DWR held an all-day workshop with the design and management teams to collaborate on alternatives for restoring the dam spillway, focusing on the main spillway. They were facing some significant challenges. With the next flood season quickly approaching, they had limited time for design, regulatory reviews, and construction. Steps that would typically take months or years needed to be compressed into weeks. On top of that, they were still in the midst of the spillway failure, without a complete understanding of what had gone wrong, making it difficult to propose solutions that would avoid a similar catastrophe in the future. Although they had a laundry list of ideas, most fell into 3 categories, nicknamed by the design team as use the hole, bridge the hole, or fill the hole. Use the hole alternatives involve taking advantage of the scoured hole and channels carved by the uncontrolled flows from the spillway. If they could protect the soil and rock from further erosion, these new landscape features could serve as the new path for water exiting the reservoir, eliminating the need for a replacement to the massive and expensive concrete chute. The engineering team built a scaled model of the spillway at Utah State University as a design tool for providing hydraulic information. They constructed an alternative with a modified scour hole to see how it would perform when subjected to significant releases from the spillway. Sadly, the model showed enormous standing waves under peak flows, so this alternative was discarded as infeasible. Bridge the hole alternatives involve constructing the spillway chute above grade. In other words, instead of placing the structure on the damaged soil and rock foundation, they could span the eroded valleys using aqueduct-style bridges. However, given the complexity of engineering such a unique spillway, the design team also ruled this option out. The time it would take for structural design just wouldn't leave enough time for construction. Fill the hole alternatives centered around replacing the eroded foundation material and returning the main spillway to its original configuration. There were a lot of advantages to this approach. It had the least amount of risk and the fewest unknowns about hydraulic performance, which had been proven through more than 50 years of service. This option also provided a place to reuse the scoured rock that had washed into the Feather River. Next, it had the lowest environmental impacts because no new areas of the site would be permanently impacted. And finally, it was straightforward construction, not anything too complicated, giving the design team confidence that contractors could accomplish the work within the available timeframe. Once a solution had been selected, the design team started developing the plans and specifications for construction. Over 100 engineers, geologists, and other professionals were involved in designing repairs to the two spillways, many working 12-plus hour days, 6 to 7 days a week, on site in portable trailers near the emergency spillway. Because many of the problems with the original spillways resulted from the poor conditions of underlying soil and rock, the design phase included an extensive geotechnical investigation of the site. At its peak, there were 10 drill rigs taking borings of the foundation materials. The samples were tested in laboratories to support the engineering of the spillway replacements. The design team elected to fill the scoured holes with roller compacted concrete, a unique blend of the same essential ingredients of conventional concrete, but with a lot less water. Instead of flowing into forms, roller compacted concrete, or RCC, is placed using paving equipment and compacted into place with vibratory rollers. The benefit of RCC was that it could be made on site using materials mined near the dam and those recovered from the Feather River. It also cures quickly, reaching its full strength faster and with less heat buildup, allowing crews to place massive amounts of it on an aggressive schedule without worrying about it cracking apart from thermal effects. RCC is really the hero of this entire project. The design engineers worked hard to develop a mix that was as inexpensive as possible, using the rock and aggregates available on the site, while still being strong enough to carry the weight of the new spillway. In the interest of time, California DWR brought on a contractor early to start building access roads and staging areas for the main construction project. They also began stabilizing the steep slopes created by the erosion to make the site safer for the construction crews that would follow. The main construction project was bid at the end of March with plans only 30% complete. This allowed the contractors to get started early to mobilize the enormous quantity of equipment, materials, and workers required for this massive undertaking. Having a contractor on the project early also allowed the design team to collaborate with the construction team, making it easier to assess the impact of design changes on the project's costs and schedule. Because the original spillway failed catastrophically, DWR knew that the entire main spillway would need to be rebuilt to modern standards. However, they didn't have the time to do the whole thing before the upcoming flood season. DWR had developed an operations plan for Lake Oroville to keep the reservoir low and minimize the chance of spillway flows while the facilities were out of service for construction. But they couldn't just empty the lake entirely. They still had to balance the purposes of the reservoir, including flood protection, hydropower generation, environmental flows, and the rights of water users downstream. The winter flood season was approaching rapidly, and there was still a possibility of a flood filling the reservoir and requiring releases. DWR needed a spillway that could function before November 2017, a little more than 6 months from when the contractor was hired, even if it couldn't function at its total original capacity. In collaboration with the contractor, the design team decided to break up the repair project into 2 phases. Phase 1 would rush to get an operational spillway in place before the 2017-2018 winter flood season. The remaining work to complete the spillway would be finished ahead of the following flood season at the end of 2018. In addition to the repairs at the main spillway, engineers also designed remediations to the emergency spillway, including a buttress to the existing concrete weir, an RCC apron to protect the vulnerable hillside soils, and a cutoff wall to keep erosion from progressing upstream. To speed up regulatory approval, which can often take months under normal conditions, the California Division of Safety of Dams and the Federal Energy Regulatory Commission both dedicated full-time staff to review designs as they were produced, working in the same trailers as the engineers. The project also required an independent board of consultants to review designs and provide feedback to the teams. This group of experts met regularly throughout design and construction, and their memos are available online for anyone to peruse. Phase 1 of construction began as the damaged spillway continued to pass water to lower the reservoir throughout the month of May. The contractor started blasting and excavating the slopes around the site to stabilize them and provide access to more crews and equipment. At the same time, an army of excavators began to remove the soil and rock that was scoured from the hillside and deposited into the Feather River. The spillway gates were finally closed for the season at the end of May, allowing equipment to mobilize to all areas of the site. They quickly began demolition of the remaining concrete spillway. Blasting also continued to stabilize the slopes by reducing their steepness in preparation for RCC placement and break up the existing concrete to be hauled away or reused as aggregate. By June, all the old concrete had been removed, and crews were working to clean the foundation materials of loose rock and soil. The contractor worked to ensure that the foundation was perfectly clean of loose soil and dust that could reduce the strength of the bond between concrete and rock. In July and August, crews made progress on the upper and lower sections of the spillway that hadn't been significantly undermined. Because they didn't have to fill in a gigantic scour hole in this area, crews could use conventional concrete to level and smooth the foundation, ensuring that the new structural spillway slab would be a consistent thickness across its entire width and length. Of course, I have to point out that the chute was not simply being replaced in kind. Deficiencies in the original design were a significant part of why the spillway failed in the first place. The new design of the structural concrete included an increase in the thickness of the slab, more steel reinforcement with an epoxy coating to protect against corrosion, flexible water stops at the joints in the concrete to prevent water from flowing through the gaps, steel anchors drilled deep into the bedrock to hold the slabs tightly against their foundation, and an extensive drainage system. These drains are intended to relieve water pressure from underneath the structure and filter any water seeping below the slab so it can't wash away soil and undermine the structure. As the new reinforced concrete slabs and training walls were going up on the lower section of the chute, RCC was being placed in lifts into the scour hole at the center of the chute. This central scour hole was the most time-sensitive part of the project because there was just so much volume to replace. Instead of building the scour hole and building the new spillway slabs and walls on top during Phase 1, the designers elected to use the RCC as a temporary stand-in for the central portion of the chute during the upcoming flood season. The designs called for the RCC to be placed up to the level of the spillway chute with formed walls, not quite tall enough for the total original capacity, but enough to manage a major flood if one were to occur. By September, crews had truly hit their stride, producing and placing colossal amounts of concrete each day, slowly reconnecting the upper and lower sections of the chute across the chasm of eroded rock. Reinforced concrete slabs and walls continued to go up on both the upper and lower sections of the chute. With only a month before the critical deadline of November 1st, the contractor worked around the clock to produce and place both conventional and roller compacted concrete across the project site. By the end of the day on November 1st, Phase 1 of the massive reconstruction was completed on schedule and without a single injury. The spillway was ready to handle releases for the winter flood season if needed. Luckily, it wasn't, and the work didn't stop at Oroville Dam. Phase 2 began immediately with the contractor starting to work on parts of the project that wouldn't compromise the dam's ability to release flows during the flood season. That mainly involved a focus on the emergency spillway. Crews first rebuilt a part of the original concrete weir, making it stronger and more capable of withstanding hydraulic forces. They also installed a secant pile cutoff wall in the hillside well below the spillway. A secant pile wall involves drilling overlapping concrete piers deep into the bedrock. The purpose of the cutoff wall was to prevent erosion from traveling upstream and threatening the spillway structure. A concrete cap was added to the secant piles to tie them all together at the surface. Finally, roller compacted concrete was placed between the secant wall and the spillway to serve as a splash pad, protecting the vulnerable hillside from erosion if the emergency spillway were ever to be used in the future. Once the flood season was over in May, DWR gave the contractor the go-ahead to start work back on the main spillway. There were two main parts of the project remaining. First, they needed to completely remove and replace the uppermost section of the chute and training walls. Except for the dentates at the downstream end, this was the only section of the original chute remaining after Phase 1. At the RCC section of the spillway, crews first removed the temporary training walls that were installed to allow the spillway to function at reduced capacity during the prior flood season. They never even got to see a single drop of water, but at least the material was reused in batches of concrete for the final structure. Next, the contractor milled the top layer of RCC to make room for the structural concrete slab. They trenched drains across the RCC to match the rest of the spillway, and finally, they built the structural concrete slabs and walls to complete the structure. All this work continued through the summer and fall of 2018. On November 1st, construction hit a key milestone of having all the main spillway concrete placed ahead of the winter flood season. Although cleanup and backfill work would continue for the next several months, The spillway was substantially complete and ready to handle releases if it was needed. It's a good thing, too, because a few months later, it was. Crews continued cleaning up the site, working on the emergency spillway, and demobilizing equipment throughout the 2018-2019 flood season. In April 2019, heavy rain and snowfall filled Lake Oroville into the flood control zone, necessitating the opening of the spillway gates. For the first time since reconstruction, barely 2 years after this whole mess got started, the new spillway was tested, and it performed beautifully. I'm sure it was a tremendous relief and true joy for all the engineers, project managers, construction workers, and the public to see that one of the most important reservoirs in the state was back in service. As of this writing, Oroville is just coming up from historically low levels resulting from a multi-year drought in California. It just goes to show the importance of engineering major water reservoirs like Oroville to smooth out the tremendous variability in rain and snowfall. It's easy to celebrate such an incredible engineering achievement of designing and constructing one of the largest spillway repair projects in the world without remembering what necessitated the project in the first place. The systemic failure of the dam owner and its regulators to recognize and address the structure's inherent flaws came at a tremendous cost, both to those whose lives were put at risk and evacuated from their homes, and to the taxpayers and ratepayers who will ultimately foot the more than $1 billion spent on these repairs. Dam owners and regulators across the world have hopefully learned a hard lesson from Oroville, thanks in large part to those who shared their knowledge and experience of the event. I'd like to give them a shout out here because this video wouldn't have been possible without them. California DWR's commitment to transparency means we have tons of footage from the event and reconstruction, much more than I was able to share here. Engineers and project managers involved in the emergency and reconstruction shared their experiences in professional journals. Finally, my fellow YouTuber Juan Brown provided detailed and award-winning coverage of the project as a citizen journalist on his channel, Blanco Leary, including regular overflights of Oroville Dam in his mighty Luskin. Go check out his playlist after this if you want to learn more. As I always say, this video is only a summary, and it doesn't include nearly the level of detail that Juan put into his reporting. Finally, I want to say thanks to the sponsor of today's video, without whom I could not see faraway objects clearly, nor could I maintain this air of confidence and charisma. Warby Parker is all things vision care, including stores that offer eye exams, but I've been using them for my glasses for many years now. Let me show you how it works. You choose 5 pairs of glasses from their website to try at home for free for 5 days. I love this option because there's less pressure to make a decision than at an optometrist's office, and I can get feedback from my wife. I always pick at least one pair I know I'll like.
Those ones look the best on you.
And one pair that isn't my normal style. Once you've tried them on, pack them up and send them back with the prepaid label. There's no obligation to buy, but glasses start at only $95 with prescription lenses, and you can use FSA or HSA dollars too. It's such a fresh take on purchasing eyeglasses, and I really enjoy the process. If you're a fellow glasses wearer, try 5 pairs of glasses at home completely free at warbyparker.com/practicalengineering.
Can I try those on?
Yeah. Supporting our sponsors helps support the channel. That's warbyparker.com/practicalengineering. Thanks, Warby Parker, and thank you for watching. Let me know what you think. In March of 2021, a long-running construction project on a New Jersey highway interchange ground to a halt when one of the retaining walls along the roadway collapsed. This project in Camden County, called the Direct Connection, was already 4 years behind schedule, and this failure set it back even further. As of this writing, the cause of the collapse is still under investigation, but the event brought into the spotlight a seemingly innocuous part of the constructed environment. I love innocuous parts of the constructed environment, and I promise by the end of this video, you'll pay attention to infrastructure that you've never even noticed before. Why do we build walls to hold back soil? What are the different ways to do it, and why do they sometimes fall down? I'm Grady, and this is Practical Engineering. In today's episode, we're talking about retaining walls. This video is sponsored by HelloFresh, America's his #1 meal kit. More on that later. The natural landscape is never ideally suited to construction as it stands. The earth is just too uneven. Before things get built, we almost always have to raise or lower areas of the ground first. We flatten building sites, we smooth paths for roads and railways, and we build ramps up to bridges and grade-separated interchanges. You might notice that these cuts and fills usually connect to the existing ground on a slope. Loose soil won't stand on its own vertically. That's just the nature of granular materials. The stability of a slope can vary significantly depending on the type of soil and the loading it needs to withstand. You can get many types of earth to hold a vertical slope temporarily, and it's done all the time during construction. But over time, the internal stresses will cause them to slump and settle into a more stable configuration. For long-term stability, engineers rarely trust anything steeper than 25 degrees. That means anytime you want to raise or lower the earth, you need a slope that is twice as wide as it is tall, which can be a problem. Don't tell him I said this, but slopes are kind of a waste of space. Depending on the steepness, it's either inconvenient or entirely impossible to use sloped areas for building things, walking, driving, or even as open spaces like parks. In dense urban areas, real estate comes at a premium, so it doesn't make sense to waste valuable land on slopes. Where space is limited, it often makes sense to avoid this disadvantage by using a retaining wall to support soil vertically. When you see a retaining wall in the wild, the job of holding back soil looks effortless. But that's usually only true because much of the wall structure is hidden from view. A retaining wall is essentially a dam, except instead of water, it holds back earth. Soil doesn't flow as easily as water, but it is twice as heavy. The force exerted on a retaining wall from that soil, called the lateral earth pressure, can be enormous. But that's just from the weight of the soil itself. Include the fact that we often apply additional forces from buildings, vehicles, or other structures on top of the backfill behind the wall. We call these surcharge loads, and they can increase the forces on a retaining wall even further. Finally, water can flow through or even freeze in the soil behind a retaining wall, applying even more pressure to its face. Estimating all these loads and designing a wall to withstand them can be a real challenge for a civil engineer. Unlike most structures where loads are vertical from gravity, most forces on a retaining wall are horizontal. There are a lot of different types of walls that have been developed to withstand these staggering sideways forces. Let's walk through a few different designs using this demonstration I built in my garage. These dowels act like soil particles, so we can easily see how different types of retaining walls are able to withstand such tremendous stress and what happens when you can't. The most basic retaining walls rely on gravity for their stability, often employing a footing along the base. A footing is a horizontal member that serves as a base to distribute the forces of the wall into the ground. Your first inclination might be to extend the footing on the outside of the wall to extend the lever arm like an outrigger on a crane. However, it's actually more beneficial for the footing to extend inward into the retained soil. That's because the earth behind the wall sits atop the footing, which acts as a lever to keep the wall upright against lateral forces. Retaining walls that rely only on their own weight and the weight of the soil above them to remain stable are called gravity walls, for obvious reasons, and the ones that use a footing like this are called cantilever walls. One common type of retaining wall involves tying a mass of soil together to act as its own wall, containing the unreinforced soil beyond. And these walls can be subject to or constructing a building in a dense urban area starting at the base of the level. Cement grout is added to the hole to bond the soil nail to the surrounding earth. Both mechanically stabilized earth and soil nails are commonly used on roadway projects, so it's easy to spot them. Consists of shotcrete, a type of concrete that can be sprayed from a hose using compressed air. For permanent installations, engineers often use interlocking concrete panels with a decorative pattern. One disadvantage of soil nails is that the soil has to settle a little bit. In some cases, it needs more soil to use an active solution, usually called anchor tieback. Just like soil nails, anchors are installed in drilled holes at regular stations. They usually need a lot of rubber. Also, unlike soil nails, they aren't grouted along the entire length. Instead, part of the anchor is installed inside a sleeve filled with grease, so you end up with a bonded link and an unbonded link. That's because once the grout settles, a hydraulic jack is used to tension each one. The unbonded link acts like a rubber band to store that control. Once the anchor is locked off, usually using a knife combined with a wedge-shaped washer, the tension in the unbonded link applies a force to the base of the wall, holding the soil back. Anchored walls often have plates, bearing blocks, or beams called railers to distribute the tension force across the length of the wall. One final type of wall driven like massive things. When they're in a road type of they call sometimes they are overlapped, called sequence piles, to make them more watertight. In this case, the primary piles are installed without steel reinforcements, and before they cure too hard, secondary piles have reinforcements to provide alternatively, you can use interlocking steel shapes called sheet piles. These are humongous hammers or vibratory rigs. Pile walls depend on the resistance in the soil below. Pile walls are often used during construction. The wall can be made of furniture before digging begins, ensuring that the excavated faces have support for the entirety of construction. All these types of retaining walls perform perfectly if designed correctly, but retaining walls decay. There are a few reasons why. One reason is just under designing for lateral earthing. It's not intuitive how much force soil can apply to a wall, especially because the slope is often holding itself up during construction. Earth pressure behind a wall can build gradually, such that failure doesn't even start until many years later. Lots of retaining walls are built without any involvement from the engineer, and it's easy to underestimate the loads if you're not familiar with soil mechanics. Most cities require that anything taller than around 4 feet or 1.5 meters be designed by a professional engineer. As I mentioned, soil loads aren't the only forces applying to walls. Some fail when unanticipated surcharging loads are introduced, like larger buildings or heavy vehicles driving too close to the edge. If you're ever putting something heavy in a retaining wall, whether it's building a new swimming pool or operating a crane, it's usually best to have an engineer review beforehand. Water is another challenge with retaining walls. Not only does water pressure add to the earth pressure, in some climates it can freeze. When water freezes, it expands with a force that is nearly impossible to restrain, and you don't want that happening to the face of a wall. Most large walls are built with drain walls, bypassing the wall altogether. All of these walls, or soil, multiple piers, or lots of groundwater, engineers perform a global stability analysis as part of design. This involves using computer software that can compare the loads and strength along a huge number of potential shearing planes and make sure that a wall won't collapse. Look around and you'll see retaining walls everywhere, holding back slopes so we all have a little more space in our constructed environment. It might just look like a pretty concrete base on the outside, but now you know the important job they do and some of the engineering that makes it possible. Our little helper got to open the box, but he went to bed so we could poop around. HelloFresh has a bunch of options to choose from depending on your taste. You get to pick a carrot meal, and the recipes are dishes we would never think to make ourselves. Key portion ingredients means there's less theft and less food waste, and the packaging is already recycled content, and most of it's recyclable as well. Go try it yourself at HelloFresh.com. If you use code PRACTICAL14, you'll get 14 free meals and 3 free gifts. Supporting our sponsors helps support this channel. That's HelloFresh.com and use my code PRACTICAL14. Thanks HelloFresh and thank you for watching. Let me know what you think. The Millennium Tower is the tallest residential building in San Francisco, with 58 stories above the ground and 419 luxury condominium units. The tower opened to residents in 2009, but even before construction was finished, engineers could tell that the building was slowly sinking into the ground and tilting to one side. How do engineers predict how soils will behave under extreme loading conditions? And what do you do when a skyscraper's foundation doesn't perform the way it was designed? Let's find out. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the Millennium Tower in San Francisco. Skyscrapers are heavy. That might seem self-evident, but it can't be overstated in a story like this. An average single-story residential home is designed to apply a pressure to the subsurface of maybe 100 pounds per square foot of building footprint. That's about 5 kilopascals, the pressure at the bottom of a knee-deep pool of water. With its concrete skeleton, the Millennium Tower was designed to impose a load of 11,000 pounds per square foot, or 530 kilopascals to its foundation, about 100 times more than an average house. It would be impossible for just the ground surface to bear that much weight, especially in this case, where the ground surface is a weak layer of mud and rubble placed during the city's infancy to reclaim land from the bay. That tremendous pressure is why most tall buildings use deep foundation systems. The Millennium Tower's foundation consists of a 10-foot or 3-meter thick concrete slab supported by 950 concrete friction piles driven into the subsurface to a depth of about 80 feet or 24 meters. Friction piles spread out the load of the building vertically, allowing much more of the underlying soils to be used to support the structure without becoming overwhelmed. The piles also allow the foundation to bear on stronger soils than those at the surface. Driving the piles so deep allowed the building to not sit on the surface layer of artificial fill or even the soft underlying layer of mud, but rather on the dense, sandy soil of the Colma Formation below. This is a fairly common design in San Francisco, with more than a dozen tall buildings in the downtown area utilizing a similar foundation system, including some nearly as large as this one. However, it's not the dense sands causing problems for the Millennium Tower, but what's underneath. Below the Colma Formation is a thick layer of Ice Age mud, locally known as the Old Bay Clay. Thanks to the geologist for that name. When the building was designed, the project geotechnical engineers predicted that it would settle 4 to 6 inches, or 10 to 15 centimeters, over the structure's entire lifetime, mainly from this layer of Old Bay Clay below the bottom of the piles. But even before construction was complete, the building had already settled more than that. I have a video that goes into greater detail about soil settlement that you can check out after this, but let me summarize the high points here. The ground below your feet may seem firm and stable, but when subjected to increased loading, and especially when that loading is extreme, like that of a concrete skyscraper, soil can compress in a process called consolidation. Essentially, the soil is like a sponge filled with water. An increased load will slowly squeeze the water out, allowing the grains to compress into the empty space. Settlement is usually a gradual process because it takes time for the water to find a path out from the soil matrix. But some things can accelerate the process, even if they're not intentional. The Millennium Tower was already designed to put more stress on the underlying Old Bay clay than any other building in the area. However, construction of the tower's basement also required the contractor to pump water out of the subsurface to keep the site dry. This is often done using vertical wells similar to the ones used for drinking water, but usually not as deep. This deliberate and continuous dewatering of foundation soils accelerated the settlement. Then other construction projects nearby began, including the adjacent Transbay Transit Center, which required their own deep excavations and groundwater drawdowns. All these factors added up to a lot more settlement than was initially anticipated by the project's geotechnical engineer. The result was that by 2016, when the public first learned about the issue, the building had already sunk more than 16 inches or 41 centimeters. Triple the movement that was anticipated for its entire lifetime. Unfortunately, that settlement wasn't happening immediately. Instead, the northwest corner had sunk a little lower than the rest of the foundation, causing the tower to tilt several inches in that direction. The media had a field day reporting on the Leaning Tower of San Francisco, and accusations started flying about who was to blame and whether the city had covered up details about the building's movement. The developer continued insisting that the building was safe, reiterating that all buildings settle over time and the Millennium Tower was no different. But it definitely was different, at least in magnitude. With so much attention to the building, the city commissioned a panel of experts in 2017 to assess its safety, both for everyday use and in the event of a strong earthquake. By that time, the building had settled another inch and was out of plumb by more than a foot or 30 centimeters. That's not something you could notice by eye and was probably only discernible to the most perceptive residents, but it's well beyond the 6 inches allowed by the building code. Even so, the panel found that the building was completely safe, and the settlement had not compromised its ability to withstand strong earthquakes. However, they cautioned that the movement hadn't stopped and further tilting may affect the building's safety. At the same time, and despite engineering assessments confirming the building's safety, the condominium prices were plummeting. No one wanted to live in a building that was sinking into the ground with no sign of slowing down. It didn't take long for lawsuits to be filed. By the end of it, just about every person and organization related in any way to the Millennium Tower was involved in at least one lawsuit, including individual residents, the Homeowners Association, the building developer, the Transbay Joint Powers Authority, and many others. In total, there were 9 separate lawsuits involving around 400 individual parties. After many years of complex litigation, a comprehensive settlement of the legal kind was eventually reached through private mediation. The result was that no one took the blame for the building's excessive movement, condo owners would be compensated for the loss of property values, and most importantly, the building would be fixed. During mediation, the retrofits to the building's foundation to slow the sinking and de-tilt the tower were a big point of contention. One early plan was to install hundreds of micropiles, small diameter drilled piles, through the existing foundation down to bedrock. But the estimated cost for the repair was as much as $500 million, more than the original cost of the entire building. Turns out it's a lot easier to drill foundation piles before the building's built than afterwards. The challenges associated with working below the building, like access, vibrations, noise, and lack of space, drove up the price, and the parties couldn't agree to pay such a substantial cost. An unconventional alternative proposed by the developer's engineer ended up resolving the dispute, and as of this writing, is currently under construction. The proposed fix to the Millennium Tower is to install piles along two sides of the building's perimeter. That may seem kind of simple, but there's a lot of clever engineering involved to make it work. 52 piles will be drilled along the north and west sides of the tower, all the way down to bedrock. Unlike the original plan, these piles will be installed outside the building below the adjacent sidewalks, saving a significant amount on the construction costs. An extension of the building's existing concrete slab will be installed around each pile, but not within the tower. Instead, the pile will be removed and extended above the That means each one will be carrying around 800,000 pounds, or 360,000 kilograms. Everything will be backfilled and the sidewalks will be replaced. If all goes according to plan, the settlement on the north and west sides of the building will be completely arrested. With less load on the original foundation, the sinking of the other two sides will gradually slow to a stop. And this one is no different. The city of San Francisco and the design engineers were carefully monitoring the building's movement. Sinking started to increase as the drilling continued. In August 2021, as of this point, crews are testing some revised drilling procedures that they hope will reduce the disturbance to the clay layer so they can get those piers installed and the building supported as quickly as possible. Especially when those soils are far below the surface, where we can only guess their properties and extents based on a few borehole samples. In addition, property lines with great problems by underestimating the impacts that adjacent properties can create. Most people will wonder why the building's foundation didn't just go to bedrock in the original design. They don't think it's necessary for geotechnical and structural engineers to go back in time. I think they probably would go with a different foundation. But whether they could have reasonably predicted the performance of the original design with all the restricted watering and adjacent construction is a more complicated question. The Millennium Tower is also an interesting case study in the relationship between engineers and the media. The developers' engineers in the city have shown that the building is perfectly safe through detailed modeling and investigation. And yet, the prices of those luxury condominiums plummet with the frenzy reporting about the settlement tilting. Those prices depend not only on buyers' confidence in the building's safety, but also their willingness to be associated with a building that is regularly in the news. The value in the multi-million-dollar repair project will be not just to slow down the settlement, but also to slow down the articles, news sections, memes, and tourists from remembering this building as the Leaning Tower of San Francisco. I know I say this at the end of all my videos, but this is not the whole story. I did my best to summarize the high points, but there are many more details to this saga. I definitely encourage you to seek out those details before drawing any hard conclusions. It's an excellent example of the challenges and complexity involved in large-scale engineering projects, the limitations and uncertainty in engineering practice, and the interconnectedness of regulations, engineering, and the media. I'll be keeping an eye on the progress of the foundation retrofit. Thank you for watching. Let me know what you This is the SpaceX South Texas launch facility on South Padre Island near Boca Chica, or at least it's how the facility started out. Before the so-called Starbase supported crazy test launches of the Starship spaceflight program, it was just a pile of dirt. Contractors brought in truck after truck of soil, creating a massive matrix of more than 300,000 cubic yards or 230,000 cubic meters of earth. That's a lot of Olympic-sized swimming pools. Not that you'd want to go swimming in it. After nearly 2 years, they hauled most of that soil back off the site for disposal. It might seem like a curious way to start a construction project, but foundations are critically important. That's true for roads, bridges, pipelines, dams, skyscrapers, and even futuristic rocket launch facilities. The Texas coastline isn't known for its excellent soil properties, so engineers had to specify some extra work before the building's tanks and launch pads could be constructed. Building that giant pile of dirt was a clever way to prevent these facilities from sinking into the ground over time. Why do some structures sink, and what can we do to keep it from happening? I'm Grady, and this is Practical Engineering. In today's episode, we're talking about soil settlement. This video is sponsored by Morning Brew. More on that later. The Earth's gravity accelerates us and everything else on our planet downward. To keep us from falling toward the center of the planet, we need an equal and opposite reaction to keep us in place. If you're at the top of a skyscraper, your weight is supported by floor joists that transfer it to beams, that transfer it to columns, that transfer it downward into massive concrete piers, but eventually the force of you must be resisted by the Earth. It's ground all the way down. You might not think about the ground and its critical role in holding stuff up, but the job of a geotechnical engineer is to make sure that when we build stuff, the earth below is capable and ready to support that stuff for its entire lifespan. Every step you take when walking along the ground induces stress into the subsurface. And every rocket launch facility you build on the Texas coastline does the same thing. This isn't always a big deal. When constructing on bedrock, there's a lot less to worry about, but much of the Earth's landscape consists of soil, granular compositions of minerals. Stress does a funny thing to soils. I mean, it does some funny things to all of us, but to soils too. At first consideration, you might not think that there's really much difference between rock and soil. After all, soil particles are just tiny rocks, and many sedimentary rocks are made from accumulated soil particles anyway. But soil isn't just particles. In between all those tiny grains are empty spaces we call pores, and those pores are often filled with water. Just like squeezing a sponge forces water out, introducing stress to a soil layer can do the same thing. I built a little demo out here in my garage to show how this works. This device is called an odometer. It's basically a piston and cylinder with holes for drainage at its end. I filled it up with soil from my backyard that was nice and saturated from recent rain. Next, I put this porous stone on top of the soil to filter particles from getting out of the drain hole. Finally, I put a weight on top to introduce some stress to this material. Over time, water is forced to exit the pore space of the soil and flow up and out of my sample. As the water departs, the soil compresses to take up the void left behind. This process is called consolidation. Not many mechanisms for substance, but it is the main one, especially for soils that are made up of fine particles. Large grained soils like sand and gravel interlock together and don't really act like a sponge so much as a solid, porous object. To the extent they do consolidate, it happens almost immediately. You can squeeze and squeeze, but nothing happens. Fine-grained soils like clay and silt are different. Like sand or gravel, the particles themselves aren't very compressible. However, unlike in coarse-grained soils, fine particles aren't so much touching their neighbors as they are surrounded by a thin film of water. When you squish the soil, the tiny particles rearrange themselves to interlock, pressurizing the pore water and ultimately forcing it out. The dial indicator on top of my demo shows how far the soil compresses in the time lapse. It's pretty easy to imagine that this weight is something you've built, like a building or a dam. The soil below the weight is, well, it's the soil below your structure. The more weight you add, the more stress goes into the subsurface, the more water is forced out of the pores, and thus the further the soil settles. Geotechnical laboratories perform a similar test, but with much more scientific rigor. Apologies to all the soil lab technicians who are shaking their odometers right now. I'm not trying to carefully characterize the soil in my backyard, but just show how the process works. This may seem obvious, but when we build stuff, we don't want it to move. We want the number on that dial to stay the same for all of eternity, or at least until the structure is at the end of its lifespan. That idea that when you build something, it stays put is essentially all of geotechnical engineering in a nutshell. It encompasses the entirety of foundation design, from the simplest slabs of concrete for residential houses to the highly sophisticated substructures of modern bridges and skyscrapers. The way movement occurs also matters. It's actually not such a big deal if settlement happens uniformly. After all, in many cases, the movement is nearly imperceptible. I'm using a special instrument just so you can see it on camera. Many buildings can take a little movement without much trouble, but often settlement doesn't happen uniformly. For one, structures don't usually impose uniform loads. If everything we built was uniform in size and density, we might be okay, but that's never the case. No matter what you're constructing, you almost always have some heavy parts and other light parts that stress the soil differently. On top of that, the underlying geology isn't uniform either. Take a look at any road cut to see this. The designers of the bell tower at the Pisa Cathedral in Italy famously learned this lesson the hard way. Small differences in the soils on either side of the tower caused uneven settlement. Geotechnical engineering didn't exist as a profession in the 1100s, and the architects would have had no way of knowing that the sand layer below the tower was a little bit thinner on the south side than the north. It didn't take long after construction started for the tower to begin its iconic leaning. I should point out that there's another soil effect that can cause the opposite problem. Certain types of soils expand when exposed to increased moisture, introducing further complications to a geotechnical engineer. I have a separate video on that topic, so check it out after this if you want to learn more. Settlement made the Tower of Pisa famous, but in most cases, it just causes problems and costs a lot of money to fix. One of the most famous modern examples is the Millennium Tower in San Francisco, California. This 58-story building was constructed atop the soft, compressible fill and mud underlying much of the Bay Area. Engineers used a foundation of piles driven deep below the building to a layer of firmer sand, but it wasn't enough. Only 10 years after construction, the northwest corner of the building had sunk more than 15 inches, 46 centimeters into the earth, causing the building to tilt. Over time, some of the building's elements were damaged or broken, including the basement and pavement surrounding the structure. As you would expect, there were enough lawsuits to fill an Olympic-sized swimming pool. The repairs to the building are in progress at an estimated cost of $100 million, not to mention the who knows how much in legal fees. One of the most reliable ways to deal with settlement is just to make sure it happens during construction instead of afterwards. As you build, you can account for minor deviations as they occur. Unfortunately, consolidation isn't always a speedy process. The voids in clay soils are extremely small, so the path that water has to take in order to exit the soil matrix is long and winding. We call this windiness sinuosity. You can see in my demo that the bottom part of the sample is much less compacted than the top. These void spaces you can see along the sides of the cylinder aren't representative of the voids inside the clay. They're comparatively huge, but the water in the big voids has to percolate through the tiny void spaces in the soils above in order to exit the sample. I ran this demo for about a day, but in a real setting, depending on the soils and loads applied, The consolidation process can take years to complete. It's not a good idea to build a structure that will settle unevenly over the next several years. Hopefully it's obvious that that's a bad design. So we have a few options. One is to use a concrete slab that's stiff enough to distribute all the forces of the structure evenly and provide support no matter how non-uniformly the settlement occurs. These slabs are sometimes called raft foundations because they ride the soil like a raft in the ocean. Another option is to sink deep piles down to a firmer geologic layer or bedrock so that loads get transferred to material more capable of handling them. But both of those options can be quite expensive. A third option is simply to accelerate the consolidation process so that it's complete by the end of construction. One way to speed up consolidation in clay soils is to introduce a drainage system. Settlement is mainly a function of how quickly water can exit the soil. In a clay layer, particularly a very thick layer or one underlain by rock, the only way for water to leave is at the surface. That means water well below the ground has to travel a long distance to get out. We can shorten the distance required to exit the soil by introducing drains. This is often done using prefabricated vertical drains called PVDs or wick drains. These plastic strips have grooves in which water can travel, and they can be installed by forcing them directly into the subsurface using heavy machinery. An anchor plate is attached, the drain is pressed into the soil to the required depth, the mandrel is pulled out, and the material is cut. It all happens in quick succession, allowing close spacing of drains across a large area. The tighter the spacing, the less distance water has to exit. One of the other benefits here is that water often travels through soils horizontally faster than it does vertically, since geologic layers are usually horizontal. That speeds up consolidation even more. I put some rolled up paper towels in my odometer with another sample of clay from my backyard. It's pretty easy to see in the time lapse that the soil is compressing more evenly across its entire length instead of slowly from top to bottom. This isn't a perfect scientific comparison since these samples are far from identical, but I still think it clearly tells the story. Plotting the displacement over time for both samples, the benefit of vertical drains is unmistakable. The second way we speed up consolidation is surcharge loading. This is applying stress to the foundation soils before construction to force the water out quickly. Like I described in the intro at SpaceX South Texas, it's usually as simple as hauling in a huge volume of earth to be temporarily placed on site. The way this works is as straightforward as squeezing a sponge harder. It's the equivalent of adding more weight to my acrylic odometer, but it's simpler just to show a graph. Let's say you're going to build a structure that will impose a stress on the subsurface. That stress corresponds to a consolidation like a red lump. If you load the foundation soils with something heavier than the structure, that weight will be associated with greater consolidation. It's going to take about the same time to reach a certain percentage of consolidation in both cases, but you're going to hit the target consolidation, the red line, much faster. In many cases, engineers will specify both weight drains and surcharging to consolidate the soil as quickly as possible so the construction can begin. Once you get rid of all that extra soil you brought in, you can start building on your foundation knowing that it's not going to settle further over time. One of the best decisions I ever made was to cut back on the amount of news I read and listen to. My mental health and happiness are susceptible to the black hole of 24/7 news media. But I can't just shut it all off. I still have to make good decisions based on what's happening in the world. Not to mention that I like to have topics for conversation with my friends and wife. I decided that my news diet needed to be very intentional, and Morning Brew is fitting that need for me. Morning Brew is a daily newsletter on business, finance, and technology delivered to your inbox every day, and it's completely free. They boil down the most important news of the day, summarizing top stories so you get a balanced overview of what's happening across the world. Morning Brew has snappy rundowns with links if you want to dive deeper, like the story about Blue Origin's proposal for a private space station called Orbital Reef. If you want to stay up to date on current events without falling down the news rabbit hole, give Morning Brew a try completely free at the link in the description. It only takes 15 seconds to subscribe. Supporting our sponsors helps support this channel. Thanks Morning Brew, and thank you for watching. Let me know what you think. May 18th, 2020, heavy rainfall in Michigan raised the level of Wixom Lake, a man-made reservoir impounded by Edenville Dam, higher than it had ever gone before. As the reservoir continued to rise the following day, the dam suddenly broke, sending a wall of water downstream. As it traveled along the Tittabawassee River, the flood wave reached and quickly overpowered the Sanford Dam downstream. The catastrophic failure of the two dams impacted more than 2,500 structures and caused more than $200 million in damage. The independent forensic team charged with investigating the event released an interim report on the failures in September 2021. The conclusions of the report include a discussion of a relatively rare phenomenon in earthen dams. Let's walk through the investigation and try to understand what happened. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the failures of Edenville and Sanford dams.
Let's go to the rocks.
Edenville and Sanford dams were two of four dams owned by Boyce Hydropower along the Tittabawassee River in Michigan. The dams were built in the 1920s to generate hydroelectricity. Edenville Dam was constructed just upstream of the confluence with the Tobacco River. It was an earth-fill embankment dam with two spillways and a powerhouse. The water impounded by the dam formed a reservoir called Wixom Lake, nearly the entire perimeter of which was surrounded by waterfront homes. State Highway 30 bisected the dam along a causeway, splitting the lake between the two rivers with a small bridge to allow water to flow between the two sections of the reservoir. Sanford Dam downstream was a similar structure as Edenville, but not nearly as long. It consisted of an earthen embankment, a gated spillway, an emergency spillway, and a powerhouse for the turbines, generators, and other hydroelectric equipment. Edenville Dam in particular had a long history of acrimony and disputes between the dam owner and regulatory agencies. Most dams that generate hydroelectricity in the U.S. are subject to oversight by the Federal Energy Regulatory Commission, or FERC. But Edenville Dam had its license to generate hydropower revoked in 2018 when the owner failed to comply with FERC's safety regulations. Their report listed 7 concerns, the most significant of which was that the dam didn't have enough spillway capacity. As a result, if a severe storm were to come, the dam wouldn't be able to release enough water to prevent the reservoir level from climbing above the top of the structure, overtopping it and likely causing it to fail. After losing the license to generate hydropower, jurisdiction over the dam fell to the state of Michigan, where disagreements about its structural condition, spillway capacity, and water levels in Wixom Lake continued. The days before the failure had already been somewhat rainy, with small storms moving through the area, but heavy rain was in the forecast for May 18th. The deluge arrived early that morning, and it didn't take long for the water levels in Wixom Lake to begin to rise. By 7 a.m., operators at the dam had started opening gates on both spillways to release some of the floodwaters downstream. Gate operations continued throughout the day as the reservoir continued rising. At 3:30 p.m., all 6 gates, 3 at each spillway, were fully open. From then on, there was nothing more operators could do to get the floodwater out faster, and the level in Wixom Lake continued to creep upwards. That night, the lake reached the highest level in its history, only about 4 feet or 1.3 meters below the top of the earthen dam. At daybreak on May 19th, it was already clear Edenville Dam was struggling from the enormous forces of the flood. Operators noticed severe erosion from the quickly flowing water in the reservoir near the east spillway along the embankment. Regulators and dam personnel met to review the damage, and a contractor was brought in to deploy erosion control measures. And still, the water kept rising. By 5 p.m., Wixom Lake had risen to within around a foot or 30 centimeters from the top of the dam. As crews worked to mitigate the erosion problems in other places, eyewitnesses noticed a new area of depression on the far eastern end of the dam. This part of the embankment hadn't been a significant point of focus during the flood because it wasn't experiencing visible erosion, but it was apparent something serious had happened. Photos from a few hours earlier didn't show anything unusual, but now the top of the embankment sank down nearly to the reservoir level. Eyewitnesses moved to the nearby electrical substation to get a better look at this part of the dam. Within only a few moments, the embankment failed. Lynn Coleman, a Michigander and one of the bystanders, caught the whole thing on camera. Over the next 2 hours, all of Wixom Lake drained through the breach in the dam. Water rushing through the narrow gap in the causeway washed out the highway bridge, and all of the waterfront homes and docks around the entire perimeter of the lake were left high and dry. As the floodwaters rushed through the breach into the river, the level downstream in Sanford Lake rose rapidly. By 7:45, the reservoir was above the dam's crest, quickly eroding and breaching the structure. With the combined volumes of Wixom and Sanford Lakes surging uncontrolled down the Tittabawassee River, downstream communities including Sanford, Midland, and Saginaw were quickly inundated. Google Earth shows aerial imagery before, during, and after the flood, so you can really grasp the magnitude of the event. More than 10,000 people were evacuated, and flooding damaged more than 2,500 structures. Amazingly, no major injuries or fatalities were reported. In their interim report on the event, the independent forensic team considered a broad range of potential explanations for what happened at Edenville Dam. Although the spillway for the dam was undersized per state regulations, this storm didn't completely overwhelm the structure. The level in Wixom Lake never actually went higher than the top of the embankment. So overtopping, one of the most common causes of dam failure, including the cascading loss of the downstream Sanford Dam, was eliminated as a possible cause of failure for Edenville Dam. The team also looked at internal erosion, a phenomenon I've covered on this channel before that has resulted in many significant dam failures. Internal erosion involves water seeping through the soil and washing it away from the inside. However, this type of erosion usually happens over a longer time period than what was witnessed at Edenville Dam. No water seepage exiting the downstream face of the embankment or eroding soil was evident in the time leading up to the breach, ruling this mechanism out as the main cause of failure. The forensic team determined that the actual cause of failure was static liquefaction, a relatively unusual mechanism for an earthen dam. Soils are kind of weird, but don't tell that to the geotechnical engineers. Because they're composed of many tiny particles, they can behave like solids in some cases and liquids in others. Of course, most of our constructed environment depends on the fact that soils mainly behave like solids, providing support to the things we build on top of them. Liquefaction happens when soil experiences an applied stress, like an earthquake, that causes it to behave like a liquid. And it mostly happens in cohesionless soils, those where the grains don't stick together, such as sand. When a body of cohesionless soil is saturated, water fills the pore spaces between each particle. When a load is applied, the water pressure within the soil increases, and if it can't flow out fast enough, it forces the particles of soil away from each other. A soil's strength is derived entirely from the friction between the interlocking particles. So, when those grains no longer interlock, the ground loses its strength. Some of the most severe damage from earthquakes comes from the near instant transformation of underlying soils from solid to liquid. Buildings sink into their foundations, sewer lines float to the surface, and roads crumble without underlying support. Liquefaction typically requires cyclical loading, like during an earthquake, or extreme sudden displacements to trigger the flow. Gradual increases in loading will only cause the water within the soil to flow out, equalizing the pore water pressure. But some soils can reach a point of instability and liquefy under sustained or gradually increasing loading conditions in certain circumstances. This phenomenon is known as static liquefaction. A good analogy is the difference between glass and steel. Both materials have a linear stress-strain curve at first. In simple terms, the harder you push, the harder they push back. But both reach a point of peak strength, beyond which a soil will fail or deform. Well-compacted sand is like steel. It fails with ductile behavior. If you stress it beyond its strength, it deforms, but the strength is still there. In other words, if you want to keep deforming it, you have to keep applying a force at its peak strength. On the other hand, loose sand is like glass. If you push it beyond its peak strength, it fails with brittle behavior, suddenly losing most of its strength. The independent forensic team took samples of the soils within the Edenville Dam embankment and subjected them to testing to see if they were liquefiable. The tests showed brittle collapse behavior necessary for static liquefaction. They also reviewed construction records and photographs where no compaction equipment was seen. The team concluded that as the level of Wixom Lake rose that fateful May evening, it increased the hydraulic load on the embankment, putting more stress on the earthen structure than it had ever been asked to withstand. In addition, the higher levels may have introduced water from the reservoir to permeable layers of the upper embankment, as evidenced by the depression that formed before the failure, increasing seepage and thus increasing the pore water pressure of saturated, uncompacted sandy soils within the structure. Eventually, the peak strength of the embankment soil was surpassed and a brittle collapse resulted, liquefying enough soil to breach a downstream section of the dam. A few seconds later, lacking support from the rest of the structure, the dam's upstream face collapsed, and all of Wixom Lake began rushing through. Edenville Dam was built in the 1920s, before most of our current understanding of geotechnical engineering and modern dam safety standards existed. Most dams are earth and embankment dams, but modern ones are built much differently than this one was. Embankments are constructed slowly from the bottom up in individual layers called lifts. This lets you compact and densify every layer before moving upward, rather than just piling up heaps of loose material. We use gentle slopes on embankments to increase long-term stability, since soils are naturally unstable on steep slopes. We have strict control over the type of soil used to construct the embankment, constantly testing to ensure the properties match or exceed the assumptions used during design. We often build an embankment of multiple zones. The core is made of clay soils that are highly impermeable to seepage, while the outer shells have less stringent specifications. We include rock riprap or other armoring on the upstream face so that waves and swift water in the reservoir can't erode the vulnerable embankment. And we include drains that both relieve pressure so it can't build up within the soil and filter the seepage to prevent it from washing away soil particles from inside or below the structure. Edenville Dam actually did have a primitive internal drainage system made from clay tiles, but many of the drains in the area of the failure appeared to be missing in a recent inspection. Although it seems like an outlier, the story of Edenville and Sanford dams is not an unusual one. There are a lot of small old dams across the United States built to generate hydropower in a time before everyone was interconnected with power grids. Over time, the revenue that comes from hydropower generation gradually declines as the maintenance costs for the facility and the danger the dam poses to the public both increase. However, the reservoir created by the dam is now a fixture of the landscape, elevating property values, creating communities and tourism, and serving as habitat for wildlife. You end up with a mismatch of value where most of the dam's benefits are borne by those who don't incur any responsibility for its upkeep, or liability for the threat it poses to downstream communities. Even owners with the best intentions find themselves utterly incapable of good stewardship. Combine all that with the fact that regulatory authorities are often underfunded and lack the resources to keep a good eye on every dam under their purview, and you get a recipe for disaster. After all, there's only so much you can do to compel an owner to embark on a multi-million-dollar rehabilitation project for an aging dam when they don't have the money to do it and won't derive any of the benefits as a result. Since the failure, the dam owner, Boyce Hydro, filed for bankruptcy protection, and the counties took control of the dams with a nonprofit coalition of community members and experts to manage repair and restoration efforts. Of course, there's a lot more to this story than just the technical cause of the failure, and the final independent forensic team report will have a deeper dive into all the human factors that contributed to the failure. They expect that report to be released later in 2021. Dams are inherently risky structures, and it's unfortunate that we have to keep learning that lesson the hard way. Thank you for watching, and let me know what you think. In November 2020, the rocket company SpaceX was just starting to make some progress in the testing program for their new vehicle, Starship, one of the most ambitious rocket projects in history. One of the prototypes, serial number 8, was on the pad to test fire the engines for the very first time as a fully stacked vehicle. Almost as soon as the engine lit up, it was clear that something was wrong. A shower of sparks exploded in the dusky sky, and the engine abruptly stopped. The sparks looked innocuous at a distance without a reference for scale, but in reality, they consisted of massive, glowing chunks of the launch pad below the rocket. One of these chunks was blasted into the engine bay, severing an essential cable and severely damaging the rocket. The event brought into the spotlight what is probably the most humble piece of engineering of the entire rocket industry, the pad. How do we build structures that can withstand such insane conditions? What happens when they don't work? And how might we solve these challenges on other planets? I'm Grady, and this is Practical Engineering. In today's episode, we're talking about launch pads and refractory concrete. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. Rocket launch pads are subject to conditions that aren't very similar to typical infrastructure. There are a lot of creative ways to manage the extremely high-temperature exhaust gases barreling out of a rocket engine at incredible speeds during a launch. With the Space Shuttle and in-progress SLS, the launch facilities incorporate a flame trench. This is a structure used to deflect the exhaust gases of a rocket away from the vehicle itself and all the delicate support structures, fuel and power lines, etc. But a launch isn't the only time that rockets and their fiery engines get close to the ground. SpaceX and other launch providers are now landing rockets propulsively, in other words, with engines. And in most cases, the coming down has a lot less precision than the going up. It isn't feasible to pinpoint a rocket landing atop a fancy flame diversion structure, at least not yet. Instead, they usually just land on a slab of concrete. But it's not just regular concrete. The relationship between heat and that omnipresent gray durable substance is pretty complex, and I have a few demonstrations set up here in my garage so we can learn more. Concrete is a relatively fire-resistant material. That's one of the reasons we use so much of it in our buildings and infrastructure. It doesn't burn. It can provide protection, like around stairwells of buildings. It can also withstand exposure to risky conditions that we wouldn't allow for other materials, like in warehouses and factories where there's potential for sparks. Because it's so durable and incombustible, there's a lot of science around the topic of concrete and fire. Engineers have to consider how to design structures that can withstand it, and if fire has occurred, we need engineers to inspect structures to figure out whether they've been damaged beyond repair or are still safe to use. That can be pretty obvious in some cases, but concrete can be damaged in ways that aren't immediately clear to the naked eye. When the damage is obvious, it's probably because of moisture. Concrete is a porous material, and it can absorb water from the air, but it's not super porous. After all, we build dams out of concrete. Moisture can take years to get in after it's cured. If that water gets too hot, it can turn to steam, expanding in volume within the interstitial spaces of the concrete. And if that steam can't get out fast enough, it will build up pressure to the point where the concrete breaks. This is known as moisture clog spalling because the water in the pores of the concrete blocks the steam from getting out. Actually, I did try to simulate this effect, but my heat wasn't enough or my sample was too small and gave the steam too many easy paths to exit. I wasn't able to make it spall, but you can see some water exiting the sample. What I really want to show you is how concrete heat damage can be more subtle and insidious. I'm making a bunch of cylinders of concrete, and we're going to test their strength after exposure to extreme heat. These samples are just made with regular old Portland cement concrete from a ready mix bag purchased from a home center. Just for fun, I'm also making equivalent samples from a specialty concrete that uses materials resistant to deterioration from high heat, also known as refractory concrete. I'm testing 3 different scenarios: controls left at room temperature with no heat, samples warmed in my oven to 500 degrees F, 260 C, and samples blasted using a gas torch. 2 types of concrete times 3 different temperatures times 2 samples means I have 12 cylinders in all. But I made a few more just in case something went wrong. They come in handy sometimes. Once they've all been heated, except the controls, I let them sit in my garage for a week. Now it's time to break them. Using a hydraulic press to crush a concrete cylinder isn't just a lot of fun, it's the time-tested and industry-approved way of figuring out how strong the concrete is. On almost all construction projects that use concrete, samples of the mix are taken to a laboratory, cured in cylindrical molds, and crushed on a press to verify the concrete was as strong as required. We're doing the same thing here to see if the heat affected the strength of these samples. Before we get started, let's just take a look. From the outside, it's not clear that anything's different, but let's find out if that's true. The regular concrete control cylinders broke at around 3,000 psi or 20 megapascals. Unfortunately, the refractory concrete control cylinders maxed out my little press here at 10 tons without break. That's 6,400 psi or 44 megapascals. This stuff has small fibers in it to provide some insulation against heat and reduce cracking, and they also help make it much stronger. A fair comparison isn't going to be possible, but I still think this demo is illuminative, if you'll pardon the pun. Now I'll break the heated samples. The ones that went into the oven spent about an hour there to make sure they were fully heated. The Portland cement cylinders broke at an average of 2,200 psi or 15 megapascals. That means they lost about 25% of their compressive strength compared to the unheated samples. We'll talk about why in a minute. The refractory concrete samples out of the oven still wouldn't break. They may have lost some strength, but it wasn't enough to break in my 10-ton press. The samples that got the blowtorch were next, and the effect was dramatic on the Portland cement concrete. Both samples broke at around 1,300 psi or 9 megapascals, losing more than half of their original strength. The refractory cylinders did break this time, although it was still at nearly the maximum pressure I could deliver. The lesson here is pretty simple. Concrete exposed to high temperatures might look fine even when it's lost a significant amount of strength. But why? The biggest culprit is microcracking caused by thermal expansion. Concrete is a composite material after all. It's made from a mixture of large and small aggregates and cement base. Most materials change volume according to temperature, expanding when hot and shrinking when cool. But the materials that make up concrete have slight differences in the way they behave when subjected to changes in temperature. Those differences aren't so critical when the temperature swings are small, but when subjected to extremes, like under the heat of a massive rocket engine, microfractures occur at the interfaces between the different components as they expand and shrink at different rates. I use these waxes that melt at different temperatures to try and estimate the temperature of the blowtorch samples. They probably didn't get much hotter than the oven samples in most places, but directly in line with the flame was scorching, probably over 1,000 degrees F, 500 C. That type of uneven heating from a small, incredibly hot source exacerbates this type of damage. The tiny cracks grow over time, weakening the concrete as they do, and they aren't usually visible to the naked eye. Interestingly, once the concrete is broken, it sometimes does carry a sign that it got too hot. Many of the aggregates used in concrete will turn pink after exposure to extreme heat. It doesn't show on camera quite as clearly as it does in person, but you can see that most of the rocks in the sample on the right are pinkish compared to the control cylinder on the left. Refractory concrete isn't a single material, but really a general name for concrete designed to withstand high temperatures. Every manufacturer has their special blend of herbs and spices. Usually they use cement that includes oxides, which absorb heat less readily and have reduced thermal expansion. So they're less prone to deterioration when subjected to extreme temperatures, as I demonstrated. They also have embedded fibers that provide insulation and tensile reinforcement, similar to the way rebar holds macroscopic cracks from growing. These extremely useful properties are taken advantage of in a variety of industrial processes like furnaces, kilns, incinerators, and even nuclear reactors. Like we saw in the demo, even refractory concrete is subject to damage due to heat. We don't know what the original strength was, but we do know it dropped below the capacity of the press after being blasted by a blowtorch. That potential for damage is especially present in the case of launch pads where concrete is not just exposed to heat, but also corrosive gases moving at incredible speeds and sometimes carrying solid airborne particulates capable of eroding even extremely durable materials. Many launch pads use a ceramic epoxy material to repair damaged areas of refractory concrete, or just to provide an extra layer of thermal insulation. It was actually a chunk of this epoxy called the martite that damaged the Starship engine during a static test flight. This demonstration highlights the difficulties that launch providers face. Landing pads are extremely important. Without them, rocket engines cause extensive erosion, blasting the loose soil atop the planet, called regolith, away at incredible speeds. This is one of the reasons the 2 recent Mars rovers used a complicated sky crane system for landing. The rovers themselves were lowered onto the planet via cables, while the rocket thruster nozzles stayed high above the surface. Once the wheels were safely on the ground, the cables were cut and the crane flew off to crash well away from the rover. It was all to reduce the potential for damage from those rocket engine plumes. In fact, when you land a rocket on the moon, the exhaust gases are moving faster than the planetary escape velocity. That means not only can the flying dust threaten the vehicle itself, the engines also send a plume of ejecta flying out like a swarm of microscopic bullets with no atmosphere and not enough gravity to slow them down. If an orbiting spacecraft were to fly through this plume, it would almost certainly be damaged. So moon landings have to be timed to prevent collisions between orbiting spacecraft and these sheets of ejected regolith. That's a lot of complexity that could be solved with a simple square of concrete. But what seems simple on Earth has some interplanetary complications. One more important than the others: concrete is heavy. That's one of its main features. Concrete structures mostly stay put because their weight pins them to the ground. But that weight is a huge disadvantage if you have to carry the raw materials to another planet. Reducing mass is everything when it comes to launch payloads, and the weight of an entire rocket is often less than the pad it takes off from. In other words, we won't be bringing concrete launch or landing pad assembly kits to the moon, Mars, or elsewhere anytime soon. There are some creative ideas for building launch pads on other planets that take advantage of local materials, and we've even made some lunar concrete using samples brought back to Earth. But, like almost all tasks that happen outside of Earth's comfort, it's never as easy as it seems at first glance. Stakes are high, as we saw during the static test of SpaceX's SN8. When a launch or landing pad fails, it can be worse than if it wasn't there at all, creating high-speed projectiles that jeopardize the safety of the vehicle and its support equipment, not to mention its crew. It's a nice reminder that even the humblest provision here on Earth, a solid, flat, and durable surface, is an absolute luxury on another world, and of the importance of infrastructure in our interplanetary quests. It's time for everyone's favorite segment of watching me try to cook while my wife and toddler try to capture that on video. Cooking dinner with a little one in the house can be a bit of an adventure. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night. We're indecisive eaters and get stuck in recipe ruts really easily. We end up eating the same meals every single week. But HelloFresh pulls us out of those ruts by curating delicious recipes from all over the world and with interesting ingredients to try.
Good thing oil is real easy to wash out of clothes.
The pre-portioned ingredients means there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner ready quickly when we haven't had time or energy for planning, prep, and shopping. Go try it yourself at HelloFresh.com and use code PRACTICAL14 to get 14 free meals, including free shipping. Supporting our sponsors helps support this channel. That's HelloFresh.com and use code PRACTICAL14. Thanks HelloFresh, and thank you for watching. Let me know what you think. On an autumn evening in 1989, Tom McMahon noticed some unusual construction getting started in his Los Angeles neighborhood. As more and more trucks began showing up with bizarre power tools, test equipment, and tanks of liquid nitrogen, his curiosity got the better of him, and he had to take a look. He learned that a high-voltage underground transmission line had experienced a fault, costing the city tens of thousands of dollars per hour in lost capacity and downtime. Over the next few months, he got more acquainted with the project manager for the repair, and he shared all the fascinating details of what he learned in a series of messages on his company's mailing list. Those messages spread like wildfire across various bulletin boards, lists, and forums of the early internet. I don't remember exactly how old I was when I came across this story, but I do know it was one of the very first times I realized how awesome infrastructure and engineering could be. I figured if it had such a big impact on me, that it's a story worth retelling, especially because there's a recent update at the end. Maybe it will inspire others to be more interested and engaged in their constructed environments like it did for me, which is basically my entire goal with these videos. I'm Grady, and this is Practical Engineering. In today's episode, we're discussing the Scattergood Olympic underground transmission line. How do you get electricity from where it's generated to where it's used? That's the job of high voltage transmission lines. Electrical power is related to the product of voltage and current in a transmission line. If you increase the voltage of electricity, you need less current to deliver the same amount of power. So that's exactly what we do. Transformers at power plants boost the voltage before sending electricity on its way, usually in 3 separate lines called phases, reducing the current and thus minimizing energy wasted from the resistance of conductors. High voltages make electrical transmission more efficient, but they create a new set of challenges. High voltage electricity is not only extremely dangerous, but it also tends to arc through the air, which is not a great insulator to the other phases or grounded objects. The conventional solution is to string these lines overhead on towers. This keeps them high enough to avoid contact with trees and human activities, but the towers serve a second purpose. They keep enough distance between each line so that electrical arcs can't form between them. Unfortunately, stringing high voltage lines overhead isn't always feasible or popular with the local residents, especially in dense urban areas. That was true in the 1970s when engineers in LA were deciding how to expand their transmission system and deliver power from the Scattergood power plant to the Olympic substation near Santa Monica. So they tried something that was relatively new and innovative for the time. They ran the line underground. 3 230 kilovolt lines, one for each phase, would deliver enormous amounts of electricity over the approximately 10-mile or 16-kilometer distance in West Los Angeles, powering hundreds of thousands of homes and businesses. However, putting high-voltage lines below the ground created a whole new set of challenges. When strung across towers, the conductors at this voltage each require around 10 feet or 3 meters of clearance to avoid arcs. The air is the insulator, doing the job of keeping electricity constrained within the conductors. So how do you take those 3 high voltage phases and cram them into a single small pipe running underground? Well, you need a better insulator than just air. One of the more popular options of the time was to use high pressure fluid-filled cables. This design starts with installation of a steel pipe below the ground with access vaults spaced along the way. Copper conductors are surrounded with many layers of paper insulation. Next, a protective layer of wire, called skid wire, is spiraled around each one to protect the paper from damage and allow for easy sliding along the pipe during installation. The conductors are pulled through the steel pipe using massive winches and then spliced together at each vault. Once the steel pipe is fully welded closed, it's slowly filled with a non-conductive oil known as liquid dielectric. This oil impregnates the paper insulation around each conductor to create a highly insulative layer that prevents arcs from forming, even with the conductors sitting mere inches apart from one another and the surrounding steel pipe. At the same time, the oil works as a heat sink to carry away heat generated from losses in the conductors. It is critical that the oil completely saturates the paper insulation and fills every nook and cranny within the pipe. Just like a hole in the plastic insulation around an extension cord, even a tiny bubble in the oil can create a place for arcs to form because of the extreme voltages. So the oil inside the pipe is pressurized, usually around 14 times normal atmospheric pressure or over 200 psi, to ensure that no bubbles can form. The rating of a transmission line, in other words, how much power it can deliver, is almost entirely based on temperature. All conductors, with rare exceptions, have some resistance to the flow of electric current, and that creates heat, which will eventually damage the conductors and insulation if it builds up. The more heat you can remove, the more power you can push through the line. That's a major benefit of pipe-type oil-filled cables. They're surrounded by a gigantic liquid heat sink that can be circulated to keep the temperature down and prevent hot spots from forming in the line. At each end of the transmission line is a plant filled with pumps and tanks to pressurize and often to circulate the dielectric oil in the pipe. This particular transmission line in LA circulated the oil in 6-hour cycles. At the end of each cycle, the pumps reverse to move the fluid in the opposite direction through the pipe. Some systems are different, but for the Scattergood line, this pumping is a slow process. You're not trying to pump all the fluid from one end of the line to the other, but rather simply get it to move a short distance along the line to average out the temperature and minimize the possibility of any single section from overheating. However, even at that slow speed, you can't just switch the flow direction in an instant. I have a video all about a phenomenon called fluid hammer, and you can check that out if you want to learn more after this. But I'll summarize here. Moving fluid has momentum, and rapidly changing its velocity can create dangerous spikes in pressure. Water hammer can be a problem in residential homes where taps or valves within washing machines close too quickly. You might hear a pipe knocking against the wall, or in worse cases, you might completely rupture a line. However, in large pipelines that can contain enormous volumes of fluid, reversing a pump can be the equivalent of slamming a freight train into a brick wall. To avoid spikes in pressure, which could damage equipment or rupture the pipe, the pumps at either end of the scattergood Olympic line would spend the last hour in the 6-hour cycle slowing the oil down, providing a smooth transition to flow in the opposite direction for the next cycle. Circulating the dielectric oil helps to keep the temperature within the pipe consistent along the line, but it can't control how that average temperature changes over time. Transmission lines don't deliver a constant current. Rather, the current depends on instantaneous electricity demand, which changes on a minute-by-minute basis depending on the devices and equipment being turned on or off. When demands fluctuate, the current in the transmission line changes, and so the amount of heat in the line increases or decreases accordingly. As you might know, many materials expand or contract with changes in temperature, and that's true for the copper conductors used in underground transmission lines. When these lines expand within the outer pipe, they often move and flex in a process called thermal mechanical bending, or TMB. If not carefully designed, these bends can become tighter than the minimum bending radius of the cable, exceeding the allowable stresses within the material. Over hundreds or thousands of cycles of TMB, the paper insulation around each conductor can begin to soften or tear, eventually leading to a dielectric breakdown. In other words, arcs and short circuits. TMB can also pull large diameter splices into narrower sections of the pipe, causing them to rub and abrade. That's what happened in 1989 to the scattergood Olympic line. But before the LA Department of Water and Power could repair the fault, first they had to find it. Locating a fault in an underground line is half art, half science, and there are many interesting types of equipment that can be used. They tried to use ground-penetrating radar along the line, but they couldn't identify the fault. They also tried time-domain reflectometry, a method of transmitting a waveform through the cable and measuring the reflection, but the results weren't conclusive. They also used a device called a thumper, which introduces impulses of high voltage into the cable. When this impulse reaches the fault, it causes an electrical arc, which can be heard as a thump above the ground, usually aided by a handheld detector with a microphone and digital filters. Going from one extreme in technology to the opposite, the crews used car batteries and voltmeters to take measurements of the conductor's resistance between tap points to precisely identify the location of the fault within Mr. McMahon's neighborhood. Once found, the challenge of repairing the faulty cable could begin. How do you fix an insulated conductor inside a steel pipe bathed in high-pressure oil? With liquid nitrogen, of course. Pumping all the oil out of the pipe before the repair wasn't feasible. It couldn't be stored and reused after the project because that process would introduce contaminants that would reduce the oil's insulative properties. They also couldn't dispose of it and replace it with new oil because the stuff's expensive and it would take a long time to get in such incredible quantity, potentially extending the very expensive downtime. Even more importantly, relieving the oil pressure from the rest of the pipe could allow gas bubbles to form inside the layers of paper insulation, potentially damaging them and creating new places for faults to form. The clever solution they used was to freeze the oil using liquid nitrogen, which is usually around -200°C or -320°F, creating solid plugs on either end of the section to be repaired. This allowed the rest of the pipe to remain under pressure. Losing these plugs would be a catastrophe, creating an eruption of high-pressure oil and spilling huge quantities of it into the environment. So the repair crew had liquid nitrogen companies on call across California as contingency to ensure that the oil could be kept frozen for the duration of the fix. Unfortunately, after taking x-rays along the entire length of the line, they realized that many of the cable splices were in danger of experiencing a similar fault due to thermomechanical bending. After coming to the conclusion that this wasn't going to be a quick fix, the Department of Water and Power decided to drain the entire line of oil and implement preventative measures while it was already down for repairs. Aluminum collars were installed at key locations along the pipe to constrain the thermal movement of the cable. This was done in a semi-clean environment with air handling and cleanliness requirements to prevent contaminants from finding their way into the pipe. After many months and tens of millions of dollars worth of downtime, the trucks and crews finally pulled out of Tom's neighborhood, and the underground transmission line was finally brought back online. There's an update to Tom's story that brings us to modern times. The scattergood Olympic line's troubles didn't end with the work in 1989. LA's routine testing showed that the insulation was continuing to degrade, and outages on the line were significantly disrupting the reliability of their transmission network across the city. In 2008, the Department of Water and Power began developing a replacement project, this time using newer cable insulated with polyethylene instead of high-pressure oil. After 10 years of planning, environmental permits, public meetings, design, and construction, the project was completed in 2018. The original transmission line is still in place and can be used as a backup if it's ever needed. As a part of my research for this story, I spoke to Tom on the phone. He told me that shortly after his write-up spread across the early internet, it was sent to a teletype machine within one of the offices of the LA Department of Water and Power, providing some higher up within the organization a neatly printed version that may or may not be still hanging on a wall somewhere downtown. Huge thanks to Tom for taking the time all those years ago to share his enthusiasm for large-scale infrastructure. Thanks to Jamie Zawinski for preserving the story on his blog. And thank you for watching. Let me know what you think. We talked about crane failures in a previous video, but you might be surprised to learn that things can still go wrong with heavy lifts, even when the crane is perfectly safe and sound. All cranes use a hook as a connection to the load, and yet few things we need to lift have an attachment that fits nicely over a gigantic steel hook. Rigging is the term used to describe all the steps we go through to attach a load to the crane so that it can be suspended and moved. And like all human endeavors, rigging is prone to error. Some of the most serious crane failures in history had nothing to do with the crane itself, but were actually a result of poor rigging. One of the worst construction accidents in U.S. history happened in New York in 2008, when a large metal component of a crane was improperly rigged. The overloaded slings failed, dropping the collar directly onto its attachment points to the building under construction, causing it to detach and collapse. 6 workers and 1 civilian were killed in the incident, and many more were seriously injured. There's a lot that can go wrong below the hook. So in this video, we're going to take a look at a few of the fundamentals in attaching and securing the load, and some of the hidden hazards that can pop up if not done properly and carefully. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about rigging. This video is sponsored by CuriosityStream and Nebula. More on that later. You probably heard the phrase that if your only tool's a hammer, every problem starts to look like a nail. It's a lighthearted way to warn about over-reliance on a familiar tool. But if you're a rigger whose job it is to secure loads to cranes for lifting, you really do just have one tool. You don't use a piece of old rope out of your pickup bed. You don't use a ratchet strap from the big box store down the road. And you definitely never use the crane's hoist line to wrap around a load. You have one option, a sling. Of course, slings come in a wide variety of sizes and types and materials, and you also have hardware like hooks and eyes and shackles and pulleys, but yeah, one main tool. And here's why. Slings have a rated capacity. That rating is a guarantee from the manufacturer. More importantly, it's a big responsibility taken off the shoulders of a rigger to know and trust that each connection to a crane or hoist can carry the right amount of load. So what do these tags mean? It's actually pretty straightforward. The tag shows how much weight you can put on the sling using 3 basic hitches. If your load has a hook or shackle, you can use the vertical hitch, one eye over the load and one eye over the hook of the crane or hoist. It's the most straightforward configuration for a sling and takes full advantage of its load capacity. If there is no attachment point on your load, you might instead use the basket hitch. In this configuration, the load is cradled by the sling and both eyes are on the hook. One benefit of the basket hitch is that it doubles the sling's load capacity since you have 2 legs holding instead of just one. But it only works if the load is balanced and easy to control, since it's only cradled from the bottom. If you need a snug grasp on the load, you might use the third basic option, a choker hitch, where the sling passes through one eye and attaches to the crane hook on the other. The choke point has extra stress when used in this configuration, so the load rating for a choker hitch is less than that of a vertical or basket hitch. If you're using a sling to lift something heavy and don't see a load rating tag, just stop. Every sling rated for rigging has to have a tag, whether it's a synthetic sling, a wire rope, or a chain. Even so, the vast majority of rigging failures happen because a sling was overloaded. You might be wondering why that's the case when the load rating is spelled out right there on the tag. But those 3 numbers hide quite a bit of complexity involved in rigging. And I have a few examples set up here in my garage to give you a glimpse into those intricacies. Even if you aren't planning to connect a 20-ton beam to a crawler crane anytime soon, this information applies to lifting just about anything. The first rigging pitfall is center of gravity. Not all loads are evenly distributed or equally balanced, and that could cause some serious issues if the rigging doesn't take it into account. For example, if you're using multiple slings to lift something, your first inclination might be to simply divide the total weight by the number of slings to estimate the load each one will carry. But if the slings aren't all attached at the same horizontal distance from the load's center of gravity, the total weight won't be distributed evenly between them. That may seem obvious, but many loads have been dropped because of misunderstandings with center of gravity. For just one example, loads often show up to a site in a crate where it's not quite so easy to see how the weight is distributed. In a worst-case scenario, incorrectly estimating the force on each sling may cause one or more to overload and fail. But even if the sling doesn't give out completely, it might stretch just enough to cause a load to shift. And if it shifts such that the center of gravity moves to the wrong side of the attachment points, there's a chance it will tip and fall. You can't push a rope after all, so slings only provide a resistance in one direction. So when lifting a load that isn't equally balanced between attachment locations, and especially for big lifts that use more than one crane, you have to calculate the load share between the slings and make sure that each one can handle its portion. The formula is super simple as long as you know the center of gravity. And if there's a chance a load could slide if one sling stretches more than the others, it's got to be secured before the lift. The next potential rigging pitfall is the sling angle. Let me show you an example. Say you have a balanced load and you need 2 slings to attach it to a crane, but your slings are kind of short. So when you get everything hooked up, the connections make a 30-degree angle from the horizontal. Is each sling carrying half the weight of the load? Would I even be asking if the answer was yes? In fact, at a 30-degree angle, each sling is subject to double the force that it would otherwise feel if it were perfectly vertical from the load. Why is this? Slings can only pull in one direction. For simplicity, we sometimes divide the force in the sling into its vertical and horizontal components. If the sling is perfectly vertical, it has no horizontal part. But as the angle of the sling changes, the horizontal component becomes a greater and greater proportion of its total load. This may not need to be said, but we don't need a horizontal force to lift something. We need a vertical one. In fact, the horizontal force isn't just unnecessary, but it also has to be canceled out by an equal and opposite force in the other sling. So the shallower the angle of the sling, the harder you have to pull on it to get enough vertical force to lift the load. Watch the spring scale as I change the angle of the slings holding this steel bar. It's a little hard to read on camera, but it's still clear what's happening. When the slings are vertical, each one holds half the weight, in this case about 800 grams each. But as I bring the tops of the slings toward the center, like they would be if attached to a single crane hook, you can see the plunger of the scale descending. When the tops of the slings touch, the scale reads about 1,200 grams, an increase of about 50%. I'm sure you can imagine what would happen if you incorrectly divided the weight of the load by 2 and assume that that would be the force in the slings. You'd be underestimating by quite a lot. So when using slings that aren't vertical, you have to apply a reduction in capacity based on the angle. Again, the formula is simple, but you have to know how and when to use it. Shallow horizontal angles aren't just an issue with sling tension, though. These horizontal components of force that I mentioned have another disadvantage related to the third and final rigging pitfall I want to discuss: abrasion. As I said, slings can be made from a few materials, including chain and wire rope, but one of the most common materials is woven synthetic fibers, like nylon and polyester. These synthetic slings have a lot of advantages. They're lightweight and easy to move around. They don't create sparks that can be dangerous in industrial environments, and they're soft, so they won't scrape or damage whatever they're connected to. But they have disadvantages too, mainly that synthetic slings are more susceptible to abrasion. Those horizontal forces I mentioned earlier don't just increase the sling tension beyond the weight of the load, they can also cause a sling to slide. Obviously, that's an issue if they slide so far the load falls, but even if they don't, the friction with the load can lead to abrasion and even failure of the sling. Synthetic materials are much easier to cut than wire rope or chain, so they have to be protected from sharp edges, corners, and burrs. Synthetic fibers can also melt. You might not think that a little sliding would generate much heat, but consider that friction is a function of the contact pressure between the two surfaces. These slings are pretty small compared to the weight they carry, meaning the pressure they exert can be enormous. Watch what happens on the thermal camera when I pull down on this loop as it slides along the pipe. Even a small amount of sliding under so much pressure can create enough heat to melt the fibers. One way to avoid the possibility of sliding is to use a spreader bar, a device that helps distribute the singular lifting force of the hook among attachment points that can be further apart. This kind of device lets you reduce the angle of your slings, giving them more capacity and reducing the possibility of them sliding and abrading. I've been referring to you a lot in this video, putting you in the shoes of a rigger learning the rope, but I just want to clarify that this video is not for training. If this is your first exposure to the topic, I hope you'll agree that you're not ready. Rigging is a vital but dangerous job, so if you're going to be involved in any heavy lifts, there's a lot more to learn than my examples in this video. Finally, if you enjoyed this one, check out the companion video about crane fins and what can go wrong above the hook. Hey, the fact that you stuck around to the end of this video means that you're pretty thoughtful about the kind of content you spend your time enjoying. In other words, you probably prefer learning new things about the world more than run-of-the-mill television programs. You probably also don't enjoy watching ads like this one, which is great because Nebula doesn't have it. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Wendover Productions, and a bunch of others, including me. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. My videos go live there the day before they publish here with no ads or sponsorship. And we're super excited to be partnered with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and all those monthly subscriptions can be tough to keep track of. That's why this bundle is such an awesome deal. CuriosityStream's taking 26% off an annual plan. That makes it only $15 for an entire year of access to thousands of thought-provoking documentaries on CuriosityStream and everything on Nebula as well. You can watch awesome big-budget content on CuriosityStream. I love nature documentaries, and this special called Wild Galapagos, narrated by Mike Rowe, is one of my favorites. Or watch Tom Scott pit other YouTubers against each other in his Nebula exclusive game show, Money. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a great deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. On June 24th, 2021, a portion of Champlain Tower South, a 12-story condominium in Surfside, Florida, near Miami Beach, collapsed around 1:30 a.m. It was one of the most deadly structural collapses in U.S. history, with nearly 100 fatalities. Forensic investigations of the event will likely take years to complete, but there's a lot we already know about the collapse. In this video, I want to summarize the events of this unthinkable tragedy, talk about a few of the structural engineering issues that may have played a part, and finally, explain the process of forensic structural investigations and what might result from learning the technical cause of this catastrophe. I'm Grady, and this is Practical Engineering. Today's video is on the collapse of the Champlain Towers South building. Champlain Towers South was built in 1981, along with a nearly identical north structure just up the street. The 12-story oceanfront tower was constructed of steel-reinforced concrete in the small Miami suburb of Surfside. The building sat atop an underground parking garage that extended below the adjacent common area that residents called the pool deck. The building had 136 condominium units. Unlike an apartment property with a single owner, Champlain Towers South was collectively maintained by those 136 condo owners through an association with board members. In the early hours of June 24th, we know that there was a failure of the pool deck adjacent to the building. Tourists at a nearby hotel were swimming when they heard a crash. They walked over to the Champlain Towers to see that part of the pool deck had collapsed into the parking garage below. About 7 minutes later, the building began to fall. A security camera nearby caught the entire event on camera. The building collapsed in 3 sections. First, a south portion of the building, immediately followed by a north portion, and finally the east section. The entire western half of the building remained standing. The search and rescue operation started immediately to get residents out of the damaged building and the rubble of the demolished area. Crews worked 24/7 to sift through debris for survivors. The western part of the structure, which didn't collapse, posed a hazard to the rescue and recovery crews, especially with the threat of Tropical Storm Elsa potentially bringing high winds to the area. Town officials made the difficult decision to demolish the remaining part of the building on July 4th to safeguard the crews and avoid the possibility of it falling onto the existing search and rescue zone. As of the recording of this video, 97 people have been confirmed deceased. There were 126 people who were in the building during the partial collapse and survived. Of course, the most critical question of the collapse is why it happened. Unfortunately, it's a difficult one to answer. The town of Surfside put all their records and correspondence about the building online in the interest of public transparency. It was in the process of being recertified, a requirement in Miami-Dade County for all buildings when they reach 40 years in age and every 10 years afterwards. That process starts with a detailed inspection by a structural engineer. For Champlain Towers South, the inspection was performed in 2018. The findings of that structural inspection have been the focus of most of the early conjecture about the cause of the building's collapse. Among the items of concern identified during the inspection, one of the most important was the pool deck. The large concrete slab adjacent to the building also served as a ceiling to the underground parking garage. The inspection report noted major structural damage to this concrete slab, mainly as a result of poor drainage and failed waterproofing. The issue was that rainwater on the pool deck could filter through the pavers above the concrete slab, and then it had nowhere to go. So instead of flowing along a properly sloped slab to drains, it simply pooled above the slab like a bathtub. Unlike a bathtub, this system wasn't watertight. Runoff was leaking into the concrete below through joints, cracks, and into the pores of the slab itself. This wasn't a surprise. It was a well-known problem at the condominium, and there were even plastic gutters installed in various locations along the ceiling of the parking garage to divert these leaks away from cars and walkways. But the water wasn't just a nuisance to residents. It was also slowly deteriorating the reinforced concrete structure itself. I produced a series of videos about concrete and steel reinforcement, so I'll link that playlist below if you want more details. Reinforced concrete is an extraordinarily versatile building material because it's strong, durable, relatively inexpensive, and can be cast into just about any shape. For better or worse, it's one of the most ubiquitous building materials of the modern world. But like all building materials, it has its weaknesses and is subject to deterioration over time. One of the most prevalent of those weaknesses is the corrosion of steel reinforcement. Embedded steel is usually safeguarded against corrosion by the impermeable covering of concrete and its alkalinity, which creates a protective oxide layer around the steel. However, over time, water flowing through concrete can leach certain constituents out, making the concrete more porous and less alkaline. That makes the steel more subject to corrosion. This is especially true in coastal areas where salt-laden air from the sea can carry chloride ions toward inland structures. When these chloride ions saturate the concrete, they accelerate degradation of the protective oxide coating around the steel. Corrosion doesn't just weaken steel, it also causes it to expand in volume, creating pressure within a reinforced concrete structure. Eventually, the corrosion can reach a point where the pressure is too much. The surrounding concrete breaks away, leading to cracks, spalls, which are small areas of flaked off concrete, or delamination, where parts of the concrete along mats of reinforcement steel are completely separated. Once the steel is no longer surrounded and protected by concrete, the corrosion can progress much more quickly and may eventually lead to a structural failure. The engineering and construction industries have made huge improvements in the design and construction of concrete structures in the past 30 years, thanks in large part to the Federal Highway Administration and the International Concrete Repair Institute. However, Champlain Tower South was designed and built before modern building codes included best practices for concrete structures in harsh coastal environments. The engineer who inspected the tower pointed out the problem with the pool deck in strong language, stating that failure to replace the waterproofing in the near future will cause the extent of the concrete deterioration to expand exponentially. Keeping water, especially salty water, away from reinforced concrete is vital. If inadequate waterproofing turns out to be the cause of the failure, it won't have been the first time. In 2012, the roof of the Algo Centre Mall in Elliott Lake, Ontario collapsed, killing 2 people. The cause of the collapse was corrosion of the building's steel framework, instigated by leaks through the improperly waterproofed rooftop parking deck. The prevailing theories about the Champlain Tower collapse from most of the current investigative journalism centers around the pool deck as a trigger or at least a major factor in the building's demise, especially because the pool deck failure preceded the collapse. However, there's less certainty about what role in the collapse the failure of the deck slab had, since it doesn't provide any support to the building itself. What we see in the surveillance video would have required failure of one or more columns below the structure. One possibility is that the deck slab punched through intermediate columns such that it was hanging like a sheet from the columns below the building, sometimes called catenary action. The forces from the hanging slab could have loaded the columns below the building in a way they weren't designed to withstand, causing them to buckle. Thanks to Mike Bell for sharing his animation of how that might have happened. However, the exact mechanism in which those columns failed is still unknown. Tragedies like this are usually the result of many separate factors coinciding, and there are several circumstances that may have contributed to the collapse. A research team studying changes in land and sea levels in the area measured some unusual settlements of a few millimeters per year in the area of this building. Although many areas experience significant long-term and large-scale settlement, also called subsidence, it's possible that if different parts of the site were settling at different rates, the tower's foundation would experience additional structural stresses. Also, some photos of the rubble appear to show less reinforcing steel than was called for in the original design drawing, particularly at the column-to-slab connection. There were also regular intrusions of groundwater into the parking garage, the recent construction of an adjacent high-rise building, and ongoing construction to the building's roof to consider. All of these factors and many more will be reviewed by the forensics teams who are already investigating the cause of the failure. Many of these investigators have been on site during the recovery and cleanup operation to make sure that rubble and debris that may offer clues into the cause of the collapse are documented and preserved. Major parts of the building are being preserved as evidence, so rubble was sorted on site and taken to a nearby warehouse for cataloging. It's important to keep in mind that each one of these forensics teams is trying to answer a slightly different question. The town of Surfside hired its own investigator, Alan Kilsheimer to begin looking into the collapse. Surfside has a number of high-rise condos under their purview, so presumably they felt the need to conduct their own investigation for the safety of their citizens. Another critical service that Mr. Kilsheimer is providing is to satisfy the public's need for information, which is why you see him doing interviews and talking on news shows on behalf of the town of Surfside. At the federal level, the National Institute of Standards and Technology announced that they would launch a full investigation into the collapse. Formerly called the Bureau of Standards, NIST does a lot of research and science around measurements, materials, manufacturing, and engineering. Since 2002, they also have a federal mandate to investigate the cause of failure when a building collapse results in substantial loss of life. Their investigation will likely be the most thorough, including laboratory testing of steel, concrete, soil specimens, and structural modeling. During the recovery operation, they were on site with sophisticated equipment to take detailed records as rubble was hauled away and performing non-destructive testing to locate reinforcing steel and determine properties of the concrete members. They will also review all the reports and photographs from professionals, survivors, and witnesses of the event. Their final report will probably take a year or two to complete. The primary purpose of that investigation will not be to find fault, but rather to make recommendations for improvements to the building code and industry practices in the fields of structural engineering and construction. Insurance companies, victims, owners, and designers will also be involved in lawsuits to try and establish who's at fault in this tragedy and potentially award damages as a result. Those legal teams will hire their own experts who will be investigating the details of the collapse. However, their focus will be toward establishing professional and organizational culpability more than the technical causes of the failure. Finally, the county called a grand jury to examine the building's collapse. A grand jury is essentially a group of citizens used to administer justice in various forms. Most commonly, grand juries are used as a step between accusing a person of a crime and trying them in court. However, they can also conduct their own investigations as representatives of their community. If the grand jury finds serious negligence or wrongdoing, there may even be criminal investigations that result from the collapse. Was it a poor design, a mistake made during construction, lack of proper maintenance, or a combination of all three? That's the question the forensic teams will be trying to answer. And just to temper expectations a little, they may not find a final and clear-cut cause of the collapse. The difficulty of forensic engineering is that you're trying to piece together a sequence of events from small and disparate puzzle pieces. Unfortunately, in this case where the failure likely began at the bottom of the structure, most of those puzzle pieces were buried in a pile of rubble. I want to emphasize that this type of event is extremely rare. The damage to the Champlain Tower South pool deck shown in the 2018 inspection report is severe, but it was not an indication of an imminent collapse of the adjacent building by itself. Although we don't know exactly how much things worsened between then and the collapse, I think you'd be hard-pressed to find a structural engineer who would evacuate a building based only on the level of deterioration shown in that report. Nearly all buildings, even with moderate maintenance, will last much longer than 40 years without fear of something catastrophic. Modern building codes are designed to ensure that our structures are engineered with redundancies and factors of safety for exactly this reason. My heart goes out to the victims of this unspeakable tragedy. I hope that investigators can get to the bottom of the collapse and its cause so that something like this never happens again. Cranes are dangerous. Anytime something goes up, there's a chance it might fall down. Keep that in mind next time you climb a ladder. But lifting stuff up and getting it back down safely is pretty much a crane's only job. So why do so many of them fall down? Let's walk through some of the biggest crane disasters in modern history to try and understand. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about crane failures. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. Cranes are the backbone of just about every construction project. All construction can be boiled down to material handling, taking delivery, storing, moving, and placing all the pieces and parts of a project. Of course, you can do a lot with your own sweat and muscles, and there are even tools to provide a mechanical advantage, allowing one person to lift a lot. But anyone working in the trades will tell you there are plenty of jobs only a crane can accomplish. Heavy equipment amplifies the amount of work that can be done. That's so true with cranes that the question at most construction sites is not if a crane will be mobilized, but when and what type. Because they're so pervasive and they do such a dangerous job of lifting massive objects high into the air, occasionally cranes fail. In this video, I want to walk through some of the reasons these failures occur using historical accidents as case studies. I've got some demos set up in my garage with toy cranes, but these accidents are no joke. Crane collapses lead to property damage, injuries, and fatalities every year, but they're almost always preventable. So I'll do my best to explain what could have been done differently for the cases described. By the way, this is part 1 of a series on cranes. A future video will cover rigging and the things that can go wrong between the hook and the load. The first reason cranes fail is improper assembly or disassembly. Most cranes on construction sites are temporary. They're not staying when the job is done. That means they either arrived under their own power, called mobile cranes, or they were shipped on trucks and assembled on site, a process that can take days or weeks depending on the size of the machine. A crane can be extremely vulnerable during assembly or disassembly since all the components aren't fully bolted together. A recent collapse in Seattle happened when a team disassembling a tower crane prematurely removed the pins holding sections of the tower together. Presumably, this was done to speed up disassembly. However, when winds picked up that day, major components of the crane were completely disconnected, being held together just by gravity and loose sliding connections between the members. It didn't take long for the crane to collapse, killing 4 people and injuring many more. In most cases, these cranes are expertly engineered for worst-case conditions, but the manufacturers are rarely the ones installing them on site, so they provide detailed manuals for the crews assembling and disassembling them. Unfortunately, those manuals aren't always followed to the letter. One of the worst crane disasters in modern history happened in 2008 in New York City. Crews were working to attach a tower crane to a building when a major component of the attachment hardware, a heavy steel collar, suddenly fell. As it fell, it crashed into the attachment points below, breaking them from the building and allowing the whole crane to overturn. The cause of the accident was simple. The crew assembling the crane didn't follow the manual. Specifically, they didn't attach that collar to the crane according to the manufacturer's guidelines while it was bolted together and attached to the building. 7 people died as a result. Another collapse in Battersea, England in 2006 also happened because the operator was using the wrong manual to assemble a crane. Instead of an 8-ton counterweight, they used 12 tons, putting the crane way out of balance. Eventually, the bolts holding the slew ring failed and the entire boom broke free, killing the operator and another person who was just fixing his car on the street nearby. Once a crane is set up, the challenges in keeping it that way aren't over. Many crane failures happen during everyday operations, and one of the biggest causes is overloading. Every crane has limitations in how much weight it can handle, but it's not as simple as something like a bridge that has a single load limit. Not only can most cranes have a wide variety of different configurations, like different counterweights, jib lengths, and boom sizes, they also, by the very nature of their job, move. They slew, luff, telescope, traverse, boom up or down, etc. And more importantly, their load limitations depend on these movements. Every crane has a tipping line. That's the line at which the machine will tip if overloaded. Any increase in weight outside the tipping line destabilizes the crane if not balanced on the other side. The further away the load is from the tipping line, the greater the moment or torque on the crane. This is easy to demonstrate with my model. Using a spring scale, I can estimate the load required to tip the crane at different distances from the tipping line. Torque is the product of length and force. As the distance from the crane goes up, the force required to tip it over goes down proportionally. Cranes have a few tools to keep the load in balance. One is counterweights. These weights oppose the torque by balancing it on the opposite side of the crane. Another tool is outriggers. When there's enough room to use them, these arms extend the tipping line, bringing it closer to the load and thus reducing the length of the lever. The crane can hold several hundred grams with the outriggers extended, but it can barely even hold up the spring scale without them. All those factors add up to a lot more than any operator can be expected to keep track of, which is why cranes have load charts. Reading these charts is pretty simple as long as you're looking at the one that matches the configuration of your crane. Look at the furthest radius your hook will be from the center line of the crane during the lift, and you'll see the maximum allowable load the crane can handle. Of course, most modern cranes have sensors and electronics that can help an operator keep track of this on the fly. Load moment indicators tell the crane operator when they're getting close to the maximum. Many cranes will even lock out specific movements to prevent the crane from tipping or sustaining damage from overloading. That doesn't mean it doesn't happen, though. In 2016 in Manhattan, a crawler crane fell over as it was being laid down due to high winds. The boom and jib of this particular crane could be set down on the ground if things got too windy. But even with nothing on the hook, the load chart doesn't allow the boom to be lowered below 75 degrees. Unfortunately, the operator dropped the boom below this level and the crane fell, killing one person and injuring several others. Even if the crane can handle the load and do it stably, that weight doesn't just stop at the base. It has to be transferred to the ground, and surprisingly, sometimes the ground can fail. The geotechnical engineers call this a vertical deformation, but you can just say the ground moved when it wasn't supposed to. And this can happen in a couple of ways. The first is settlement. That's when soil particles compress together when subjected to a load. It's usually a slow process, but it can create issues at a construction site over time. Settlement can be solved in one of two ways. Sometimes compacting the subgrade before using it as a foundation is enough to make sure that it won't compress further over time. For clay soils that are difficult to compact, it's usually best to replace the top layer with something more stable, like crushed rock. The other type of vertical deformation is called a bearing capacity failure. In this case, the soil particles actually slide against each other in a shearing motion. These dowels represent soil particles, and you can see what happens if the earth can't withstand a vertical load. The particles below the base get forced downward, while the adjacent particles bulge up on the sides. Here's an example using a tower crane. With the hook at the end of the boom, the crane can hold 150 grams without tipping on a stable surface. But when set on top of loose sand, things aren't quite so static. The soil isn't able to support the 2 feet in compression. Instead, it gives way, allowing the crane to topple. In 2012, this crane fell over while lifting a part of a ship in Vietnam. The cause is obvious. The ground wasn't strong enough to withstand the load. This accident killed 5 people. Geotechnical engineers can estimate the bearing capacity using simple tests, so there's no good reason this should ever happen. If the ground can't handle what's required for the crane, the solution is simple. Distribute the load over a larger area. This is often done using steel plates or wooden constructions called crane mats. Water also affects bearing capacity. The strength of the soil is primarily a function of friction between soil particles. If water gets into the space between those particles, it pushes them away from each other, reducing the friction and weakening the soil. If you've ever stepped in the mud, you have some intuition about this. In 2013, a massive crane helping with the construction on the Brazil World Cup Stadium collapsed while lifting a roof section into place. The cause of the collapse was a bearing capacity failure of the soil beneath the crane, exacerbated by several days of heavy rainfall. So, keeping the site well drained from water is essential. And again, replacing crummy soil with a stable, free-draining material is usually best practice. The final cause of crane collapses that I want to discuss is wind, or rather, neglecting the power of the wind to overload. In 2019, a severe thunderstorm led to the collapse of a tower crane in Dallas, killing one person and injuring several others. The fault for the accident is still being litigated, but it brings up one thing many don't realize. Most tower cranes are designed to withstand very high winds, but only under certain conditions. When winds are high, operators have to disengage the clutch so the crane can freely point into the wind. This is called weather vaning. If the boom is locked, it can end up broadside to the wind, significantly increasing the forces on the crane. In the video of the 2019 collapse, you can see 2 cranes pointing in different directions, and only one of them failed. That suggests that an operator may have forgotten to secure the crane properly, or the crane malfunctioned and couldn't weather vane into the wind. In September 2017, 3 cranes at separate construction sites in Florida all collapsed on the same day due to winds from Hurricane Irma. All 3 cranes were the same make and model, and they were all secured to weather vane as required. Luckily, no one was injured at any of the sites since they were shut down due to weather. The winds during the storm were more than 125 miles per hour or 200 kilometers per hour in some places. That's far more than the maximum design wind speed for the cranes, which was 95 miles per hour or about 150 kilometers per hour. As the saying goes, there's always a bigger storm. And in this case, Hurricane Irma just delivered winds that were well above the requirements and codes that cranes are required to meet. However, since only this single type of crane failed during the storm, investigators recommended some changes to the design that may make them safer in the future. Situations like what happened in Florida are the exception, not the rule though. As I mentioned, nearly every crane accident is easily preventable. In 1999, one of the largest cranes in the world collapsed during construction of Miller Park in Milwaukee, now called American Family Field. The crane was lifting a 500-ton roof section of the stadium at 97% of its rated capacity. But it wasn't just the weight of the structural members bearing on the hook. Steel assemblies can appear pretty slender, but that doesn't mean they can't catch the wind. Watch what happens when I put my leaf blower on this steel truss. It's a little hard to see the spring scale, but a little bit of wind goes a long way. By my estimation, the wind is adding about 15% to the load on the hook. It's more than the margin of error when you're operating at maximum capacity, and that doesn't even consider the huge horizontal loads affecting the crane. These machines are rarely capable of withstanding much force in any direction other than straight down, so their load charts generally disallow operation when winds are high. On that fateful day in 1999, the crane operator neglected to include the additional force from wind loading when assessing the crane's capacity, and so it ended up overloaded. A safety inspector happened to catch the entire collapse on camera. 3 construction workers were killed during this incident, and a sculpture of them still stands at the stadium in their memory. As you may have noticed, there are technical reasons that cranes fall over, but there are also underlying human factors as well. That's why it's best practice to create a lift plan anytime a crane is used. That involves taking the opportunity before the load is in the air to consider all aspects of the lift and what could go wrong. Weight, dimensions, the center of gravity and lifting points of the load, the path it will travel during the lift, the capabilities of the crane, outside factors like wind, and communications during the whole process. For complicated lifts, these plans can take days or weeks to prepare with detailed engineering reviews to ensure that nothing goes wrong once the load is on the hook. It's time for everyone's favorite segment of watching me try to cook while my wife tries to capture that on video.
Yeah, just mod that up. Yeah, that looks.
With a helper who, let's be honest, isn't really that helpful. Not to mention our currently broken microwave, dinner time in our house is a little chaotic. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night. We are indecisive, meaning neither of us likes to be the one to decide what's for dinner. It's nice to have HelloFresh curating delicious and healthy recipes so we don't have to.
You want sound effect or no sound effect? Okay.
The pre-portioned ingredients mean there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner ready quickly when we haven't had time for planning, prep, and shopping. Not that we're easily distracted or anything.
No.
Go try it yourself at HelloFresh.com and use code PRACTICAL14 to get 14 free meals, including free shipping.
You're practicing on yours first, right? Good.
Supporting our sponsors helps support this channel. That's HelloFresh.com and use code PRACTICAL14. Thanks, HelloFresh, and thank you for watching. Let me know what you think. Our secret telescope, one of the using the Arecibo telescope. The same way we observe visible light from celestial objects using our eyes and optical telescopes, we can also take advantage of other parts of the electromagnetic spectrum in astronomy. Most of the gamma rays, X-rays, ultraviolet, and infrared portions of the spectrum are blocked out by the atmosphere, but long-wave radio waves are not. A radio telescope is basically an antenna that can tune in to some frequencies of electromagnetic radiation that emanate from celestial objects. These radio waves can be quite faint, complicating the task of separating them from the background noise. You essentially have two options to get high-quality radio astronomy data: more time or more space. The longer you focus on the object, the more resolution you get. But there's only so much time. To speed up observations, you can also gather radio waves from a larger area and focus on the half-kilometer fast. It could transmit them as well, allowing Arecibo to work as a celestial radar. It could send out radio signals including the Nobel Prize-winning observation of binary pulsars, providing the first evidence of gravitational waves. The telescope's dish was constructed inside an enormous circular cylinder. Although it looked solid from a distance, the reflector was a series of aluminum panels carefully suspended on steel cables. Because the dish was faced to the Earth, it was constrained to the point of whatever part of the sky happened to be overhead. The designers of Arecibo had a pretty clever solution to the problem. Rather than using a parabolic shape that would focus everything to a single point, they chose a spherical curve. Spherical reflectors don't perfectly focus all the incoming rays. That might sound like a bad thing, since you want to gather and focus as much signal as possible across the entire dish. The beauty of a spherical reflector is that by changing the position at which you measure the reflected waves above the dish, you're measuring those waves from different parts of the sky. You can essentially steer the telescope by choosing where to receive radio waves above the dish, allowing you to focus on various objects and track them as the Earth rotates. Focusing those waves to a narrow area above the dish doesn't do much good unless you have a receiver up there to collect and measure them. The Arecibo telescope was designed with a triangular platform suspended by steel cables above the dish to support the various instruments used to gather radio signals. To keep the platform aloft, 3 reinforced concrete towers, named for their positions on a clock, 4, 8, and 12, supported each group of cables. There were originally 4 cables for each corner of the platform, 3 inches or 8 centimeters in diameter. Big cables. Additional cables, called backstays, were connected to anchorages behind each tower to balance the horizontal forces, similar to the way suspension bridges work with their towers and abutment anchorages. Initially, the telescope used line beams, elongated receivers that could gather signals within the focal line of the spherical dish, but they could only measure signals within a narrow band, so line beams would have to be swapped to change the frequency of the telescope. Upgrades in 1997 included the addition of the Gregorian dome. They used 2 additional This dome allowed telescope operators to observe a much wider range of radio frequencies. But this Gregorian dome didn't just add capabilities, it also added weight, lots of weight. About 50% 50% of the original platform. All of this extra load required some more support, so 2 auxiliary cables from the platform to each tower were added, plus more backstays to balance the load. The dome was far more sensitive to tiny movements. You can imagine the stiffness and rigidity of a gigantic wind-catching dome suspended in the air by narrow steel cables, analyzing the structural arrangements. To compensate, 3 tie-down cables were added, one for each corner of the platform, increasing the forces even further. A laser ranging system can communicate with hydraulic jacks to carefully adjust the tension in these tie-downs and keep the platform perfectly stable within the precision of a millimeter. The telescope's last few years were pretty rough. The 2017 Atlantic hurricane season sent 2 massive storms, Irma and Maria, across Puerto Rico. Maria was one of the strongest storms ever to hit the island and caused nearly 3,000 fatalities and close to $100 billion in damage. Arecibo wasn't spared from that devastation. It suffered a broken line feed that fell from the instrument platform and crashed through the dish, among other damages. More consequential than hurricanes, though, Arecibo was slowly losing its funding. The National Science Foundation had been trying for years to divert Arecibo funds to newer projects. In 2018, the University of Central Florida stepped up to take over the management and funding of this observatory, not knowing what was soon to come. Only a few years later, in August 2020, one of the newer auxiliary cables on Tower 4 broke free from its socket unexpectedly in the middle of the night. As the cable failed, it crashed through the reflector dish, tearing the gash through the aluminum panels. These sockets, called spelter sockets, used to attach the cables to the tower, are a common way to terminate wire ropes and cables, but they have to be installed correctly. You have to broom the end of the cable, making sure that every strand is separated from the others, clean them meticulously, then carefully pour molten zinc into the socket to create a permanent wedge that only gets tighter with more tension. If done properly, the termination should be stronger than the cable itself. In other words, there's no good reason that cable should ever pull out of a spelter socket, and yet this was not the first incident of cables slipping in their sockets at Arecibo. Maintenance staff at the observatory had been concerned about the problem for years. This failure was the beginning of the end of the telescope, though we didn't know it yet. The damage from the failed cable was significant, but the engineers brought in to assess the structure believed that it could be repaired. The suspended platform was designed with some redundancy, so losing a single cable wasn't necessarily catastrophic. Managers put a temporary stop to the science of the facility while a remediation project could be installed, but it had to be designed first. As a first step, engineers developed a structural computer model of the platform and towers to evaluate options for repair. One nice aspect of cable-supported structures is that you can estimate the tension in each one just by looking at it. All cables sag under their own weight, following a curve called a catenary. The more tension in the cable, the tauter it becomes, and so the less it sags. If you know the weight of the cable, you can use the catenary equation with the measured sag distance to estimate cable force fairly accurately. A sag survey was conducted at Arecibo using lasers, and this is how the structural model was calibrated. To make sure the model could predict how changes in forces would affect the structure, the engineers performed some pretty clever validation as well. Since they had measurements of the instrument platform before and after the first cable failed, they could remove that cable in the model and compare the predicted behavior of the platform to what actually happened. When the first cable failed, that corner of the platform dropped by 2.5 feet, or about a meter, and the model was able to predict this within a couple of inches. While all this design was taking place, further trouble was just around the corner. In November, only 3 months after the first cable broke at Tower 4, a second one failed. This time it was one of the original cables installed in the 1960s. It didn't pull from its socket, but simply broke. And it broke at a force well below what it should have been able to handle. About 62% of its rated strength, to be precise. The fallen cable again damaged parts of the telescope, and again the platform remained standing. However, optimism about the structure was quickly declining. The question went from how do we fix the telescope to can we fix the telescope? And there were differing opinions. The engineers used the structural model to evaluate options that could relieve the tension in the remaining cables and reduce the possibility of a complete failure. They could cut the broken cables, since they're pretty heavy and not doing anything useful anymore. They could move the Gregorian dome so the other towers were holding more of its weight. They could loosen the backstays, causing the towers to lean inward by 18 inches or half a meter. And of course, they could add some temporary cables at Tower 4 to take up some of the weight. All of these options showed reductions in the forces carried by the remaining cables. But the problem was figuring out how to do the work safely. At this point, they had two failures, both well below the specified braking strength of the cables. Not only had the telescope lost its structural redundancy, but the engineers also didn't trust the strength of the remaining cables, and for good reason. Crews couldn't access the site due to the risk of another cable failing, but nearly all the options to relieve the load on the cables would require having personnel on the platform and towers. One of the engineering firms working on the problem suggested some last-ditch efforts to save the structure. After that, they could perform proof tests remotely using the tie-down jacks to check if the remaining cables had at least 10% extra strength. If the engineers could gain some confidence in the strength of the remaining cables, crews might be able to enter the site and implement further measures to save the structure. However, no one could get comfortable with the risks of the helicopter work or proof testing the already distressed cables. It's a tough thing to say when such an important and iconic structure is still standing that there's no path forward to repair them. This quote from the engineer tells the whole story. It is unlikely any of these methods will yield sufficient reductions without placing crews in jeopardy. Although it saddens us to make this recommendation, we believe the structure should be demolished in a controlled way as soon as pragmatically possible. They wouldn't get the chance, though. On the morning of December 1st, a third cable at Tower 4 broke, starting a chain of events that would quickly collapse the structure. Amazingly, one of the observatory staff was flying a drone at the top of the tower when it happened, capturing this incredible footage of the event. It happens almost instantly. Two of the main cables are already clearly in distress when the video starts. All the chipped paint is from individual strands of the cable failing. Observatory staff could hear these breaks and knew what was likely imminent, which is why the drone was up there in the first place. The third cable snaps, and the remaining cables, forced to bear the additional load, quickly follow. The drone turns around to reveal the platform crashing into the side of the dish. The observatory also had a GoPro set up in the control room that captured the failure. You can see the cables let go from Tower 4, the platform swinging downward, the supporting cables crashing through the suspended catwalk, and the top section of Tower 4 breaking off from the unbalanced force of the backstays. All three towers suffered failures, major portions of the dish were destroyed, and the platform and instruments it supported were a complete loss. Several buildings, including the visitor center, were damaged by falling debris. Thankfully, even though there were people on site during the collapse, the engineers had established safe zones away from the structure, and no one was injured. Several forensic investigations are still underway to examine the causes of these failed cables. Those results could be years away, so we don't yet know for certain why the first two cables gave way when they should have had more than enough strength to carry the load. Engineers involved during the event suggested the first cable to fail likely was not fabricated correctly. Whether the spelter sockets were installed in the field or a shop, there are a lot of details required to do it properly, and it's certainly possible that something was missed. And once those sockets are installed, they are difficult to inspect. As for the second cable, the engineers suggested a likely failure mode to be corrosion of the steel. The cables were painted regularly and reportedly had a dehumidification system that could blow dry air between the strands, although those systems usually require an airtight sleeve around each cable. Even so, Arecibo sat nearly 60 years only a short distance from the northern coast of Puerto Rico, and exposure to that salty sea air could have accelerated the demise of the main cables. Another element worthy of scrutiny is the factor of safety used in the original design. This is the quotient of a structure's demands and its strength. The whole point of a factor of safety is to accommodate uncertainty. We predict the demands on a structure, we compare them to the strength, we recognize that there might be extra forces or less strength than expected for a variety of reasons outside our control, so we give our structures some margin. The Arecibo suspended platform cables were designed to have a factor of safety of 2, meaning they were twice as strong as the expected static loading from the platform. That might seem like a lot, but consider that elevator cables use a factor of safety of 11, and many bridges use safety factors above 3. In aerospace engineering, where weight is critical, they do tons of modeling and testing to build enough confidence in designs to get their factor of safeties down to around 1.5. Arecibo was a unique facility, unlike any other structure in the world. It didn't go through a rigorous structural testing program, and it was designed before computer modeling could be used to accurately characterize all the static and dynamic forces we could experience. I think it's worth considering whether the structure should have been designed with a little extra margin, especially considering the possible circumstances in which that margin would be required. A cable failure is a violent event. All the load the failed cable was carrying doesn't just redistribute itself to the other cables evenly and gently. The dynamic loads that occur as the structure shakes and vibrates can be significantly higher than the static loads. It wouldn't be surprising at all to find out that the peak stress in the remaining cables on Tower 4 actually did exceed their rated strength when that first and second cable broke, even if only for an instant. Despite the collapse, Arecibo Observatory is not closed, and science continues at the other facilities on site. As of this writing, crews are still working to clean up the debris from the collapse, and the National Science Foundation is holding workshops to discuss the future of the site. I hope eventually that they can replace the telescope with an instrument as futuristic and forward-looking as the Arecibo telescope was when first conceived. It was an ambitious and inspiring structure, and we sure will miss it. Thank you for watching, and let me know what you think. A sewage collection system is not only a modern convenience, but also one of the most critical pillars of public health in an urban area. Humans are kind of gross. We collectively create a constant stream of waste that threatens city dwellers with plague and pestilence unless it's safely carried away. Sewers convert that figurative stream into a literal one that flows below ground, away from public view and hopefully public smell. There are a lot of technical challenges with getting so much poop from point A to point B, and the fact that we do it mostly out of mind, I think, is cause for celebration. So this video is an ode to the grossest and probably most underappreciated pieces of public infrastructure. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about sewers. This video is sponsored by CuriosityStream and Nebula. More on that later. As easy as it sounds to slap a pipe in the ground and point it toward the nearest wastewater treatment plant, designing sanitary sewage lines, like a lot of things in engineering, is a more complex task than you would think. It is a disruptive and expensive ordeal to install subsurface pipes, especially because they're so intertwined with roadways and other underground utilities. If we're going to go to the trouble and cost to install or replace them, we need to be sure that these lines will be there to stay, functioning effectively for many decades. And speaking of decades, sewers need to be designed not just for the present conditions, but also for the growth and changes to the city over time. More people usually means more wastewater, and sewers must be sized accordingly. Joseph Bazalgette, who designed London's original sewer system, famously doubled the proposed sizes of the tunnels, saying, "We're only going to do this once." Although wantonly oversizing infrastructure isn't usually the right economic decision, in that case, the upsizing was prescient. Finally, these lines carry some awful stuff that we do not want leaking into the ground or, heaven forbid, into the drinking water supply, whose lines are almost always nearby. This all to say, the stakes are pretty high for the engineers, planners, and contractors who make our sewers work. One of the first steps of designing a sewage collection system is understanding how much to expect. There are lots of published studies and guidelines for estimating average and peak wastewater flows based on population and land use, But just counting the number of flushes doesn't tell the whole story. Most sanitary systems are separated from storm drains, which carry away rainfall and snowmelt. That doesn't mean precipitation can't make its way into the sewage system, though. Inflow and infiltration, referred to in the business as I&I, are the enemies of utility providers for one simple reason: precipitation finding its way into sewers through loose manholes, cracks in pipes, and other means can overwhelm the capacity of the system during storms. The volume of the fabled super flush during the halftime of the Super Bowl is usually a drop in the bucket compared to a big rainstorm. I&I can lead to overflows which create exposure to raw sewage and environmental problems. So, utilities try to limit this I&I to the extent possible through system maintenance, and engineers designing sewers try to take it into account when choosing the system capacity. Once you know how much sewage to expect, then you have to design pipes to handle it. It's often said that a civil engineer's only concerns are gravity and friction. I'll let you take a guess at which one of those makes poop flow downhill. It's true that almost all sewage collection systems rely mostly on gravity to do the work of collecting and transporting waste. This is convenient because we don't have to pay a gravity bill. It comes entirely free. But like most free things, it comes with an asterisk, mainly that gravity only works in one direction, down. This fact constrains the design and construction of modern sewer systems more than any other factor, and I've built some demonstrations in the garage to show you how. I'm pumping a slurry of sand and water through this clear pipe, which represents a sewer, and we'll take a look at the factors engineers consider in designing these systems. We need some control over the flow in a sewer pipe. It shouldn't be too fast so as to damage the joints or walls of the pipe, but it can't flow too slow, or you risk solids settling out of suspension and building up over time. We can't adjust gravity up or down to reach this balance, and we also don't have much control over the flow of wastewater. People flush when they flush. The only things engineers can control are the size of the sewer pipe and its slope. Take a look at what happens when the slope is too low. The water moves too slowly and allows solids to settle on the bottom. Over time, these solids build up and reduce the capacity of the pipe. They can even completely clog. Pipes without enough slope require frequent and costly maintenance from work crews to keep the lines clear. If I adjust the slope of the line without changing the flow rate, watch what happens. The velocity of the water increases. This not only allows solids to stay in suspension, but it also allows the water to scour away the solids that have already settled out. The minimum speed to make sure lines stay clear is known as the self-cleaning velocity, and you can see why in the demo. It can vary, but most cities require that flow in a sewer pipe be at least 3 feet or 1 meter per second. So far, I've been using sand to simulate the typical solids that could be found in a wastewater stream, but you might be interested to know that we're, thankfully and by design, only scratching the surface of synthetic human waste. Laboratories doing research on urban sanitation, wastewater treatment, and even life support systems in space often need a safe and realistic stand-in for excrement, of which there are many interesting recipes published in the academic literature. This polymer slime toy is as realistic as I want to be while keeping this video family-friendly, but feel free to take your own journey down the rabbit hole of simulated sewage after this. I mean that figuratively, of course. The slope of a sewer pipe is not only constrained by the necessary range of flow velocities, it also needs to consider the slope of the ground above. If the slope is too shallow compared to the ground, the sewer can get too close to the surface, losing protection of the overlying soil. If the slope is too steep compared to the ground, the sewer can eventually become too deep below the surface. Digging deep holes to install sewer pipes isn't impossible or anything, but it is expensive. Above a certain depth, you need to lay back the slopes of the trench to avoid having it collapse. In urban areas where that's not possible, you instead have to install temporary shoring to hold the walls open during construction. You can also use trenchless excavation like tunneling, but that's a topic for another video. This all to say that choosing a slope for a sewer is a balance. Too shallow or too steep and you're creating extra problems. Another topographic challenge faced by sewer engineers is getting across a creek or river. It is usually not cost-effective to lower an entire sewer line or increase its slope to stay below a natural channel. In these cases, we can install a structure called an inverted siphon. This allows for a portion of the line to dip below a depressed topographic feature like a river or creek and come back up on the other side. The hydraulic grade line, which is the imaginary line representing the surface of the fluid, comes up above the surface of the ground, but the pipe contains the flow below the surface. The problem with inverted siphons is that because they flow full, the velocity of the flow goes down. That means solids are more likely to settle out, something that is especially challenging on a structure with limited access for maintenance. This is similar to the P or U trap below your sink, that spot where everything seems to get stuck. Notice how even though the pipe is the same size along the full length, settling is only happening within the siphon. To combat this issue, inverted siphons often split the flow into multiple smaller pipes. This helps keep the velocity up above the self-cleaning limit. A smaller pipe obviously means a lower capacity, which is partly why siphons often include 2 or 3. You can see that even though there's some settling happening, it's not increasing over time. The velocity of the flow in the smaller siphons is high enough to keep most of the solids in suspension. The volume and hydraulics of wastewater flow aren't the only challenges engineers face. Sewers are lawless places by nature. There are no wastewater police monitoring what you flush down the toilet, thank goodness. However, that means sewers often end up conveying, or at least trying to convey, substances and objects for which they weren't designed. For a long time, grease and oil were the most egregious of these interlopers since they congeal at room temperatures. However, the rising popularity of quote-unquote flushable wipes has only made things worse. Grease and fat combine with wet wipes in sewers to create unsettling but aptly named fatbergs, disgusting conglomerates that, among other things, are not easily conveyed through sanitary sewer lines. Just to illustrate the issue, this is how quickly toilet paper breaks down when agitated in a mixer. And this is a wet wipe labeled flushable. You can imagine the problems this would cause. Conveniently, most places in the world have services available to carry away your solid waste so you don't have to flush them, but they usually do it in trucks, not pipes. Obviously, this issue is more complicated than my little experiment. The labeling of wipes has turned into a controversy that is too complex to get into here. My point, though, and indeed the point of this whole video, is that your friendly neighborhood sewage collection system is not a magical place where gross stuff goes to disappear. It's a carefully planned, thoroughly tested system designed to keep the stuff we don't want to see unseen. What happens to your flush once it reaches a wastewater treatment plant is a topic for another video, but I think the real treasure is the friends, sewers, it made along the way. If you're here at the end of the video, I'm guessing that means you're pretty thoughtful about the kind of videos you spend your time enjoying. In other words, you probably prefer learning new things about the world rather than run-of-the-mill television programming. You probably also don't enjoy watching ads like this one, which is great because Nebula doesn't have it. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Wendover Productions, and a bunch of others, including me. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. My videos go live there the day before they publish here, no ads or sponsorships. And we're super excited to be partnered with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and all those monthly subscriptions can be tough to keep track of. That's why this bundle is such an awesome deal. CuriosityStream's taking 26% off an annual plan. That makes it only $15 for an entire year of access to thousands of awesome documentaries on CuriosityStream and everything on Nebula as well. You can watch awesome long-form content on CuriosityStream. I love this David Attenborough special called Light on Earth about all the different animals that exhibit bioluminescence. Or watch Tom Scott pit other YouTubers against each other on his Nebula exclusive game show, Money. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a great deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. In May of 2021, Inspectors on the Hernando de Soto Bridge between Arkansas and Memphis, Tennessee, discovered a crack in a major structural member. They immediately contacted emergency managers to shut down this key crossing over the Mississippi River to vehicle traffic above and maritime traffic below. How long had the crack been, and how close did this iconic bridge come to failing? I'm Grady. This is Practical Engineering. In today's episode, we're discussing the Memphis I-40 bridge incident. The Hernando de Soto Bridge carries U.S. Interstate 40 across the Mississippi River between West Memphis, Arkansas, and Memphis, Tennessee. Opened for traffic in 1973, the bridge's distinctive double-arch design gives it the appearance of a bird gliding low above the muddy river. I-40 through Tennessee and Arkansas is one of the busiest freight corridors in the United States. So the Mississippi River Bridge is a vital east-west link, carrying an average of 50,000 vehicles per day. Although it was built in the 70s, the bridge has had some major recent improvements. It's located in a particularly earthquake-prone region called the New Madrid seismic zone. Starting in 2000 and continuing all the way through 2015, seismic retrofits were added to the bridge to help it withstand a major earthquake and serve as a post-earthquake lifeline link for emergency vehicles and the public. RDOT and TDOT share the maintenance responsibilities for the structure, with RDOT in charge of inspections. On May 11, 2021, a climbing team from an outside engineering firm was performing a detailed inspection of the bridge's superstructure. During the inspection, they noted a major defect in one of the steel members below the bridge deck. The crack went through nearly the entire box with a significant offset between the two sides. Recognizing the severity of the finding, several of the engineers called 911 to alert local law enforcement agencies and shut the bridge down to travel above and below the structure. This decision to close the bridge snarled traffic, forcing cars and trucks to detour over the older and smaller I-55 bridge nearby. It also created a backup of hundreds of barges and ships needing to pass north and south on the Mississippi River below the bridge. Knowing how significant an impact closing the bridge would be on such a vital corridor, how did engineers know to act so quickly and decisively? In other words, how important is this structural member? To explain that, we need to do a quick lesson on arch bridges. There are so many ways to span a gap, all singular in function, but remarkably different in form. One type of bridge takes advantage of a structural feature that's been around for millennia, the arch. Most materials are stronger against forces along their axis than those applied at right angles, called bending forces. That's partly because bending forces introduce tension in structural members. Instead of beams that are loaded perpendicularly, arch bridges use a curved element to transfer the weight of the bridge to the substructure using almost entirely compressive forces. Many of the oldest bridges use arches because it was the only way to span a gap with materials available at the time, stone and mortar. The Caravan Bridge in Turkey was built nearly 3,000 years ago, but is still in use today. Even now, with the convenience of modern steel and concrete, arches are a popular choice for bridges. When the arch is below the roadway, we call it a deck arch bridge. Vertical supports transfer the load of the deck onto the arch. If part or all the arch extends above the roadway with the deck suspended below, it's a through arch bridge like the Hernando de Soto. Arches can be formed from many different materials, including steel beams, reinforced concrete, or even stone or brick masonry. The I-40 Mississippi River Bridge has two arches made from a lattice of steel trusses. One result of compressing an arch is that it creates horizontal forces called thrusts. So, arch bridges normally need strong abutments on either side to push against that can withstand the extra horizontal loads. So why do the arches of this bridge sit on top of spindly piers? Just from looking at it, you can tell that this support was not designed for horizontal loading. That's okay, because the Hernando de Soto uses tied arches. Instead of transferring the arch thrust into an abutment, you can tie the two ends together with a horizontal cord. This tie works exactly like a bowstring, balancing the arch's thrust forces with its resistance to tension. Tied arch bridges don't transfer thrust forces to their supports, meaning they can sit atop piers designed primarily for vertical loads. This tension member is the subject of our concern. The crack in the Hernando de Soto Bridge went right through one of the two arch ties on the eastern span. Watch what happens if I simulate a crack in my homemade bridge model. It's hard to understate the severity of the situation. These ties are considered fracture-critical members, those non-redundant structural elements subject to tension whose fracture would be expected to result in a collapse of the entire bridge. Obviously, this member did fracture without a collapse, so there may be a dispute about whether it truly qualifies as fracture-critical. But suffice to say that losing the tie on a tied arch bridge is not a minor issue. So why would a tension member like this crack? Let me throw in a caveat here before continuing. Structural engineering is not an armchair activity. Forensic analysis of a failure requires a tremendous amount of information before arriving at a conclusion, including structural analysis, material testing, and review of historical information. Without such an investigation, the best we can do is speculate. A detailed forensic review will almost certainly be performed, and then we'll know for sure. With all that said, there's really only one reason that a steel member would crack like what's shown in the photos of the I-40 bridge. When steel fails, it's usually a ductile event. In other words, the material bends, deforms, and stretches. But steel can experience brittle failures too, called fractures, where little deformation occurs. And the primary reason that a crack would initiate in a steel tension member of a bridge is fatigue. Fatigue in steel happens because of repeated cycles of loading. Over time, microscopic flaws in the material can grow into cracks that open a small amount with each loading cycle, even if those loading cycles are well below the metal's yield strength. If not caught, a fatigue crack will eventually reach a critical size where it can propagate rapidly, leading to a fracture. Bridges are particularly susceptible to fatigue because traffic loads are so dynamic. This bridge sees an average of 50,000 vehicles per day. That is tens of millions of load cycles every year. Fatigue is common on steel members that have been welded because welding has a tendency to introduce flaws in the material. When weld metal cools, it shrinks, generating residual stress in the steel. These stress concentrations are where most fatigue cracks occur. And the box tie member at the I-40 bridge is a built-up section. That means it was fabricated by welding steel plates together. It's a common way to get structural steel members in whatever shape the design requires. But if not carefully performed, the welds have the potential to introduce flaws from which a fatigue crack can propagate. Of course, these ties aren't purely tension members holding the two sides of the arch together. If they were, the load cycles would probably be a lot less dynamic. The ties don't support these lateral beams below the road deck. That's done by the suspender cables hanging from the arch above. But they do have a rigid connection. That means when the deck moves, the tension ties move with it, potentially introducing stresses that could exacerbate the formation of a crack. Again, without a detailed structural model, it's impossible to say how the dynamic cycles of traffic forces are distributed through each member. We can't say whether the original design or the seismic retrofits had a flaw that could have been prevented. Fatigue and fractures are difficult to characterize, and in some cases, inevitable, given the construction materials and methods, even with a good design. That's why inspections are so important. One of the biggest questions everyone's asking, and rightly so given the severity of the situation, is how long has this structural member been cracked? National bridge standards require inspections for highway bridges every 2 years. Bridges with fractured critical members like this one are usually inspected more frequently than that, and inspection of those members has to be hands-on. That means no drones or observations from a distance. A human person has to check every surface of the steel from, at minimum, an arm's length away. Given those requirements, you would think that this crack, discovered in May of 2021, did not exist the year before. Unfortunately, RDOT provided a drone inspection video from 2 years earlier, clearly showing the crack on the tie beam. Although it hadn't yet grown to its eventual size, the crack is nearly impossible to miss. And it could have been there well before that video was shot. One amateur photographer who took a canoe trip below the bridge in 2016 shared a photo of the same spot, and it sure looks like there's a crack. Bridge inspections are not easy. Even on simple structures, they often require special equipment, like snooper trucks, and closing down lanes of traffic. Complicated structures like the I-40 bridge require teams of structural engineers trained in rope access climbing to put eyes on every inch of steel. And even then, cracks are hard to identify visually and can be missed. Inspectors are humans, after all, but none of that justifies this incident, especially given how large and obvious the fracture was. RDOT announced that they fired an unnamed inspector who was presumably responsible for the annual inspections on this bridge. We don't know many details of that situation, but I just want to clarify that it's not a solution to the problem. If your ability to identify a major defect in a fractured critical member of a bridge hinges on a single person, there's something very wrong with your inspection process. Quality management is an absolutely essential part of all engineering activities. We know we're human and capable of mistakes, so we build processes that reduce their probability and consequences. That includes quality assurance, which are the administrative activities of verifying the work is being performed correctly, such as making sure the bridges are inspected by teams and that inspectors are properly trained. It also includes quality control, the checks and double checks of work products like inspection reports. And quality management should be commensurate with the level of risk. In other words, if an error would threaten public safety, you can't just leave it up to a single person. Put simply and clearly, there is absolutely no excuse for this crack to have sat open on the bridge's tire for as long as it did. This story is ongoing. As of this video's writing, the bridge is closed to traffic indefinitely. But that doesn't mean the incident is over. There's a chance that, as the forces in the bridge contributed with the damage to this vital member, other structural elements became overloaded. The second tension tie may have taken up much of its partner's stress, and the pier supporting the arch may have been subject to a lot more horizontal force than it was designed to withstand. In addition, bridges are full of repetitive details. If this crack could happen in one place, there's a good chance similar cracks may exist elsewhere. The Federal Highway Administration recommends that when a fatigue crack is found, a special in-depth inspection be performed to look for more. That will involve hands-on checking of practically every square inch of steel on the bridge, and probably non-destructive tests that can identify defects like using X-rays, magnetic particles, or dyes that make the cracks more apparent. The repair plan for the bridge is already in progress. Phase 1 was to temporarily reattach the tie using steel plates to make the bridge safe for contractors. The design for Phase 2 will depend entirely on the findings of detailed structural analysis and forensic investigation. In the meantime, it's clear that RDOT and TDOT have some work ahead of them. Most importantly, they need to do some reckoning with their bridge inspection procedures and thank their lucky stars that this fracture didn't mean catastrophe. There's no clear end in sight for the inconvenience motorists needing to cross the Mississippi River, but I'm thankful that they're all still around to be inconvenienced. Thank you for watching, and let me know what you think. This is the West Closure Complex, a billion-dollar piece of infrastructure that protects parts of New Orleans from flooding during tropical storms. Constructed partly as a result of Hurricane Katrina, it features one of the largest pumping stations in the world, capable of lifting the equivalent of a fully loaded Boeing 747 every second. When storm surge threatens to raise the levels of the sea above developed areas on the west bank of the Mississippi River, the facility's job is to hold it back. The gates close and the pumps move rainwater and drainage from the city's canals back into the Mississippi River and out to the Gulf. This pump station may be the largest of its kind, but its job is hardly unique. We collectively move incredible volumes of freshwater, drainage, and wastewater into, out of, and around our cities every day. And we mostly do it using pumps. I love pumps, but even though they're critical for the safety, health, and well-being of huge populations of people, there are a lot of things that can go wrong if not properly designed and operated. I'm Grady, and this is Practical Engineering. In today's episode, we're exploring some of the problems that can happen with pumps. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. I've got some colored water and clear pipe out here in my garage to demonstrate a few common pitfalls that pumps can face. And the first one is priming. Although liquids and gases are both fluids, not all pumps can move them equally. Most types of pumps that move liquids cannot move air. It's less dense and more compressible, so it's often just unaffected by impellers designed for liquids. That has a big implication, though. It means if you're starting a pump dry, that is, when the intake line and the housing are not already full of water, like I'm doing here, nothing happens. The pump can run and run, but because it can't draw air out of the intake line, no water ever flows. This is why mini pumps need to be primed before starting up. Priming just means filling the pump with liquid to displace the air out of the housing and sometimes the intake pipe. Watch what happens when I raise the discharge line to let water flow backwards into the pump. It happens quickly. As soon as the air is displaced from the housing, the pump is primed and water starts to flow. There are a lot of creative ways to accomplish this for large pumps. Some even have small priming pumps to do this very job. But what primes the priming pumps? Well, there are some kinds of pumps that are self-priming. One is submersible pumps that are always below the water where air can't find its way in. Another is positive displacement pumps that can create a vacuum and draw air through. They may not be as efficient or convenient to use as the main pump, but they work just fine for the smaller application of priming. However a pump is primed, it's critical that it stays that way. If air finds its way into the suction line of a pump, it can lose its prime and stop working altogether. When I lift the pump out of the water, the prime is lost. And now if I put the pump back down into the water, it doesn't start back up. This can be a big problem if it goes unnoticed, not just because the pump isn't working, but also because running a pump dry often leads to damage. Many pumps depend on the fluid in the housing for cooling, so without it, they overheat. In addition, the seals around the shaft that keep water from intruding on the motor depend on the fluid to function properly. If the seals dry out, they get damaged and require replacement, which can be a big job. The next problem with pumps is also related to the suction side. Pumps work by creating a difference in pressure between the inlet and outlet. In very simple terms, one side sucks and one side blows. A problem comes when the pressure gets too low on the suction side. You might know that the phase of many substances depends not just on their temperature, but also the ambient pressure. That's why the higher you are in elevation, the lower the temperature needed to boil water. If you continue that trend in the lower and lower pressures, eventually some liquids, including water, will boil at normal temperatures without any added heat. It's a pretty cool effect as a science demonstration, but it's not something you want happening spontaneously inside your pump. Just like they don't work with air, most pumps don't work very well with steam either. But the major problem comes when those bubbles of steam collapse back into a liquid. Liquids aren't very compressible, so these collapsing bubbles send powerful shockwaves that can damage pump components. This phenomenon is called cavitation, and I have a video covering it in a lot more detail that you can check out after this one to learn more. It usually doesn't lead to immediate failure, but cavitation will definitely shorten the life of a pump significantly if not addressed. The solution to this problem at pumps is known as net positive suction head, and with a name like that, you know it's important. Manufacturers of large pumps will tell you the required net positive suction head, or NPSH, which is the minimum pressure needed at a pump inlet to avoid cavitation. The engineer's job is to make sure that a pump system is designed to provide at least this minimum pressure. That NPSH depends on the vertical distance between the sump and inlet, the frictional losses in the intake pipe, the temperature of the fluid, and the ambient air pressure. Here's an example. With this valve wide open, the suction pressure at the inlet is about 20 kilopascals or 5 inches of mercury. Now watch what happens when I move the pump to the top of the ladder but leave the bucket on the ground. The suction pressure just about doubles. A constriction in the line also decreases the available NPSH. If I close this valve on the intake side of my pump, you immediately see the pressure in the line becoming more negative. In other words, a stronger vacuum. This pump isn't strong enough to cavitate, but it does make a bad sound when there isn't enough positive suction head at the inlet. I think it easily demonstrates how a poor intake design can dramatically affect the pressure in the intake line and quickly lead to failure of the pump. The last problem that can occur at pumps is also the most interesting: vortices. You've probably seen a vortex form when you drain a sink or bathtub. These vortices occur when the water accelerates in a circular pattern around an outlet. If the vortex is strong enough, the water is flung to the outside, allowing air to dip below the surface. This is a problem for pumps if that air is allowed to enter the suction line. We talked a little bit about what happens when a pump runs dry, to run at a reduced performance, and may cause it to lose prime, creating further damage. The easiest solution to vortexing is submergence, just getting the intake pipe as far as possible below the surface of the water. The deeper it is, the larger and longer a vortex would have to be before air could find its way into the line. This is achieved by making the sump, that is, the structure that guides the water toward the intake, deeper. That solution seems simple enough, except these sumps are often major structural elements of a pump station that are very costly to construct. You can't just indiscriminately oversize them, but how deep is deep enough? It turns out that's a pretty complicated question, because a vortex is hard to predict. Even sophisticated computational fluid dynamics models have trouble accurately characterizing when and if a vortex will form. That's an issue because you don't want to design and construct a multi-million-dollar pumping facility just to find out it doesn't work. And there aren't really off-the-shelf designs. Just about every pumping station is a custom-designed facility meant for a specific application. Whether it's delivering raw water from a reservoir or river to a treatment plant, sending fresh water out to customers, lifting sewage to be treated at a wastewater plant, pumping rainwater out of a low area, or any number of other reasons to move large volumes of water. So, if you're a designer, you have some options. First, you can just be conservative. We know through lots of testing that vortices occur mostly due to non-uniform flow in the sump. Any obstructions, sharp turns, and even vertical walls can lead to flow patterns that evolve into vortices. Organizations like the Hydraulic Institute have come up with detailed design standards that can guide engineers through the process of designing a pump station to make sure that many of these pitfalls are avoided. Things like reducing the velocity of the flow and maintaining clearance between the walls and the suction line can reduce the probability of a vortex forming. There are also lots of geometric elements that can be added to a sump or intake pipe to suppress the formation of vortices. The second option for an engineer is to build a scale model, like I have here. Civil engineering is a little bit unique from other fields because there aren't as many opportunities for testing and prototyping. Infrastructure is so large and costly, you usually only have one shot to get the design right. But some things can be tested at scale, including hydraulic phenomena. In fact, there are many laboratories across the world that can assemble and test scale models of pump stations, pipelines, spillways, and other water handling infrastructure to make sure they work correctly before spending those millions or billions of dollars on construction. They give engineers a chance to try out different configurations, gain confidence in the performance of a hydraulic structure, and avoid the pitfalls like loss of prime, cavitation, and vortices at pump stations. It's time for everyone's favorite segment of watching me try to cook while my wife tries to capture that on video.
Don't mind if I just ground some espresso in the background.
Goofing around in the kitchen is one of our favorite things to do together. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night.
How geometrically pleasing to the eye.
We are indecisive eaters, meaning neither one of us likes to be the one to decide what's for dinner, so it's nice to have HelloFresh curating delicious and healthy recipes so we don't have to.
Don't mash it.
The pre-portioned ingredients means there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner ready quickly when we don't feel like planning prep and shopping, which is pretty much every day right now. Go try it yourself at HelloFresh.com and use code PRACTICAL12 to get 12 free meals, including free shipping.
You're mashing it. Just throw that one in there.
Supporting our sponsors helps support this channel. That's HelloFresh.com and use code PRACTICAL12. Thanks HelloFresh, and thank you for watching. Let me know what you think. In February 2017, concrete slabs in the spillway at Oroville Dam failed during releases from the floodgates, starting a chain of events that prompted the evacuation of nearly 200,000 people downstream. The dam didn't fail, but it came too close for comfort, especially for the tallest structure of its kind in the United States. Oroville Dam falls under the purview of the Federal Energy Regulatory Commission in a state with a progressive dam safety program and regular inspections and evaluations by the most competent engineers in the industry. So how could a failure mode like this slip through the cracks, both figuratively and literally? Luckily, an independent forensics team got deep in the weeds and prepared a 600-page report to try and find out. This is a summary of that. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the Oroville Dam crisis. Oroville Dam, located in Northern California, is the tallest dam in the United States at 770 feet or 235 meters high. Completed in 1968 and owned and operated by the California Department of Water Resources, every part of Oroville Dam is massive. The facility consists of an earthen embankment, which forms the dam itself, a hydropower generation plant that can be reversed to create pump storage, a service spillway with 8 radial floodgates, and an emergency overflow spillway. The reservoir created by the dam, Lake Oroville, is also immense, the second biggest in the state. It's part of the California State Water Project, one of the largest water storage and delivery systems in the U.S. that supplies water to more than 20 million people and hundreds of thousands of acres of irrigated farmland. The reservoir is also used to generate electricity with over 800 megawatts of capacity. Finally, the dam also keeps a reserve volume empty during the wet season. In case of major flooding upstream, it can store floodwaters and release them gradually over time, reducing the potential damage downstream. No dam is built to hold all the water that could ever flow into the reservoir at once, and yet having water over top an unprotected embankment will almost certainly cause a breach and failure. So all dams need spillways to safely release excess inflows and maintain the level of the reservoir once it's full. Spillways are often the most complex and expensive components of a dam, and that's definitely true at Oroville. The service spillway has a chute that is 180 feet or 55 meters wide and 3,000 feet long. That's nearly a kilometer for the metric folks. Radial gates control how much water is released, and massive concrete blocks at the bottom of the chute, called dentates, disperse the flow to reduce erosion as it crashes into the Feather River. This spillway is capable of releasing nearly 300,000 cubic feet or 8,000 cubic meters of water per second. That's roughly an Olympic-sized swimming pool every other second, which I know isn't that helpful in conceptualizing this incredible volume. If you somehow put that much flow through a standard garden hose, it would travel at 15% of the speed of light, reaching the moon in about 9 seconds. How's that for a flow rate equivalency? But even that is not enough to protect the embankment. Large dams have to be able to withstand extraordinary flooding. In most cases, their design is based on a synthetic or made-up storm called the probable maximum flood, which is essentially an approximation of the most rain that could ever physically fall out of the sky. It usually doesn't make sense to design the primary spillway to handle this event, since such a magnitude of flooding is unlikely to ever happen during the lifetime of the structure. Instead, many dams have a second spillway, much simpler in design and thus less expensive to construct, to increase their ability to discharge huge volumes of water during rare but extreme events. At Oroville, the emergency spillway consists of a concrete weir set 1 foot above the maximum operating level. If the reservoir gets too high and the service spillway can't release water fast enough, this structure overflows, preventing the reservoir from reaching and overtopping the crest of the dam. Early 2017 was one of Northern California's wettest winters in history, with several major flood events across the state. One of those storms happened in February, upstream of Oroville Dam. As the reservoir filled, it became clear to operators that the spillway gates would need to be opened to release excess inflows. On February 7th, early during the releases, they noticed an unusual flow pattern about halfway down the chute. The issue was worrying enough that they decided to close the gates and pause the flood releases in order to get a better look. What they saw when the water stopped was harrowing. Several large concrete slabs were completely missing, and a gigantic hole had eroded below the chute. There was a lot more inflow to the reservoir in the forecast, so operators knew they didn't have much time to keep the gates closed while they inspected the damage, and no chance to try to make repairs. They knew they would have to keep operating the crippled spillway. So they started opening gates incrementally to test how quickly the erosion would progress. Meanwhile, more rain was falling upstream, contributing to inflows and raising the level of the reservoir faster and faster. It wasn't long before operators were faced with an extremely difficult decision. Open more gates on the service spillway, which would further damage the structure, or let the reservoir rise above the untested emergency spillway and cascade down the adjacent hillside. Several issues made this decision even more complicated. On one hand, the service spillway was in bad shape, and there was the possibility of the erosion progressing upstream toward the headworks, which could result in an uncontrolled release of the reservoir. Also, debris from the damaged spillway was piling up in the Feather River, raising its level and threatening to flood out the power plant. Finally, electrical transmission lines connecting the power plant to the grid were being threatened by the erosion along the service spillway. Losing these lines or flooding the hydropower facility would hamstring the dam's only backup for making releases from the reservoir. Operators knew that repairing the spillway would be nearly impossible until the power plant could be restored. These factors pointed toward closing the spillway gates and allowing the reservoir to rise. On the other hand, the emergency spillway had never been tested, and operators weren't confident that it could safely release so much water, especially after witnessing how quickly and aggressively the erosion happened on the service spillway nearby. Also, its use would almost certainly strip at least the top layer of soil and vegetation from the entire hillside, threatening adjacent electrical transmission towers. A huge contingent of engineers and operations personnel were all hands on deck, running analyses, forecasting weather, reviewing geologic records and original design reports, trying to decide the best course of action. Of course, all this is happening over the course of only a couple of days, with conditions constantly changing and no one having slept, further complicating the decision-making process. Operators work to find a sweet spot in managing these risks, limiting releases from the service spillway as much as possible while trying to keep the reservoir from overtopping the emergency spillway. But every new forecast just showed more rain and more inflows. Eventually, it became clear to operators that they would have to pick a lesser evil: increase discharges and flood the powerhouse, or let the reservoir rise above the emergency spillway. They decided to let the reservoir come up. The morning of February 11th, about 4 days after the damage was initially noticed, Lake Oroville rose above the crest of the emergency spillway for the first time in the facility's history. Almost immediately, it was clear that things were not going to go smoothly. As it flowed across and down the natural hillside, water from the emergency spillway began to channelize and concentrate. This quickly accelerated erosion of the soil and rock, creating features called headcuts, which are a sign of unstable and incising waterways. Headcuts are vertical drops in the topography eroded by flowing water, and they always move upstream, oftentimes aggressively. In this case, upstream meant toward the emergency spillway structure, threatening its stability. This hillside was a zone many had assumed to be solid, competent bedrock. It only took a modest flow through the emergency spillway to reveal the true geologic conditions. The hillside was composed almost entirely of highly erodible soil and weathered rock. If the headcuts were to reach the concrete structure upstream, it would almost certainly fail, releasing a wall of water from Oroville Lake that would devastate downstream communities. Authorities knew they had to act quickly. On February 12th, only about a day and a half after flow over the emergency spillway began, an evacuation order was issued for downstream residents, displacing nearly 200,000 people to higher ground. At the same time, operators elected to open the service spillway gates to double the flow rate and accelerate the lowering of the reservoir. The level dropped below the emergency spillway crest that night, stopping the flow and easing fears about an imminent failure. 2 days later, on Valentine's Day, the evacuation order was changed to a warning, allowing people to return to their homes. But there was still more rain in the forecast, and the emergency spillway was in poor condition to handle additional flow if the reservoir were to rise again. California DWR continued discharging through the crippled service spillway to lower the reservoir by 50 feet or 15 meters in order to create enough storage that the spillway could be taken out of service for evaluation and repairs. The gate stayed open until February 27th, nearly 3 weeks after this whole mess started, revealing the havoc to the dam's right abutment. Water that started its journey as tiny drops of rain in a heavy storm, funneled and concentrated by the Earth's topography and turbulently released through massive human-made structures, had carved harrowing scars through the hillside. But how did it happen? Like all major catastrophes, there were a host of problems and issues that coincided to cause the failure of the concrete chute. One of the most fundamental issues was geologic. Although it was well understood that some areas of the spillway's foundation were not good stuff, in other words, weathered rock and soil, the spillway was designed and maintained as if the entire structure was sitting on hard bedrock. That mischaracterization had profound consequences that I'll discuss. As for how the spillway damage started, the issue was uplift forces. How do concrete structures stay put? Mostly by being heavy. Their weight pins them to the ground so they can resist other forces that may cause them to move. But water complicates this issue. You might think that adding water to the top of a slab just adds to the weight, making things more stable. And that would be true without cracks and joints. The problem with the Oroville Dam service spillway chute was that it had lots of cracks and joints, for reasons I'll discuss in a moment. These cracks allowed water to get underneath the slabs, essentially submerging the concrete on all sides. Here's the issue with that. Structures weigh less underwater, or more accurately, their weight is counteracted by the buoyant force of the water they displace. So being underwater already starts to destabilize them because it adds an uplift force. But concrete still sinks underwater, right? The net force is still down, holding the structure in place. That's true in static conditions, but when the water is moving, things change. We talk about Bernoulli's principle a lot on this channel, and he's got something to say about the flow of water in a spillway. In this case, the issue was what happens to a fast-moving fluid when it suddenly stops. Cracks and joints in a spillway have an effect on the flow inside. Any protrusion into the stream redirects the flow. If a joint or crack is offset, that redirection can happen underneath the slab. When this happens, all the kinetic energy of the fluid is converted into potential energy. In other words, pressure. When it's 100% of the kinetic energy being converted, we call it the stagnation pressure. See how the level rises in this tube when I direct it into the flowing water? The equation for stagnation pressure is a function of the velocity squared. So if I double the speed of the flow in my flume, I get 4 times the resulting pressure, and thus 4 times the height the water rises in my tube. And the water in the Oroville spillway is moving a lot faster than this. When this stagnation pressure acts on the bottom of a concrete slab, it creates an additional uplift force. If all the uplift forces exceed the weight of the slab, it's going to move. That's exactly what happened at Oroville. And once one slab goes, it's just a chain reaction. More of the foundation is exposed to the fast-moving water, and more of that water can inject itself below the slabs, causing a runaway failure. Of course, we try to design around this problem. The service spillway had drains consisting of perforated pipes to relieve the pressure of water flowing beneath the slabs. Unfortunately, the design of these drains was a major reason for the cracking chute. Instead of trenching them into the foundations below the slabs, they reduced the thickness of the concrete to make room for the drains. The crack pattern on the chute essentially matched the layout of the drains beneath perfectly. So in this case, the drains inadvertently let more water below the slab than they let out from underneath it. The chute also included anchors, steel rods tying the concrete to the foundation material below. Unfortunately, those anchors were designed for strong rock, and their design wasn't modified when the actual foundation conditions were revealed during construction. The root cause wasn't just a bad design, though. There are plenty of human factors that played into the lack of recognition and failure to address the inherent weaknesses in the structure. Large dams are regularly inspected, and their designs periodically compared to the state of current practice in dam engineering. Put simply, we built bigger structures on worse foundations than this. Modern spillway designs have lots of features that help avoid what happened at Oroville. Multiple layers of reinforcement keep cracks from getting too wide. Flexible water stops are embedded into joints to keep water from migrating below the concrete. Joints are also keyed so individual slabs can't separate from one another easily. Lateral cutoffs help resist sliding and keep water from migrating beneath one slab to another. Anchors add uplift resistance by holding the slabs down against their foundation. Even the surface of joints is offset to avoid the possibility of a protrusion into the high-velocity flow. All these are things that the Oroville spillway either didn't have or weren't done properly. Periodic reviews of the structure's design, required by regulators, should have recognized the deterioration and inherent weaknesses and addressed them before they could turn into such a consequential chain of tribulations. As for the emergency spillway, the fundamental cause of the problem was similar: a mischaracterization of the foundation material during and after design. Emergency spillways are just that, intended for use only during a rare event where it's okay to sustain some damage. But it's never acceptable for the structure to fail, or even come close enough to failing that the residents downstream have to be evacuated. That means engineers have to be able to make conservative estimates of how much erosion will occur when an emergency spillway engages. Predicting the amount and extent of erosion caused by flowing water is a notoriously difficult problem in civil engineering. It takes sophisticated analysis in the best of times, and even then the uncertainty is still significant. It is practically impossible to do under the severe pressure of an emergency. The operators of the dam chose to allow the reservoir to rise above the crest of the emergency spillway rather than increase discharges through the debilitated service spillway, trusting the original designer that it could withstand the flows. It's a decision I think most people, in hindsight, would not have made. The powerhouse was further from flooding and the transmission lines further from failing than initially thought, and they eventually ramped up discharges from the service spillway anyway, after realizing the magnitude of the erosion happening at the emergency spillway. But it's difficult to pass blame too strongly. The operators making decisions during the heat of the emergency did not have the benefit of hindsight. They were stuck with the many small but consequential decisions made over a very long period of time that eventually led to the initial failure. Not to mention the limitations of professional engineering practices' ability to shine a light down multiple paths and choose the perfect one. The forensic team's report outlines many lessons to be learned from the event by the owner of the dam and the engineering community at large, and it's worth a read if you're interested in more detail. But I think the most important lesson is about professional responsibility. The people downstream of Oroville Dam, and indeed any large dam across the world, probably chose their home or workplace without considering too carefully the consequences of a failure and breach. We rarely have the luxury to make decisions with such esoteric priorities. That means whether they realize it or not, they put their trust in the engineers, operators, and regulators in charge of that dam to keep them safe and sound against disaster. In this case, that trust was broken. It's a good reminder to anyone whose work can affect public safety. The repairs and rebuilding of spillways at Oroville Dam are a whole other fascinating story. Maybe I'll cover that in a future video. Thank you for watching, and let me know what you think. There's a popular and persistent saying that pumps only create flow in a fluid, and resistance to that flow is what creates the pressure in a pipe. That may be helpful in conceptualizing what's happening in a pump system, but it's not the whole story. In fact, it's almost identical to another popular but misleading belief, this one about electrical safety, that says it's not the voltage that kills you, it's the current. Well, if you know anything about Ohm's law, you know that voltage and current go hand in hand, and the same is true about the pressure and flow rate in pipe systems. This isn't rocket science, but it's not common knowledge either, even though almost everyone has used or interacted with a pump before. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about how pumps work. This video is sponsored by CuriosityStream and Nebula. Get 26% off at the link in the description. More on that later. Let me just say right at the start that I love pumps. They're one of my favorite topics, so this is the first of 2 videos I'm doing about them. Let me know if you want to see more, because there are a ton of topics we can cover. Funny enough, most engineers working with pumps aren't all that concerned with the physics of what's happening inside one. They mostly care about performance. That's because the most important job of an engineer designing a pump system is choosing the right one. That might sound silly at first. For a small aquarium pump or sump pump, you usually don't have to be very thoughtful about selection. The difference between them on such a small scale is not that significant. But, like most things in our industry, those small variances turn into large ones at scale. As pumps get bigger and their roles become more important, selecting the right one for the job becomes a critical task. For example, choosing the wrong pump to supply a city with fresh water or get rid of floodwaters can be life or death. Today, we'll walk through some of the considerations engineers use to select the right pump, using demonstrations here in my garage and even give you some tips if you ever have to choose one yourself. Most pumps used in civil engineering, and indeed most pumps you'll encounter in your everyday life, are centrifugal pumps. That means they use an impeller connected to a motor to accelerate the liquid into the discharge line. If you go searching for pumps online for smaller applications, you'll likely see them listed according to flow rate. That makes sense because it's usually what we care about. How many gallons or liters per minute can I move? But for centrifugal pumps, it's not quite that simple. Let me show you what I mean. I have a small fountain pump here rated for 2 liters per minute. If I turn it on and pump this water into a beaker, it does just about that. It takes about 30 seconds to fill 1 liter. But watch what happens if I raise or lower the vertical distance of the beaker above the pump. In fact, through the magic of video compositing, I can show you all 3 at the same time. It's very easy to see the effect the discharge pressure has on the pump's flow rate. The higher the beaker, the greater the pressure, and the greater the pressure, the lower the flow. To illustrate this further, here's a graph of my little experiment with flow rate on the x-axis and pressure on the y-axis. In this case, I'm measuring pressure as the height of a fluid column, also known as head. You can see that my experiment created a curve on this graph. In fact, all centrifugal pumps have a curve like this, called the characteristic curve. And, at the risk of this just becoming a video about cool graphs, even though some might argue that it has inherent value on its own just by being a cool graph, in this case, it also is a means to an end. Let me show you why it's so important. No matter what you connect a pump to, whether a single hose or a complex citywide network of water mains, it's going to have its own curve, describing how much flow will occur under different pressure conditions. You can see when I change the supply pressure by adjusting this valve, the flow rate through the pipe changes accordingly. The graph of this relationship is called the system curve, and it's different for every network of pipes from the simple to the complex. A system with lots of constriction will have a more vertical curve, where no matter what the pressure is, the flow rate doesn't change much. A system with less constriction will have a flatter curve, where more pressure equals a lot more flow. A system at a much higher elevation or higher pressure will have a curve high up on the graph. System curves can even change over time. A city's freshwater distribution system will have a flatter curve during the day when more people are using their taps, and a steeper curve at night when the demand for water is lower. Stay with me because here's why this matters. If you plot a pump's characteristic curve on top of the system curve to which it's connected, you can see they intersect. This point of intersection tells you the pressure and flow rate at which the pump will operate. It's conceptually both simple and confusing. The pump doesn't decide what pressure and flow rate it will deliver. What it's connected to does. When I change my system curve by opening or closing this valve, both the pressure and flow rate created by the pump respond accordingly. So, to select the right pump for an application, you have to know how your system will respond to being supplied with a range of different pressures. Flow and pressure are important, but they're not the only considerations that go into pump selection. A pump curve sometimes also shows other important information, like efficiency. Even if a pump can operate in the extreme ranges of its performance curve, it usually can't do it efficiently. Listen to the sound of this pump as I close the valve, and you can tell that it's not performing its best over the full range of pressure. That might not matter in some applications, but if it's a big pump that requires a lot of energy, or one that will run 24/7, 365, this is something to be thoughtful about. Again, think about scale. On your fish tank pump, a little inefficiency is not a huge deal. If you're delivering water to millions of customers 24 hours a day, small inefficiencies add up quickly. And it's especially challenging if your system curve changes over time. It might seem cheaper to use a single pump that can handle a wide range of flow rates, but it's often more cost-effective to use multiple pumps so that you can always operate in the most efficient part of each one. The pump curve also shows you the pressure at which it can create any pump. Watch what happens when I raise the tube from my aquarium pump to above its maximum pressure. The liquid reaches the maximum head and it stops. I have to say, despite what you'll read in nearly every internet forum about pumps, this one is not creating flow, but it is creating pressure. I'm being a little facetious here, talking only about centrifugal pumps when there's another major category that behaves a little bit different. Positive displacement pumps trap a fixed volume of fluid and force it into the discharge line. Unlike centrifugal pumps, where the impeller can spin without actually moving any fluid, positive displacement pumps directly couple the motor to a fixed volume, no matter what the pressure is in the discharge line. As long as the motor has enough power to force that fluid out, it will happen at a constant rate. Essentially, their characteristic curve is just a flat line. I think in most cases, people who say that pumps only create flow and not pressure are specifically referring to positive displacement pumps. But if the pressure wouldn't be there without the pump, I have to contend that the pump created it. That said, I think I understand the sentiment of this idea that pumps only create flow and why it's so often repeated. It is a little bit confusing that a pump itself is not directly responsible for the flow rate and pressures under which it operates. Those properties depend on the characteristics of the system to which the pump is connected. In the case of a positive displacement pump, only the pressure is determined by the system curve. The flow rate is a fixed value. Both are still created by the pump, but only one is decided by it. For a centrifugal pump, both the flow and the pressure depend on the system curve. Given this discussion, I'd like to propose this new mantra for the internet pump enthusiast as a more correct answer to the question of whether pumps create pressure or flow. Pumps impart flow and pressure to a fluid in accordance with their characteristic curve and the corresponding system curve. Not a great catchphrase, but it is accurate. Maybe one of you can come up with something a bit more catchy. Thanks for sticking to the end of the video. If you're here, I'm guessing that means you prefer to spend your valuable free time learning new things about the world. You probably also don't enjoy watching ads like this one, which is great because Nebula doesn't have any. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Wendover Productions, and a bunch of others, including me. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. My videos go live there the day before they publish here, with no ads or sponsorships. And we're super excited to be partnered with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and it can be tough to add another monthly subscription. That's why this bundle is such an awesome deal. For a short time, CuriosityStream is taking 26% off an annual plan. That makes it only $15 for a year of access to thousands of awesome documentaries on CuriosityStream and everything on Nebula as well. You can watch awesome long-form content on CuriosityStream. One of my favorites is The Secret Life of Lakes, which covers fascinating details of both human-made and natural lakes across the world. Or watch Tom Scott pit other YouTubers against each other in his Nebula-exclusive game show, Money. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. On March 23, 2021, the massive container ship Ever Given ran aground in the Suez Canal. The wedged vessel obstructed the entire channel, blocking one of the most important trade routes in the world for nearly a week. The cause and details of this event are still under investigation, but there's a lot we already know. How could something like this happen, and why did it take so long to fix? I have two demonstrations to help us understand. I'm Grady, and this is Practical Engineering. In today's episode, we're exploring some of the engineering principles behind the 2021 Suez Canal obstruction. Before we get into the event itself, let's learn a little bit about the Suez Canal. Built in the 1860s, the Suez Canal is a constructed waterway in Egypt, allowing shipping and other maritime traffic to go from the Mediterranean Sea to the Red Sea and vice versa. This means ships don't need to navigate all the way north around the European and Asian continents or all the way south around the African continent to travel between the Atlantic and Indian Oceans. It's basically a global shortcut. That makes it one of the most important routes for global commerce, handling roughly 10% of the entire world's ocean trade. For as important as it is to the global economy, the Suez Canal is a relatively straightforward structure, essentially a trapezoidal channel cut through the sand of the low-lying Suez Peninsula and taking advantage of the existing Great Bitter Lake in the center. Unlike the Panama Canal, which uses locks to raise vessels up for transit, the Suez Canal is entirely at sea level, with no gates or locks. Minor differences in level between the Mediterranean and Red Seas create gentle currents in the canal, but they're not strong enough to trouble the ships. In 2016, an expansion to the Suez Canal opened, essentially doubling its capacity. The project involved adding a second shipping lane to part of the canal and deepening and widening some of the choke points so larger ships could pass through. It's now about 200 meters or 700 feet wide and about 24 meters or 80 feet deep. All ships passing through the Suez Canal are required to have a Canal Authority pilot to help navigate each step. These pilots aren't fully responsible for the safety of the ship during transit, but they have special knowledge about the processes, procedures, and challenges required to navigate these massive vessels through the canal. It's tricky, and ships have been stuck in the canal before, including a 3-day blockage in 2004. So, each ship's master, sometimes called the captain, and the Canal Authority pilot work together to maneuver the ship through. It takes about half a day to get from one end to the other, and on average about 50 ships make their way through the canal each day. Navigating the Suez Canal is a careful dance, since some parts of the channel only have a single shipping lane with no room to pass. That's why ships are required to go through in convoys. Early each morning, the convoys line up to enter the canal. The southbound group begins their journey from about 3 a.m. to 8 a.m. at Port Said, following the Western Channel. At around the same time, the northbound convoy enters the canal at Suez. On a normal day, everything is carefully timed so the two convoys can pass each other in the Great Bitter Lake and the dual-lane section of the canal without any stopping or interruptions. Unfortunately, March 23rd was not a normal day. One of the first ships in the northbound convoy, the Ever Given, had barely entered the canal at Suez when it veered into the eastern bank, smashing its bow into the sandy embankment and wedging the massive vessel diagonally across the channel's entire width. Amazingly, there was not a single injury and the cargo was completely unharmed. As I mentioned, the exact reason the ship ran aground is still under investigation. Some reporting suggested the Ever Given experienced a loss of power, but that was denied by the ship's technical manager. Sources also say there was an ongoing dust storm that morning, creating high wind and limited visibility. Many have suggested that the Ever Given's unscheduled and unfortunate landing in the canal may have been hastened by a hydraulic phenomenon unique to vessels transiting through shallow water called the bank effect. Luckily, I have an acrylic flume in my garage, and I can try to demonstrate how this works. But first, a little info on this ship. Leased and operated by the international shipping company Evergreen, the Ever Given is one of the 11 Golden-class container ships, all confusingly named Ever combined with a seemingly arbitrary G word. Weird names aside, these ships are truly massive. In fact, the Ever Given will never get a chance to go through the Panama Canal because it's too long for the locks at 400 meters or over 1,300 feet long. This is a cross-sectional view of the Suez Canal and the Ever Given to scale. The ship's beam is 60 meters or nearly 200 feet with a fully loaded draft of 15 meters or 48 feet. You can see how small the margin for error is with a ship this size in the canal. If you remember your lessons on buoyancy, you know that a ship displaces its own weight in water. That means for every pound of steel and cargo aboard, a pound of water below the ship has to get out of the way. For the Ever Given, that is hundreds of thousands of tons of liquid being pushed to either side of the ship as it cuts through the water. On the open sea, that's not a problem. The displacement forms a wake, but the water otherwise doesn't have trouble finding a new place to go. In a shallow canal, though, things are a little bit different. Let me show you what I mean. My flume isn't long enough to simulate a boat moving through a canal, but if you switch your frame of reference to that of a ship, it can simulate the movement of water passing by. In a shallow canal, all the water displaced by a ship has to essentially squish through the small areas along the sides and bottom of the vessel. The smaller the area, the faster the water has to move to get out of the way. I'm using some brick pavers as my surrogate shipping vessel. Watch what happens when I drop them in the flow. The water builds up at the bow or front of the ship. As the water accelerates through the narrow gaps on either side, its level drops. Obviously, this demo is exaggerated from a real situation, but this is a well-known phenomenon that creates some unusual effects on ships. That's because, in accordance with Bernoulli's law, a fluid's pressure goes down when its speed goes up. When traveling in a shallow area, the squished and sped up flow below the hull creates a suction force, pulling the ship further into the water, a phenomenon known as squatting. One massive ship even used the effect by speeding up as it went below the Great Belt Bridge in Denmark to create some extra margin above the deck. But the exact same effect can happen on the side of a ship as well. If a vessel gets too close to the bank of a shallow canal, the water it displaces on that side essentially has nowhere to go. It has to pick up speed as it squishes through the narrow gap, lowering the pressure and thus pulling the ship toward the bank. It seems pretty straightforward when you exaggerate it in a demo like this, but in reality, the bank effect is not that well understood. Research is ongoing to better characterize how depth, distance, speed, propeller action, and other factors can affect the way a ship moves in a restricted waterway. We still have a lot to learn, both in an academic sense and in nautical practice, a fact made very clear when this massive vessel found the edge of the Suez Canal. Images of the first responder to the accident, a tiny excavator removing soil from the Ever Given's gigantic hull, circulated around the internet like wildfire. The yawning gap between the machine's assignment and its capability was just too ripe for parody. You could hardly check a single social media feed without being overwhelmed by the memes. In a long period of collective unrest and despondency during a global pandemic, and the seemingly constant uncertainty surrounding who or what to believe about so many complicated issues, here was a story that anyone could understand. A boat was stuck in a canal. It was in the way of other boats that needed to get through. Simple as that. So why did it take so long to dislodge? Humanity has a long and storied history of driving stuff into the ground so it will stay put, from the small, like tent stakes, to the massive, like the earth anchors used to hold guy wires for antenna masts. It's pretty intuitive how this works. The pull-out force is resisted by the friction between the soil and anchor. This ability to resist pull-out is a function of the pressure against the soil and the surface area of the anchor. And when your anchor is a ship the size of a skyscraper, you obviously have both of those in abundance. It's really no wonder that salvage crews struggled to unstick the Ever Given. But there is a geotechnical phenomenon that I suspect made things even worse. And just a warning that I'm straying a little into speculation here, since the geotechnical details of the extraction have not been widely reported. Soils with large grains, like sand, have an interesting property called dilatancy. Essentially, when they're deformed, they expand in volume. Watch what happens when I strike the top of the sand in my beaker. Notice how the sheen of water on the surface disappeared? If you've ever walked on the beach, this is probably something you've seen before. The water disappears from the surface because it soaks into the extra space created when the sand was deformed. This dilation occurs because the grains of sand, which were interlocked, rotate and lever against each other, pressing outwards as they do. This would not be a major issue except for one detail about the Ever Given's hull, the bulbous bow, a feature included on many large ships to reduce drag. The hydrodynamics of bulbous bows are definitely worth discussing in a future video, but here's why it was such a problem for the Ever Given. Unlike if only the triangular hull was wedged in the sand, the bulbous bow was surrounded by soil on all sides. Essentially, the Ever Given put its appendage into a gigantic finger trap toy. Any movement of the ship would dilate the sand, effectively clamping down harder on the bulbous bow. Ultimately, it was impossible to simply pull the ship out. Removal took a much more extensive operation of dredging the sand from around the hull and lightening the ship by releasing ballast water, both to relieve the friction from the soil. Even the moon joined in on the operation, raising the tide in the canal to give a little more buoyancy to the foundered ship. After 6 days aground, the Ever Given was finally dislodged, and traffic through the canal could resume. At the time, there were about 400 vessels waiting to make their pass, and many more that had already diverted around the Cape of Good Hope. With a capacity of only around 90 ships per day, the backlog took about a week to clear up. That doesn't mean the problem is resolved, though. A week-long disruption to such a big portion of global shipping traffic doesn't untangle itself so quickly. The investigation into the exact cause of the incident is ongoing, and I'm sure many insurance claims are too. In the meantime, I hope this video helps you understand a few of the engineering challenges associated with navigating massive ships through tiny canals, and what can happen when they run aground. Thank you for watching, and let me know what you think. All pipes carrying fluids experience losses of pressure caused by friction and turbulences of flow. It affects seemingly simple things like the plumbing in your house, all the way up to the design of massive, way more complex and long-distance pipelines. I've talked about many of the challenges that engineers face in designing pipe systems, including water hammer, air entrainment, and thrust forces, but I've never talked about the factors affecting how much fluid actually flows through a pipe and the pressures at which that occurs. So today we're going to have a little fun, test out some different configurations of piping, and see how well the engineering equations can predict pressure and flow. Even if you're not going to use the equations, hopefully you'll gain some intuition from seeing how they work in a real situation. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about closed conduit hydraulics and pressure drop in pipes. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. I love engineering analogies, and in this case, there are lots of similarities between electrical circuits and fluids in pipes. Just like all conventional conductors have some resistance to the flow of current, all pipes impart some resistance to the flow of fluid inside, usually in the form of friction and turbulence. In fact, this is a lovely analogy because the resistance of a conductor is both a function of the cross-sectional area and the length of the conductor. The bigger and shorter the wire, the lower the resistance. The same is true for pipes, but the reasons are a little bit different. The fluid velocity in a pipe is a function of the flow rate and the pipe's area. Given a flow rate, a larger pipe will have a lower velocity and a small pipe will have a higher velocity. This concept is critical to understanding the hydraulics of pipeline design because friction and turbulence are mostly a result of flow velocity. I built this demonstration that should help us see this in practice. This is a manifold to test out different configurations of pipes and see their effect on the flow and pressure of the fluid inside. It's connected to my regular tap on the left. The water passes through a flow meter and valve, past some pressure gauges, through the sample pipe in question, and finally through a shower head. I picked a shower head since for many of us, it's the most tangible and immediate connection we have to pressure problems in plumbing. It's probably one of the most important factors in the difference between a good shower and a bad one. Don't worry, all this water will be given to my plants, which need it right now anyway. I use these clear pipes because they look cool, but there won't be much to see inside. All the information we need will show up on the gauges, as long as I bleed all the air from the lines each time. The first one measures the flow rate in gallons per minute. The second one measures the pressure in the pipe in pounds per square inch. And the third gauge measures the difference in pressure before and after the sample, also called the head loss, in inches of water. In other words, this gauge measures how much pressure is lost through friction and turbulence in the sample. This is the one to keep your eye on. In simple terms, it's saying how far do you have to open the valve to achieve a certain rate of flow. I know the metric folks are giggling at these units. For this video, I'm going to break my rule about providing both systems of measurement because these values are just examples anyway. They're just nice round numbers that are easy to compare with no real application outside the demo. Substitute your own preferred units if you want because it won't affect the conclusion. There are a few methods engineers use to estimate the energy losses in pipes carrying water, but one of the simplest is the Hazen-Williams equation. It can be rearranged in a few ways, but this way is nice because it has the variables we can measure. It says the head loss, in other words, the drop in pressure from one end of a pipe to the other, is a function of the flow rate and the diameter, length, and roughness of the pipe. Now, that's a lot of variables, so let's try an example to see how this works. First, we'll investigate the effect the length of the pipe has on head loss. I'm starting with a short piece of pipe in the manifold, and I'm testing everything at 3 flow rates, 0.3, 0.6, and 0.9 gallons per minute, or GPM. At 0.3 GPM, we see the pressure drop across the pipe is practically negligible, just under half an inch. At 0.6 GPM, the head loss is about an inch, and at 0.9 GPM, the head loss is just over 3 inches. Now I'm changing out the sample for a much longer pipe of the same diameter. In this case, it's 20 times longer than the previous example. Length has an exponent of 1 in the Hazen-Williams equation, so we know if we double the length, we should get double the head loss. And if we multiply the length times 20, we should see the pressure drop increase by a factor of 20 as well. And sure enough, at a flow rate of 0.3 GPM, we see a pressure drop across the pipe of 7.5 inches, just about 20 times what it was with the short pipe. That's the max we can do here. Opening the valve any further just overwhelms the differential pressure gauge. There's just so much friction and turbulence in this long pipe that I would need a different gauge just to measure it. Length is just one factor that influences the hydraulics of a pipe. This demo can also show how the pipe diameter affects the pressure loss. If I switch in this pipe with the same length as the original sample, but which has a smaller diameter, we can see the additional pressure drop that occurs. This pipe has 2/3 the diameter of the original sample, and diameter has an exponent of 4.9 in our equation. That's because, as I mentioned before, changing the diameter changes the fluid velocity, and friction is all about velocity. We expect the pressure drop to be 1 over 2/3 to the 4.9, or about 7 times higher than the original pipe. At 0.3 GPM, the pressure drop is 3 inches. That's about 6 times the original. At 0.6 GPM, the pressure drop is 7.5 inches, about 7 times the original. And at 0.9 GPM, we're off the scale. All this to say, we're getting close to the correct answers, but there's something else going on here. To explore this even further, let's take it to the extreme. We'll swap out a pipe with a diameter 5 times larger than the original sample. In this case, we'd expect the head loss to be 1 over 5 to the 4.9. Basically, a tiny fraction of that measured with the original sample. Let's see if that's the case. At 0.3 GPM, the pressure drop is basically negligible, just like last time. At 0.6 and 0.9 GPM, the pressure drop is essentially the same as the original. Obviously, there's more to head loss than just the properties of the pipe itself. And maybe you caught this already. There's something conspicuous about the Hazen-Williams equation. It estimates the friction in a pipe, but it doesn't include the friction and turbulence that occurs in sudden changes of direction or contraction and expansion of the flow. These are called minor losses because for long pipes, they usually are minor. But in some situations, like the plumbing in buildings or my little demonstration here, they can add up quickly. Every time a fluid makes a sudden turn, like around an elbow, or expands or contracts, like through these quick-release fittings, it experiences extra turbulence, which creates an additional loss of pressure. Think of it like you're walking through a hallway with a turn. You anticipate the turn, so you adjust your path accordingly. Water doesn't, so it has to crash into the side and then change directions. And there's actually a formula for these minor losses. It says they are a function of the fluid's velocity squared and this K factor that has been measured in laboratory testing for any number of bends, expansions, and contractions. As just another example of this, here's a sample pipe with 4 90-degree bends. If you were just calculating pressure loss from the pipe flow, you would expect it to be insignificant. Short, smooth pipe of an appropriate diameter. The reality is that at each of the flow rates tested in the original straight pipe sample, this one has about double the head loss, maxing out at nearly 6 inches of pressure drop at 0.9 GPM. Engineers have to include minor losses to the calculated frictional losses within the pipe to estimate the total head loss. In my demo here, except for the case of the 20-foot pipe, most of the pressure drop between the two measurement points is caused by minor losses through the different fittings in the manifold. It's why, in this example, the pressure drop is essentially the same as the original. Even though the pipe is much larger in diameter, the expansion and contraction required to transition this large pipe makes up for the difference. One clarification to this demo I want to make. I've been adjusting this valve each time to keep the flow rate consistent between each example so that we make fair comparisons. But that's not how we take showers or use our taps. Maybe you do it differently, but I just turn the valve as far as it will go. The resulting flow rate is a function of the pressure in the tap and the configuration of piping along the way. More pressure or less friction and turbulence in the pipes and fittings will give you more flow, and vice versa. So let's tie all this new knowledge together with an example pipeline. Rather than just knowing the total pressure drop from one end to the other, engineers like to draw the pressure continuously along the pipe. This is called the hydraulic grade line, and conveniently, it represents the height the water would reach if you were to tap a vertical tube into the main pipe. With a hydraulic grade line, it's really easy to see how pressure is lost through pipe friction. Changing the flow rate or diameter of the pipe changes the slope of the hydraulic grade line. It's also easy to see how fittings create minor losses in pipe. This type of diagram is advantageous in many ways. For example, you can overlay the pressure rating of the pipe and see if you're going to go above it. You can also see where you might need booster pump stations on long pipelines. Finally, you can visualize how changes to a design, like pipe size, flow rate, or length, affect the hydraulics along the way. Friction in pipes, not necessarily the most fascinating hydraulic phenomenon, but most of engineering is making compromises, usually between cost and performance. That's why it's so useful to understand how changing a design can tip the scales. Formulas like the Hazen-Williams and minor loss equations are just as useful to engineers designing pipelines that carry huge volumes of fluid all the way down to homeowners fixing the plumbing in their houses. It's intuitive that reducing the length of a pipe or increasing its diameter or reducing the number of bends and fittings ensures that more of a fluid's pressure makes it to the end of the line. But engineers can't just rely on intuition. These equations help us understand how much of an improvement can be expected without having to go out to the garage and test it out like I did. Pipe systems are important to us, so it's critical that we can design them to carry the right amount of flow without too much drop in pressure from one end to the other. It's time for everyone's favorite segment of watching me try to cook while my wife tries to capture that on video.
And action.
Who got this tiny hole in the cheese? Goofing around in the kitchen is one of our favorite things to do together. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night.
So delicioso.
Sometimes the hardest part about dinner is just deciding what to have, so we love having HelloFresh curate delicious and healthy recipes so we don't have to.
How's it feel?
The pre-portioned ingredients means there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner ready quickly on the days we don't feel like planning, prep, and shopping. We get to skip straight to the fun part.
Let me see. Ooh is right. Ooh is right.
Go try it yourself at HelloFresh.com and use code PRACTICAL12 to get 12 free meals, including free shipping. Supporting our sponsors helps support this channel. That's HelloFresh.com and use code PRACTICAL12. Thanks, HelloFresh, and thank you for watching. Let me know what you think. This February of 2021, a major winter storm made its way through the U.S. Central Plains, setting all-time records for low temperatures across the country. One of the biggest impacts of the storm happened here in Texas, where people across the state suffered extended outages of electricity and water. It was one of the worst winter weather events in history, creating loss of life and economic impacts that will take years to unfold. When disaster strikes, the flurry of political positioning and finger-pointing can make it difficult to understand what really happened. This is especially true for complex systems of infrastructure like the power grid, where most people really need a little more context and background than can be provided in a 500-word news story, but a little more boiled down than those discussions between economists and electrical engineers on Twitter. So, for the first time ever on this channel, by the way, I'm talking about a current event. This is a developing story, and we're still learning the details and consequences of what happened during the storm. But I've received a lot of requests for a video like this, and I hope we can provide some clarity and technical knowledge to elevate the dialogue surrounding this disaster. I'm Grady, and this is Practical Engineering. Today's episode is the story of the 2021 Texas power grid emergency. Before diving into the chronology of events, I want to just provide a quick overview of some important technical topics. I actually have a series of videos explaining the power grid in greater detail linked below, so check that out if you want to learn more. A wide area interconnection, which is the technical term for a power grid, is the solution to the number one problem of the supply and demand of electricity: volatility. There aren't many feasible ways to store large quantities of electricity, so for the most part, The supply and demand have to be matched simultaneously. Electricity is produced, transmitted, and consumed all in the exact same instant. Managing those ebbs and flows is a very difficult thing to do unless large groups of power producers and users are connected together, smoothing out the volatility of demands, making them more predictable, and the supply, making it possible to have larger, more efficient generating facilities. Interconnection increases the efficiency and reliability of electricity supply, and the majority of Texans are served by a single interconnection that covers most of the state. I'll be referring to it as the Texas power grid. Just because there are so many power producers and users interconnected doesn't mean there is no volatility in supply and demand. These are some example demand curves on the Texas grid. You can see that demand is always changing throughout the day. When power demand drops due to mild weather or at night when people are asleep, we need generators to shut down. Otherwise, the frequency of the AC power will speed up above 60 Hz. When demand spikes, we need generators spun up to match it. Otherwise, the extra load will bog down the physical generators and the frequency of the AC power will fall below 60 Hz. The consequences of the AC frequency deviating by too much are massive because every generator in the entire system is magnetically coupled. If parts of the system lose synchronization, both generators and equipment connected to the grid can tear themselves apart. Because of that, most parts of the grid, including generation facilities, have breakers that trip to isolate equipment if the frequency deviates too far. The breakers in your house monitor electrical current. If you plug in too many things to one circuit, the breaker will trip. These work in the exact same way, except they monitor frequency. And unlike in your house where restoring power is a quick fix, large power generating stations don't turn on and off with the flip of a switch. So matching supply and demand to maintain a stable frequency is the most critical part of managing the power grid. In Texas, the entity in charge of this task is ERCOT, the Electric Reliability Council of Texas. This is a nonprofit corporation with board members representing basically every segment of the electricity market, from generators to utilities to consumers. ERCOT's job is to oversee the entire system. They don't own or operate any facilities themselves, but they tell operators of generation facilities when to start and stop running depending on the electrical demand. ERCOT also manages scheduled outages. Owners have to have approval from ERCOT before they take facilities offline for maintenance. Finally, ERCOT manages the wholesale market of electricity by setting prices and handling the transactions between power sellers and buyers. The week before Valentine's Day 2021 had already been a wintry one in many parts of Texas, but as the weekend drew near, the forecast started to make clear that the next week would be extraordinarily cold. On February 8th, a full week before things really hit the fan, ERCOT had already started issuing public communications about very high expected electrical demands across the state. They canceled or delayed approval for a large number of scheduled outages to make sure that as much electrical infrastructure as possible would be in service in anticipation of the storm. They worked with the Texas Railroad Commission, which confusingly is in charge of the oil and gas industry, to increase the priority of delivering natural gas to power plants. They also worked with the U.S. Department of Energy to get permission for some power plants to temporarily exceed their emission limits from the EPA during peak needs for electricity. All this to say, the folks managing the power grid were expecting exceptional strain on the system and had already started working the week beforehand to prepare. When the storm did hit on Valentine's Day, it really was one for the history books. 3 major facts to illustrate this point. First, it was extremely cold. This figure from the National Weather Service shows the departure from normal temperatures for 3 historical winter weather events in the southern U.S. plains. The one on the right is the 2021 event. Essentially, the entire southern U.S. had average temperatures more than 25 degrees Fahrenheit or 15 degrees Celsius below normal. All-time low temperature records were set in nearly every city across the region. It was the coldest many places had practically ever been. The next point, which you can see also in this figure, is that it was not just a local event. This storm had significant impacts across the entire state of Texas and beyond. Finally, the duration of frigid temperatures was just so long. This figure from the National Weather Service shows that large portions of the state were below freezing for more than 7 continuous days. That might not seem like a lot to those of you in northern climes, maybe even a welcome respite, but in most parts of Texas, it is unheard of. The state started Sunday with about a quarter of its total electrical capacity already out of service, mainly due to the weather the week before. These outages were about half wind power and half natural gas generators. Even with that lack of capacity, as night began to fall that Sunday, Texas hit its all-time winter peak electrical demand of nearly 70,000 megawatts, and it met that full demand. The previous peak was 66,000. Everyone in the state was running their heaters to the max trying to stay warm. As the evening continued, though, it became clear to ERCOT and the utilities that the amount of electricity available on the grid may not be able to continue to meet the demand. An advisory was issued that electrical reserves were low at around 11:30 p.m. Not long after that, generation facility after facility started tripping offline, reducing the capacity to meet the high demand. Texas has a diverse portfolio of power generators. The largest segment of that is natural gas, making up about half of the capacity. The second segment is wind turbines at about 30%. The rest of the generation fleet is made up of coal-powered plants, nuclear plants, and solar farms. This graph shows the outages of each generation type during the winter storm. You can see that wind and natural gas make up the majority of the lost capacity, but no type of power plant was spared during the storm. The most important part of this figure is the natural gas line. Plant after plant went offline to the tune of 15,000 megawatts of capacity within the span of 8 hours. All the details are still coming out about what really happened, but there was a lot that we know went wrong. Natural gas wells and pipelines are particularly vulnerable to cold temperatures. Not only does a gas stream contain water vapor that can freeze by itself, that water vapor can also combine with hydrocarbons to create hydrates that solidify at temperatures well above freezing. Combine this with the fact that many roads were completely impassable during the storm, it was nearly impossible for some gas suppliers to keep things flowing. That despite the fact that the wholesale price of natural gas during the storm skyrocketed to more than 100 times its normal price due to the incredible demand, with power plants competing with residential homes that use gas for heat. At that price, suppliers were doing essentially everything in their power to deliver gas to customers, but it just wasn't enough. Or in some cases it was enough, but the generators couldn't afford to operate their plants with such a high cost for fuel. But it wasn't just gas power plants that struggled, and it wasn't just about fuel. Wind turbines were shut down due to icing, solar panels were covered in snow, one of the few nuclear units in Texas tripped offline because of cold weather issues with its water supply. Basically, the entire system was ill-prepared for a storm of this magnitude. Texas does have a few connections to other power grids to help alleviate supply problems during emergencies, but those grids were suffering under similar conditions without much extra electricity to spare. This graph shows the total outages during the event. With that huge spike of generators going offline the morning after Valentine's Day, the state had nearly half its total capacity gone during one of the highest periods of electrical demand on record. Without any remaining reserve of resources, ERCOT had only one option left to keep supply and demand in sync: shed load. This is the technical term for what is essentially turning off parts of the power grid, in other words, disconnecting customers to reduce total demands on the system. Here's a simplified version of how this works. ERCOT tells the transmission operators they need to take X megawatts off the grid. Those megawatts are distributed roughly evenly between the operators you may have heard of, like Encore, Centerpoint, CPS Energy, Austin Energy, etc., based on their share of the total load. Each operator has a plan in place for how to shed load within their system when required. It's not something they decide on the fly. Certain circuits critical to public health and safety, like hospitals, are prioritized. The other non-critical circuits are usually shut off in a rolling manner at 15 to 30-minute intervals. That way, the inconvenience of lost service is spread out more evenly across the entire service area. Of course, in many places during the storm, that is not what happened. And this graph is the key to why. As more and more resources tripped offline so quickly, the frequency of the Texas power grid began to drop. ERCOT continued ordering additional load to be shed from the system, trying to keep up with both the rising demand from the cold weather and the quickly failing power plants. At about 1:50 a.m., the frequency fell below 59.4 hertz. It doesn't sound that significant, but this is a critical threshold for grid stability. Power plant controls are set to automatically disconnect if the frequency stays below 59.4 hertz for more than 9 minutes. In such a situation, as each generator trips, the frequency would quickly plummet until just about every circuit breaker on the grid had disconnected. 4 minutes and 37 seconds is all that separated Texas from a complete grid collapse. Without the urgent action to continue shedding load from the system, many might still be without power in Texas a month later. That's because recovering from a complete collapse, called the black start of the power grid, is an immense technical challenge. so much equipment would need to be inspected, repaired, or replaced from the damage caused by the collapse. Only then can we start bringing generators and customers online slowly but surely and maintain balance between supply and demand throughout the process. If anything goes wrong during a black start and frequency deviates too far, breakers will trip to protect the equipment and you have to start all over. I am not an economist, but the energy market is an important part of this story, so I'll do my best to summarize the key points here. Unlike other markets that pay generators to secure capacity for the future, the wholesale electricity market in Texas is energy only. That means if you put power on the grid, you get paid for it. You get no extra points for having generation capacity when it wasn't needed. The only reason it's feasible to invest in future capacity is the scarcity pricing of wholesale electricity. When demand is high, the price goes way up. In theory, this incentivizes generators to not only make short-term investments to ensure their facilities are up and running during peak demands, but also long-term investments in plants that can spin up during these times when prices are sky high to capitalize on the energy scarcity. This type of price model also favors intermittent sources of electricity like wind and solar, which would struggle to compete in a market that valued firm capacity. While it normally varies between $30 and $50 per megawatt hour on an average day, the wholesale electricity price went up to the cap of $9,000 per megawatt hour during the storm and stayed that high for days. The result was that providers spent more money on wholesale electricity in a week than would normally be spent in 4 average years. That's with the extreme load shedding that occurred and doesn't include the incredible prices that some utilities had to pay for natural gas. Most energy users won't see those massive costs, at least not right away. That's because nearly every retail provider offers a fixed or at least tiered rate for electricity to their customers, bearing the dips and swings of the wholesale price using a wide variety of financial tools and long-term contracts to try and hedge against the extreme volatility. Prudent planning can only take you so far in an event like this, though, and at least one utility has already filed for bankruptcy protection after the extreme energy bill came due. Other retail energy providers use a different strategy to manage the market unpredictability, pass the risk on to their customers by offering direct access to wholesale energy rates for a monthly fee. The idea is that some users may prefer to manage their own demand, cutting back on electricity usage when rates are high and shifting usage to times when rates are low. Unfortunately, many of these customers were misled about or misunderstood the incredible volatility of the wholesale energy market to which they were being exposed, and there are many reports of residential energy bills in the thousands of dollars. During the peak of the event, ERCOT ordered 20,000 megawatts of load to be shed from the system. That's the equivalent of turning off half of Texas on a normal day. And the load shed orders lasted for 3 days straight, from early morning on the 15th to the end of the 18th. What should have been rolling outages couldn't roll, because many utilities didn't have any non-critical circuits on their system left to turn on. The result was that millions of Texans were plunged into darkness, in some cases for days, without heat or light during one of the coldest winter storms on record. My house lost power in the middle of the second night of outages, and it was already 42 degrees Fahrenheit or 6 degrees Celsius that morning before we relocated to a family member's house. And we were the lucky ones. Many were not so fortunate to have friends or family with power nearby, or even to have roads clear enough to safely make the trek. The selection of which circuits were left on versus off seemed arbitrary or even capricious to many. Water utilities started losing service both because of frozen lines and lack of power available for pumping, reducing the availability of yet another basic human necessity to huge swaths of the population. Even though we had avoided the catastrophe of a total grid collapse, we did not avoid a crisis. Many lives were lost, and the economic impacts of this emergency are untold. I have my own opinions about what could have or should have been done better during the storm and by whom, but this is not the place. My goal with this video is to try to summarize the facts of this tragic event in a way that is approachable by people who don't have a working knowledge of the intricacies of the power grid. Many are still recovering from the storm and will be for years to come. Please feel free to share your thoughts and opinions in the comments below. All I ask is that you be kind and respectful to one another. Thank you for watching, and let me know what you think. Most of of the world's biggest cities and half the global population live within 100 kilometers or 60 miles from the ocean. That's pretty important, especially given the huge amount of land that isn't near a coastline. We humans just tend toward the ocean. It's got food, it's got ships, it's got beaches and waves, it's got unimaginable beauty. But not everything about the coast is great, especially when all that ocean water starts finding its way up the shore and into developed areas. We've talked about riverine flooding caused by intense precipitation in a previous video, but there's another type of flooding that has almost nothing to do with rain and almost everything to do with air. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about storm surge and coastal flood protection. This video is sponsored by CuriosityStream and Nebula. Get 26% off at the link in the description. More on that later. Whether you call them hurricanes or typhoons, tropical cyclones are some of the most devastating phenomena that Mother Nature has to throw at us. They get their own names and their own elite aircrew reconnaissance squadrons and their own cult following of hardcore weather nerds, including me. These gigantic rotating storms coalesce over the ocean, fed by warm tropical waters. And when they happen to make landfall, the results can be catastrophic. Hurricanes and typhoons are a study in extremes, producing some of the fastest sustained winds and highest precipitation depths across the globe. But the most damaging part of a tropical cyclone is an effect called storm surge, which produces flooding and inundation of coastal areas that can be practically unimaginable. In fact, the vast majority of lost lives and dollars of damage caused by hurricanes every year can be attributed not to the wind, lightning, or rainfall, but to the storm surge. So what is it? Storm surge is an increase in sea level that results mostly from all that wind. But it's much easier to show you than to tell you, especially because I have a big acrylic flume in my garage. Still water is level. That means its surface is perpendicular to the local gravity vector, which at small scales is just a straight line. But when you start introducing other forces, things change. For example, the gravity from the sun and the moon cause seas to bulge and contract, leading to high and low tides. The other force that can affect the level of the sea is wind. When air passes along the surface of a water body, it creates a shear force. The viscosity or stickiness of the wind transfers some of its momentum, carrying water along with it. When that water encounters an obstacle, like the end of the flume here or a shoreline in the real world, it has nowhere to go but up. The effect is that the wind blows the water against the shore and it bulges up against the normal sea level. But the ocean is always windy. This effect is so pronounced for tropical cyclones because of the intensity and consistency of the winds. If you've ever experienced one of these storms, you know how bizarre it is. Hurricanes aren't just gusty. The wind is faster than highway speeds, and it's constant. That's what allows so much of the sea to move toward the coast and up the shoreline. Characterizing storm surge might seem pretty simple at first glance. Just measure how high the sea goes for various wind speeds. Connect the dots and you'll know for any hurricane the height of the surge, as long as you know the speed of the wind. But like all real-world challenges, and especially those involving weather, things aren't quite so simple. First off, just knowing the wind speed of a hurricane is pretty challenging on its own. It varies from the center of the storm to the outside and from the top to the bottom. Magnitude of storm surge also depends on how fast the storm itself is moving and where it makes landfall. Hurricane winds move in a circular motion rather than a straight line, so every part of the shore sees a different wind direction. In fact, one side of the storm can actually pull water away from the shore, creating a reverse storm surge. Tropical cyclone winds change over time as the storm itself changes intensity, direction, and size. Storm surge height is also sensitive to the air pressure and the ocean bathymetry, the depth and shape of the terrain below the water. A steep coastal shelf keeps the water deeper for longer, which leads to lower storm surge. A gradual shallow shelf creates higher surge. All this complexity combined together means it's not that easy to predict the height of storm surge we'll see along the coast during a hurricane or typhoon. In the US, the National Weather Service uses a numerical model to try and capture all these details, called sea, lake, and overland surge from hurricanes, or just SLOSH. This model gets run to develop an approximate map of potential storm surge that can be used by emergency managers for purposes like coordinating evacuations. It's difficult to overstate how vulnerable our cities are to storm surge. We build so much stuff along coastlines. Ports, houses, roads, railways, airports, and more. Around half of the world's economic activity happens in coastal areas. Storm surge can raise the ocean's level by upwards of 8 meters, or 26 feet in the worst cases, like when the storm landfalls during the normal high tide. Once that water's there, waves crash against buildings and other things that weren't meant to withstand the enormous force of the sea. The damage can be incredible. Storm surge also makes freshwater flooding worse, something that can be particularly bad during a hurricane because there's so much rain. Urban drainage systems work mostly by gravity, so storm sewers are sloped downward to carry floodwaters away. If storm surge has pushed the seawater inland, you have a smaller difference in elevation between where the water is and where you need it to be, slowing down the drainage of rainwater and making the flooding even worse. Coastal flooding is a difficult challenge to address, but we do have ways of managing it. The first is detection and monitoring. Real-time sensors track sea levels and relay the data online so we can see the timing, extent, and magnitude of storm surge as it happens. This can help us make critical public safety decisions like where to evacuate. These instruments also help us evaluate coastal flooding after it occurs so we can be better able to predict what will happen the next time. Another way we deal with storm surge is just to build stuff further up. The higher you go in elevation, the lower your vulnerability to storm surge. That can be tough to do in shallow coastal plains where the ground isn't much higher than the sea level. We use elevated foundations like pilings to try and keep water from damaging structures. We can also put more resilient parts of buildings, like parking structures, on the lower floors to minimize flood damage. Another major way we deal with coastal flooding is with barrier infrastructure, walls or dams that can hold back the sea when it rises too high. These can be as simple as earthen coastal levees or as sophisticated as the Delta works in the Netherlands, a complex series of dams, locks, and levees which protect the vulnerable Dutch coastline from storm surge. Many of these structures, like the Maasvlakering, are normally open to reduce impacts on the environment and allow for the passage of ships. They only close when a storm threatens to raise the sea level and flood the coast. Take a look at this generalized hazard map, and you can truly get a sense of how exposed coastlines can be to this type of flooding. And it's not getting any better. The Intergovernmental Panel on Climate Change synthesized a huge body of research on tropical storms, and specifically how their frequency and intensity might change in the future. Their conclusion was that the frequency of tropical cyclones may stay the same or even go down over time, but their intensity, that is the wind speed and rainfall amount, is likely to increase due to greenhouse warming. Combine that with the expected rise in sea level, and it has some pretty important implications to coastal areas. Those risks of flood damage are baked into the cost of development in hurricane-prone regions. Most importantly, it means we need to continue to innovate solutions to not only reduce the likelihood of storm surge with protective infrastructure, but also reduce the consequences of it by making cities more resilient to flooding, so that when the next storm comes, they can recover more easily and quickly than ever. Thanks for sticking to the end of the video. If you're here, it probably means you spend your valuable free time learning new things about the world. You probably also don't enjoy watching ads like this, which is great because Nebula doesn't have any. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Windover Productions, and a bunch of others. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. And we're super excited to be partnering with CuriosityStream, a service with thousands of documentaries and non-fiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and it can be tough to add another monthly subscription. That's why this bundle is such an awesome deal. For a short time, CuriosityStream is taking 26% off an annual plan. That's only $15 for a year of access to thousands of awesome documentaries on CuriosityStream and everything on Nebula as well. Watch awesome long-form construction content like Engineering the Future on CuriosityStream, or watch Tom Scott pit other YouTubers against each other in his Nebula exclusive game show, Money. it's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. We humans are fascinated with the coast. It's not just that the sea facilitates commerce and travel. It's not only because it's fun to swim in the water and lie in the sun on the beach. There's something inherently interesting about seeing the place where two things meet, where the vast expanse of ocean touches the land on which we live. Just like campfires, we are naturally drawn to the coast, even just to simply watch and hear the waves crash ashore. It might not seem like it, but there's an endless battle going on between land and sea along every coastline in the world. And just a hint, the sea is almost always winning. They may look static and unmoving on a map, but coastlines are some of the most dynamic areas in the world. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about coastal erosion and the ways we fight against it. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. The position of the coastline over time is highly variable. Tides create fluctuations in the level of the sea, moving the shore in and out, sometimes hundreds of meters over the course of a day. But it's not just the level of the ocean that influences the shape and topography of the shore, that infinitesimal line between land and sea. The material that makes up the land, soil, and rock is in constant flux, largely due to the interminable power enacted by seawater over time. Although the currents sometimes deposit more sediment than is there already, usually work the other way around. Rock and sediment are carried out to sea in a process we all know as erosion. The big difference between coastal erosion and other types is the time scale. The sea steals away land so much quicker than other forces on inland areas for many reasons, a few of which I will try to demonstrate here in my garage with a homemade flume. Ocean currents move beaches constantly, but the biggest component of coastal erosion is waves. That's why I've assembled a simple wave generator here in my garage. If you've ever played in the ocean or even in a wave pool, you've probably been surprised at the power behind them. Just like waves wash around swimmers with no hesitation, they can also wash away the coastline. Simply put, waves are destructive because water is heavy. This isn't exactly a precise law of physics, but it is a good rule of thumb in engineering. When you bash heavy stuff against something, it's liable to break. When you combine this helpful hint with the fact that a good proportion of coastlines are made of not very erosion-resistant, loose, sandy beaches, you get a recipe for serious erosion. What happens along coastlines across the world is mostly a physical process, where the relentless crashing of water exerts pressure that can separate soil particles and even splinter and remove pieces of rock. A single wave can smash tons of force into a small area, easily washing away loose sediment or wearing away at rocks. Waves also carry sand and sediment from the seabed, which gets bashed against the rocks, grinding, scraping, and chipping them over time. In some cases, the seawater can actually dissolve the rocks themselves, a process called chemical weathering. This destructive environment certainly creates some serious erosion, but it gets even worse. All of these processes are amplified during storm events like hurricanes and typhoons, which produce some of the fastest sustained winds on Earth. That high wind leads to high waves, which accelerate erosion way beyond normal levels. That would be fine if the coast wasn't such a popular place to put stuff. And by stuff, I mean houses, commercial buildings, apartments, condos, etc. Basically cities and all the expensive infrastructure that comes with them. Erosion literally steals away from the shore, carrying it piece by piece out to sea or to be deposited somewhere else along the shore. That means development nearest to the coast is constantly at risk of being claimed by the sea. In addition to that, beaches support massive local economies, providing millions of jobs and billions of dollars of economic activity. As I mentioned before, people love the beach, and they'll spend lots of money to see and hear and swim in those waves. So, just by adding humans to the mix, what was this perfectly natural geologic process of coastal erosion is now a certified hazard in many places, threatening structures along the shore and the livelihood of huge portions of coastal populations. That's bad, and we don't want it to happen, so over time we've developed some solutions to try to mitigate these adverse impacts. A lot of engineer solutions to coastal erosion involve armoring the shore with structures like seawalls, bulkheads, and revetments. These involve building some kind of hardened structure that can withstand the continued impacts from waves. Some seawalls even include a recurve to make sure the waves don't crash over the top and erode the area beyond the wall. Another protective structure, called a groin, protrudes into the sea to reduce the currents directly along the shore and retain the soil and sand. Finally, breakwaters are structures built parallel to shorelines to break up waves before they make it to shore. Hard armoring often provides a more long-term solution to erosion, but it also creates a lot of unintended consequences. Smooth seawalls like concrete reflect waves rather than absorbing them. This is not ideal because waves can be sent towards other parts of the coast, worsening erosion at the edges of walls or further downshore. Improperly designed groins can also worsen erosion on the downdrift side. These structures can also affect the quality of habitat in the sea, creating environmental challenges. So when possible, we look towards softer solutions to erosion. These might not last as long, but they have fewer unintended consequences. One of those solutions is planting of mangrove forests. These are trees and shrubs that grow in tidal zones along coasts. They can't grow everywhere, but where they can, they provide natural stabilization of the coastline, reducing erosion from tides, waves, and storm surge. You can see in my model how a mangrove forest could protect the shoreline by absorbing the energy from waves before it's able to wash soil away. The other solution is simply to reverse the process of erosion by replacing the material that's been lost. This is commonly known as beach nourishment. Beaches are not only important recreation areas and economic drivers, they also serve as buffers between development and the sea. Replenishing lost sand by dredging it from the seafloor and pumping it back to the shore protects coastal structures and creates important areas for recreation. It's not without its own environmental impacts, and it's certainly not a permanent solution, but beach nourishment is one of the primary tools for addressing coastal erosion. Just like with riverine flooding, sometimes the cheapest option to protect development from erosion is for it not to be there in the first place. For coastal structures, this strategy is called retreat. Either purchase property and condemn it to serve as a buffer, or relocate housing and infrastructure further from the shore. The National Oceanic and Atmospheric Administration projects that in 50 years, the global mean sea level will be at least a foot higher than it was in the year 2000, and potentially more than 3 feet higher. That's about a meter. Higher sea levels mean more inundation, more exposure to tides, waves, and storm surge, and ultimately more erosion. This is a real threat that is already affecting coastal areas and will only continue to worsen over time. It's not necessarily something to panic over, but it is an ongoing challenge for property owners, government officials, politicians, and in some cases, even for engineers. We have to be thoughtful about our relationship to the sea and what solutions are appropriate to manage its constant battle with the land. In many cases, the best option is simply to let nature do what it does best, maintaining the coastline as the vibrant and dynamic place that draws humans to it in the first place. It's time for everyone's favorite segment of watching me try to cook while my wife tries to capture that on video.
I'm getting a very unique angle.
I don't want to unique angles.
Okay. So horizontal then.
We're not foodies, but we do love to spend time in the kitchen. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night.
Can y'all focus?
Sometimes the hardest part about dinner is just deciding what to have, so we really enjoy the variety of delicious recipes HelloFresh sends to expand our culinary horizons.
What is Philip?
I don't know.
Showing.
The pre-portioned ingredients means there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner ready quickly on the days we just don't have time for planning, prep, and shopping, especially since we have another mouth to feed now. Go try it yourself by using my code 10PRACTICAL to get 10 free meals, including free shipping.
You didn't help at all.
Supporting our sponsors helps support this channel. That's HelloFresh.com and use code 10PRACTICAL. Thank you for watching, and let me know what you think. year, floods make their way through populated areas, costing lives and millions of dollars in damages, devastating communities, and grinding local economies to a halt. If you've ever experienced one yourself, you know how powerless it feels to be up against Mother Nature. And if you haven't, be careful in thinking it can't happen to you. Nearly every major city across the world is susceptible to extreme rainfall and has areas that are vulnerable to flood risk. Luckily, we've developed strategies and structures over the years to reduce our vulnerability and mitigate our risk. We still can't change how much it rains, at least in the short term, but we found lots of ways to manage that water once it reaches the earth to limit the danger it poses to lives and property. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about how large-scale flood control structures work on rivers. This video is sponsored by CuriosityStream and Nebula. Get 26% off at the link in the description. More on that later. We all know generally what a flood is. Too much water in one place at one time. But I think there's still uncertainty in how floods actually occur. Part of the reason for that confusion, I think, is the huge variety of scales we have when talking about flooding. Most river systems are dendritic. The topography of the land and the long-term geologic processes mean that streams join and concentrate the further you move downstream, just like the branches of a tree. A watershed is the entire area of land where precipitation collects and drains into a common outlet. It's a funnel. And as you move downstream, those funnels start to combine. The further you go, the larger the watershed becomes as more and more streams contribute to drainage. So watersheds can be tiny or gigantic. Your front yard is a watershed to the gutter on the street. If it happens to be raining hard directly on your house, the gutter will flood, maybe even overtop the road onto the sidewalk. At the complete opposite end of the spectrum, more than 1 million square miles, or 3 million square kilometers, make up the drainage area of the Mississippi River in the U.S. A big rainstorm in one city is not going to make a dent in the total flow of this river. But if everywhere in the basin is having an unseasonably wet year, that can add up into major flooding as all that water concentrates into a single waterway. This seems simple, but it's a real conceptual challenge in understanding flooding, not to mention trying to control it. Smaller watersheds only flood during single intense storm events called flash floods. Usually this water is already long gone by the time the next storm comes. In contrast, large watersheds flood in response to widespread and sustained wet weather. They aren't really affected by single storm events. Of course, in a dendritic system, there's everything in between, which means a flood can be a local event affecting a few houses and streets for a couple of hours during an intense thunderstorm, or a months-long ordeal impacting huge swaths of land and multiple communities. Riverine flooding is also a challenge because it's not linear. This is a generalized cross-section through a river. You have the main channel, where most normal flows occur. Every unit of rise in the river doesn't equal that much extra width in inundation. Plus, there's not much development within the banks of a river, maybe some low bridges and a few docks. But above the channel banks, things change. The slopes aren't so steep, and you end up with wide, flat areas of land. And you know what we humans like to do with wide, flat areas near waterways? We build stuff, like entire cities, that or use it as farmland. The problem is that once a channel overbanks, every unit of rise in the river equals much wider extents of inundation. You can see now why this is called the floodplain. And looking at a cross-sectional view, it's easy to see one of the most common structural solutions to flooding: levees. If overtopping the banks of the river creates the problem, we can just make the banks of the river higher by building earthen embankments or concrete walls. Levees protect flooded areas by confining rivers within artificial banks. That means areas outside the levees flood less frequently. It doesn't mean they have zero flood risk at all, since it's always possible to have an extreme event that overwhelms the levees. For earthen structures, overtopping of a levee can cause erosion and even failure or breach of the berm. That can make flooding even worse than it would have been otherwise, especially if people weren't evacuated from the area ahead of time. So even though they're a pretty simple solution to the problem of flooding, levees aren't perfect. Sometimes getting that water out of the channel is exactly what you want, though. Another tried and true flood control technique is diversion canals. These are human-made channels used to divert floodwaters to undeveloped areas where it won't be as damaging. Often it's not possible to widen an existing river because there's already too much development or for environmental reasons. So instead we create a separate channel to divert floodwater around developed areas and back into the natural waterway downstream. In most cases, there will be some kind of structure at the head of the diversion channel to help control which route the water takes. For normal conditions, water will flow through the natural river. But when a flood comes, most of that water will be diverted, reducing the flood risk to developed areas. But it would be nice if all that water didn't make it into the river in the first place. That's only possible with the other major type of flood control infrastructure, dams. These are structures meant to impound or store large volumes of water, creating reservoirs. Dams meant for flood control are kept partially or completely empty so that when a major flood event occurs, all that water can be stored and released slowly over time. The theory here isn't too complicated. We can't change the volume of water that comes from a flood, but with enough storage, we can change the time period over which it gets released into the river. Big sloshes of water into this bucket come out slowly over time. As long as the sloshes are far enough apart and the bucket is big enough, you almost never see significant flooding out on the other side. But not all dams are built specifically for flood control. Many reservoirs are intended to stay as full as possible so the water can be used for hydropower, supplying cities, or irrigation of crops. If a water supply reservoir happens to be empty at the time of a big flood, it will work just like a flood control reservoir, storing the water for later use. But if the reservoir is already full, they have to open the floodgates to let the water through. This can be frustrating for the residents downstream who may have thought they had protection from the dam. In many cases, a dam can serve multiple purposes at the same time. Different zones called pools are established for different uses. One pool is kept full to be used for hydropower or water supply, and one is kept empty to be used for storage in the event of a flood. Finding the right balance point between how much storage to keep full versus empty is a complicated challenge that considers climate, weather, and the maximum amount of flow that can be released without damaging property downstream. Some dams vary the size of these pools over the course of the year, depending on the seasonality of flooding. And some even use risk indicators like the depth of the snowpack within the watershed to dynamically adjust the volume available to store a potential flood. I've been using the term flood control throughout this video, but the truth is that term is falling out of favor. Now, if you ask an engineer or a hydrologist, they're more likely to talk about flood risk management. Our ability to quote-unquote control Mother Nature is tenuous at best, and the more we try, the more we realize this. Even if expensive infrastructure is helpful in a lot of circumstances, at best, it is an incomplete strategy to reduce the impacts of flooding over the long term. For one, flood control structures, especially levees, can protect some areas while exacerbating flooding in other places. For two, overbanking flows are actually beneficial in a lot of ways. Just like wildfires, flooding is a natural phenomenon that has positive effects on the floodplain, like improving habitat, ecology, soils, and groundwater recharge. And for three, we are understanding more and more the true value of resiliency. That is, instead of reducing the probability of flooding, instead reducing the consequences. This is normally accomplished with strategic development, like reserving or converting the floodplain for natural wetlands, parks, trails, and other purposes that aren't as easily damaged by flooding. In fact, flood buyouts, where high-risk property is purchased and converted to green space, is often the most cost-effective way to reduce flood damages in the long term, even if not the most politically popular strategy. It's not likely we'll ever have the ability to reduce the volume of rainfall during major storms, and in fact, many locations are already experiencing more extreme rainfall events than they ever have due to climate change. But we will continue to develop strategies, both structural and non, to reduce the risk to lives and property posed by flooding. If you're here at the end of the video, I'm guessing you spend your valuable free time learning new things about the world. You probably also don't enjoy watching ads like this, which is great because Nebula doesn't have it. Nebula is a streaming service built by and for independent creators like Metaphysics, Real Engineering, Windover Productions, and a bunch of others. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. And we're super excited to be partnering with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up. CuriosityStream.com/practicalengineering. There are a lot of streaming services right now, and if you add them all up, it would be hundreds of dollars a month. That's why this bundle is such an awesome deal. For a short time, CuriosityStream is taking 26% off an annual plan. That's only $15 a year to get access to thousands of awesome documentaries on CuriosityStream and everything on Nebula as well. Watch how castles were built, or deep dive into the railways of India on CuriosityStream, or watch Tom Scott pit other YouTubers against each other in his Nebula exclusive game show, Money. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click the link in the description. Thank you for watching, and let me know what you think. Although it's an entirely normal and natural process on Earth, flooding represents a huge problem for people. Every year, we collectively throw billions of dollars essentially into the trash because of flood damage to property, buildings, vehicles, and equipment. But it's not just private property that's affected. Nearly every part of the constructed environment is vulnerable in some way to heavy rainfall. Culverts, bridges, sewers, canals, dams, and drainage infrastructure, they all have to be designed to withstand at least some amount of flooding. But how do we decide how much is enough? And how do we estimate the magnitude of any particular storm event? I'm Grady, and this is Practical Engineering. On today's episode, we're talking about synthetic floods for designing infrastructure. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. A big portion of the constructed environment has at least something to do with drainage. If it's exposed to the outdoors, and almost all infrastructure is, it's going to get wet or deal with some water. Designers and engineers have to be thoughtful about how and where that water will go during a storm. This might seem self-evident, but someone had to decide how long to make this storm drain inlet, how high above the river to build this bridge, how wide to make this spillway, and how big to build this culvert. And these types of decisions aren't arbitrary because infrastructure is expensive and it's always built on a budget. You can't waste dollars installing pipes that are too big, bridges that are too high, or spillways too wide because then that money can't be used to fund other projects or improvements. But how much is too much? After all, if you can imagine a flood that meets the capacity of a given structure, you can probably imagine a bigger one that exceeds it. On one hand, you have the structure's cost, and on the other, you have its capacity. In other words, its ability to withstand flooding. Finding a balance point between the two is a really important job, and it usually has to do with statistics. Weather is sporadic. It's noisy data. Some days it rains, some days it doesn't. Some years it rains nearly every day, and some years not at all. But behind all that noise, there is a hidden beauty to weather data, which is the relationship between a storm's magnitude and its probability. Small storms happen all the time, multiple times a year. Big storms happen rarely, only every few years. Massive floods occur only once every tens or hundreds of years. Their probability of occurring in a given year is low. This is all relative, of course, especially depending on the location. But I hope you're seeing why this matters. Because if you know the probability a particular storm will occur, you also know the average number of times it will happen over a given period of time. And why does that matter? Let's use a simple case as an example. Say you have a roadway crossing a stream and you want to install a culvert. By the way, if you want to learn more about culverts, check out my video on that topic after this. Say you choose a tiny pipe for your culvert to save some money. That's fiscal responsibility, right? But every time even a small amount of rain comes along, the culvert's capacity will be exceeded, and the roadway will overtop and wash out. Your cheap pipe actually ends up being pretty expensive when you have to replace it every year. On the other hand, you can go for broke on a massive pipe that never gets full, even during huge rainstorms. You'll never have to replace it, but you wasted money by building a much bigger structure than was necessary. That might not seem like a big deal for a single culvert, but if it's your policy to do it every time you have to cross a stream, you'll run out of money in a hurry. We can't just overbuild all our infrastructure to avoid any exposure to flood risk. Usually the most cost-effective solution is somewhere in the middle, where you're willing to accept some risk of being overwhelmed. Maybe on average it will happen once every 10 years or once every 50 years, to save the cost of overbuilding every single piece of drainage infrastructure. This works the same way as the floodplain, the area along coasts and rivers most likely to be impacted by flooding. In the US, at least, we arbitrarily decided to use 1% as the dividing line between at risk for flooding and not. If the land has a 1% probability or greater of being inundated by a flood in a given year, it's inside the quote-unquote floodplain. And the storm that would completely flood this floodplain is colloquially called the 100-year flood. That's a confusing name, and I made a video on that topic quite a while back, so I won't rehash it here. This binary approach of drawing a line in the sand is also a little misleading because it implies this area is safe and this area isn't, when the reality is there's a continuum of flood risk. Those considerations aside, the concept of the floodplain is still really valuable. Knowing our vulnerability to flooding helps us make good decisions about how to manage or mitigate it. But actually figuring out that vulnerability is pretty challenging. The truth is that the only way we have to estimate how vulnerable different areas are to flooding is to look at how they flooded in the past. In the US, we do have a network of stream gauges, dutifully recording the level of creeks and rivers, and some of them have been doing so for over 100 years now. These instruments record the magnitude of floods through history, so we can try to understand the relationship between the size of a flood and its frequency of recurring. But these stream gauges are relatively expensive, time-consuming to maintain, and their data is only applicable to the watershed in which they're installed, which means not every location you might want to build something has a historical flood record to review. However, there is a type of instrument that does exist practically everywhere with long-duration historical records: a rain gauge. Rain gauges are simple and cheap, and luckily in the US, our government has seen fit to collect huge volumes of rainfall data, synthesize it, and provide the information back to us citizens for our practical application or just for our curiosity. The latest version of this is called Atlas 14, and you can use the online web map to get statistical relationships between rainfall volume, duration, and probability for nearly everywhere in the US. But estimating the magnitude of a flood doesn't stop with knowing how much rain is falling from the sky. It may not surprise you to know that the 100-year storm doesn't really exist. It's a synthetic storm event invented by engineers and hydrologists. We fabricate it by taking that statistical amount of rain for a given watershed and use models to estimate how much flooding will result and where that flooding will occur within the landscape. These simulations allow us to understand flood risk, so we know where not to build our buildings, how big to make our culverts, how tall to make our bridges, and how wide to make our drainage channels. But flooding doesn't just cost money, it also affects public safety. In fact, some of the worst floods in history, like the Johnstown flood in Pennsylvania, actually occurred because a storm overwhelmed a dam, causing it to fail and release a sudden wave of water downstream. In that case, over 2,000 people lost their lives. With critical infrastructure like this, the calculus changes because it's not just dollars on the other side of the balance, it's also human lives. We are much less willing to accept the risk of overwhelming a dam if there are people who could be affected downstream. So how do we know how big spillways should be? Turns out there's another type of synthetic flood in the toolbox, the probable maximum precipitation. This is the most extreme rainstorm that could ever occur given our knowledge of meteorology and atmospheric science. If all the factors perfectly align to carry and drop the maximum amount of rainfall in the shortest period of time, could our infrastructure withstand it? In the case of dams, the answer is usually yes. That's because they're required to. We spent lots of time, money, and effort researching storms to estimate this probable maximum precipitation across the US for this exact reason, so we can build spillways big enough to safely discharge it without being overwhelmed. The field of engineering hydrology is huge. Many engineers focus their entire careers on this one topic that we've just dipped our toes into. Flooding is one of the biggest challenges of building and developing the modern world. The ways we deal with it are constantly evolving, hopefully in a direction that puts greater emphasis on natural watershed processes and ecosystem services. But no matter how we deal with it, the first step will always be to understand our vulnerability to it. I hope this video gave you a little peek into the world of water resources engineering and how we make good decisions about infrastructure's ability to handle flooding. It's time again for everyone's favorite segment of watching me try to cook while my wife tries to capture that on video, now while managing the baby too. I'm not much of a culinary mastermind, but I do love to spend time with the family in the kitchen. That's why we're thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night.
Well, I mean, if you mangle it like that. I'm just kidding, that looks good.
HelloFresh delivers seasonal recipes and pre-measured ingredients right to your door. We get the vegetarian meals, and they're always delicious. It's an awesome way to try new foods, especially healthy and fresh stuff that we aren't always great about including in our usual cooking.
Yay, kale! That's the only time you're going to hear Mommy say those words.
The pre-portioned ingredients means there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner ready quickly on the days we just don't have time for planning, prep, and shopping, especially with how distractible we are these days.
What are you guys doing?
Go try it yourself by using my code 80practical to get $80 off across 5 boxes, including free shipping with your first box. Supporting our sponsors helps support this channel. That's HelloFresh.com and use code 80practical. Thank you for watching, and let me know what you think. Cities, those dense congregations of people and buildings, have made possible economies and lifestyles our early ancestors could never have imagined. Whether you thrive in or despise the concrete jungle, there's no denying its benefits. Putting all the people, houses, jobs, stores, offices, and diversions in one place gives us humans opportunities that wouldn't be possible if we all lived agrarian lifestyles spread out across the countryside. But there are some negative consequences that come from cramming so much into such a small area. At no time is this more clear than when it rains. Managing the flow of runoff through a city is an immensely complex challenge that affects us in so many ways, from public safety to property rights, from the environment to the health and welfare of citizens. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about urban stormwater management. This video is sponsored by CuriosityStream and Nebula. Get 26% off with the link in the description. More on that later. The water cycle is one of the most basic science lessons we learn. So basic in the fact that it's easy to forget how relevant and important it is to our lives. Take a look out your window when it's raining, even when it's raining hard, and it doesn't seem that significant. Some of the rain soaks into the ground, some gets taken up by plants, some gets caught in puddles, and some runs off downhill, usually into the street. One of the biggest challenges in a city is the proportions of all these different paths that water can take. All those streets, sidewalks, buildings, and parking lots cover the ground with impervious surfaces, which means that instead of water into the ground, it runs off toward creeks and rivers, swelling them faster and higher and filling them with more pollution. One of the biggest impacts on the environment of building anything is its effect on how water moves above and below the ground during storms. Multiply that to the scale of the city, and you can see how remarkably we modify our landscape. Instead of acting like a sponge to absorb rainwater as it falls, urban watersheds act like funnels, gathering and concentrating rainwater runoff. In this video, I want to walk you through some of the cities to manage this massive challenge, and a few new ideas in stormwater management that are slowly taking hold in urban areas. Like most of the biggest challenges of building and maintaining a civilization, the negative impacts from adding impervious cover don't befall the property owner doing the adding, but rather the people downstream. Just like dumping pollution into the river carries it away to the next guy, it's easy to make bad drainage decisions into someone else's problem. That's why most large cities have rules about how to manage runoff and flooding when new buildings or neighborhoods get built. Drainage reviews are just a normal part of the process of obtaining a building permit these days. If you live in a major city, just do a search for your local drainage manual to see the kinds of things that are required. Increased runoff has been a problem since people started living in cities in the first place, and the first way we handled it was simply to get the water out and away as quickly as possible. That's because runoff creates flooding, and flooding causes billions of dollars of property damage and many lives each year. This solution is in the name we still use for how cities manage storms: drainage. When it rains or when it pours, we try to give that runoff somewhere to go. Most cities are organized so the streets serve as the first path of flow for rainfall. Individual lots are graded with a slope toward the street so that water flows away from buildings where it would otherwise cause problems. The standard city street has a crown in the center with gutters on either side for water to flow. This keeps the road mainly dry and safe for vehicle travel while providing a channel to convey runoff. But the streets aren't the end of the line. Eventually, the road will reach a natural low point and start back uphill, or will have collected so much runoff that it can't hold it all in the gutter. At this point, the water needs a dedicated system to carry it away. In the past, it was common to simply put all the runoff from the streets directly into the sewage system. It's a well-developed network of pipes flowing by gravity out of the city. Why not use it for stormwater too? Well, there's actually a really good reason not to do that. At the end of each sanitary sewer system is a wastewater treatment plant that was almost certainly not designed to process a massive influx of combined sewage and stormwater runoff at the whims of Mother Nature. In the worst cases, these plants have to release untreated wastewater directly into waterways when it's too much to be stored or processed. That's why most cities now use municipal separate storm sewer systems, usually abbreviated as MS4s. These are networks of ditches, curbs, gutters, sewer pipes, and outfalls solely dedicated to moving runoff from everywhere in the city to the natural waterways that eventually carry it away. These inlets aren't just places for clowns to hang out. They usually represent a direct path between the street and the nearest creek or river. Just to be clear, there's not usually any type of treatment happening along the way. These sewers are not for waste. Whatever you put in the storm sewer system goes directly into a waterway, so please don't dump stuff in there. It's easy to see why cities try so hard to get stormwater out as fast as possible if you look at the floodplain. This is just the area most likely to be inundated during a major flood. Land is one of the most valuable things within a city, but its value goes way down if it's exposed to flood risk. No one wants to build something on land that could be flooded. That being said, humans are notoriously bad at assessing risk, and no matter where you look, you're likely to find development near creeks and rivers. Getting the water out quickly reduces the depth of flooding and thus shrinks the floodplain. That's a big reason why you see natural waterways in cities enlarged, straightened, and lined with concrete. You can see in my demo, for the same amount of flow, the channel with lots of vegetation moves water more slowly and thus at a higher depth. The channel with smooth sides gets the water moving faster and thus reduces the depth of flooding. But channelization isn't all it's cut out to be. It's ugly for one. No one wants a big dirty concrete channel as part of their surroundings. But channelization also worsens flooding downstream for the next guy and degrades the habitat of the original waterway. It didn't take long for cities to realize you can't just keep widening and lining channels to keep up with the increased runoff from more and more development. That's why most cities now require developers to take responsibility for their own increase in runoff. By and large, that means on-site storage for stormwater. Retention and detention ponds act like mini sponges, absorbing all the rain that rushes off buildings, streets, and parking lots, and releasing it slowly back into waterways. This shaves off the peak of the runoff with the goal of reducing it back down to or less than it was before all those buildings and parking lots got built. They also help reduce pollution by slowing down the water so suspended particles can settle out. On-site storage is a pretty effective solution and one you'll see everywhere if you're paying attention. But it still treats stormwater as a waste product, something to be gotten rid of. The reality is that rain is a resource, and natural watersheds do a lot more than just getting rid of it. They serve as habitat for wildlife. They naturally clean runoff with vegetation. They divert rain into the ground to recharge aquifers, and they reduce flooding by slowing down the water at the source rather than letting it quickly wash away and concentrate. That's why many cities are moving toward ways to replicate and recreate natural watershed functions within developed areas. In the US, this is called low-impact development, and it includes strategies like rain gardens, vegetated rooftops, rain barrels, and other ways to bring more harmony between the built environment and its original hydrologic and ecological functions. It can also include better management of the floodplain by using it for purposes less vulnerable to flooding, like parks and trails. One low-impact strategy is permeable pavement, and I have a video just on that topic if you want to check it out after this one. One thing I have to mention when talking about flooding is vehicle crossings. Any location where a waterway and a road cross paths, whether it's a bridge, a culvert, or a low water crossing, there's always a chance of flooding getting so bad that it overtops the road. If you ever see water over the top of a roadway, just turn around. Half of all flood-related deaths happen when someone tries to drive a car or a truck through water over a road. If you can't see the road, you have no idea how deep the water is. And even if you can, it only takes a small amount of swift water to push a vehicle down into a river or creek. Water is heavy. Even when it's flowing slowly, floodwaters can impart a massive force on a vehicle. Even if it didn't, most cars will float once the water reaches the floorboard anyway. Some cities have warning systems to help block roads when they're overtopped by floods, but it's not something you should count on. It just isn't worth the risk. Find another way. As they say, turn around, don't drown. Just like cities represent a colossal alteration of the landscape and thus the natural water cycle, we're also going through a colossal shift in how we think about rainfall and stormwater and how we value the processes of natural watersheds. Look carefully as you travel through your city and you'll notice all the different pieces and parts of infrastructure that help manage water during storm events. You'll see plenty of ways to get water out and away from buildings and streets, but you hopefully also notice elements of low-impact design, ways of harnessing and benefiting from stormwater on site, treating it like the resource that it truly is. If you're here at the end of the video, then I have to assume that you spend your valuable free time learning new things about the world. You probably also don't have time to listen to a bunch of ads, which is perfect because Nebula doesn't have it. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Windover Productions, and a bunch of others. It's a way for us to try new ideas and longer videos that might not work on YouTube. And we're super excited to be partnering with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. There are a lot of streaming services right now, and if you add them all up, it would be hundreds of dollars a month. That's why this bundle is such an awesome deal. For a short time, CuriosityStream is taking 26% off an annual plan. That's only $15 a year to get access to thousands of awesome documentaries on CuriosityStream and everything on Nebula as well. Watch how the Hubble telescope's images get created, or deep dive into Swiss watchmaking on CuriosityStream, or watch Tom Scott pit other YouTubers against each other in his Nebula exclusive game show, Money. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think. As much as I love infrastructure in the urban environment, it definitely has its downsides. Cities represent a remarkable transformation of the landscape, from natural to human-made. We change almost everything, cut down trees, level the ground, and slice and dice the land into individual plots. But one of the most significant changes to the landscape that comes with urbanization is impervious cover. I'm talking about anything that prevents rain from soaking into the subsurface. Buildings, sidewalks, driveways, and the biggest culprits, streets and parking lots. Impervious cover is a big issue. When it rains, that water has to go somewhere. If it can't soak into the ground, it washes off into creeks and rivers. That means increasing the magnitude of floods and the amount of pollution in waterways. It also means less water goes to recharge groundwater resources. When you pave paradise to put up a parking lot, you cause a pretty significant disruption to some really important natural processes in a watershed. But not all cover has to be impervious. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about permeable pavement. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. Management of stormwater in urban areas is a vast field of study. Pretty much since humanity started building stuff, we also started building ways to keep that stuff dry. Traditional engineering had a single goal in mind: get stormwater off of streets and property and into a creek, ditch, or river as quickly as possible. It's not hard to see the problem with this strategy. Every new road and building means a higher volume of runoff in the waterways during a storm event. As cities grew, flooding problems became more severe and more frequent. Streams were eroded and receiving waterways were polluted. So over time, municipalities adopted rules to try and curb these problems, focusing primarily on flooding. Now, in nearly every large city, at least in the US, land developers are required in some way or another to make sure their projects won't worsen downstream flooding. The traditional solution to this is control of flood peaks through essentially having a small pond to store runoff during a storm, allowing gradual release to mitigate flooding. The retention ponds have a lot of protection and deserve their own city. They definitely help reduce flooding, but not really replace other functions of the natural landscape. The filtration and reduction of runoff volume that comes from water infiltrating into the ground. Also, these basins are usually pretty ugly and kind of gross since they concentrate polluted runoff in one mucky area. And beauty is already in short supply in many urban areas. For all these reasons, cities are encouraging and sometimes requiring developers to take even greater responsibility for impacts on the natural landscape through a process called low-impact design, or just LID. LID practices are ways to integrate stormwater management as a part of land development and mimic natural hydrologic processes. There's a considerable variety of LID strategies that help manage urban stormwater, reduce erosion, minimize pollution, and help with flooding. These are things like rain gardens, green roofs, and vegetated filter strips. If you live in a big city, there's a good chance your municipality has a manual describing the strategies that work best for your area. One of my favorites of these addresses the problem at its root. Just make the cover less impervious. Pavement serves a vital role in a city. A quick glance at the condition of dirt roads after a good rain is all you need to understand this. Pavement equals accessibility. In most places, the soil making up the ground isn't a stable, durable surface for people to walk, roll, scoot, or drive. Particularly when the earth gets wet, it loses strength and turns to mud. You can see why we normally prefer pavement to be impermeable to water. Pavement protects against erosion and weakening of the soil. A poorly designed pervious pavement works about as well as if it wasn't paved at all, since it doesn't provide any protection against water. If you watch my previous video on potholes, you know the cruel fate of pavement that inadvertently lets water through. So how is it possible to achieve the good parts without the bad? To allow water to infiltrate into the subsurface through a pavement without softening and weakening its foundation? Luckily, we have a pretty good example to help understand how this works. Some might even call it the OG permeable pavement. I'm talking about steel grading. You've almost certainly seen grading used on roads, sidewalks, and other surfaces to allow water in while keeping most everything else out. We can do precisely the same thing with traditional pavement as well. I have the ingredients for concrete laid out here in my shop, or at least the type of concrete. If you've seen my previous videos on this topic, you'll know that concrete is a mix of cement, rocks, sand, and water. If you leave out the sand, you get something really cool, a material that behaves almost exactly like regular concrete, but that's full of voids and holes that can let water pass through. This is a really cool effect that is almost an optical illusion. Our brains are so used to seeing water run off a paved surface, they almost can't make sense when it flows straight through. This has led to quite a few viral clips of water disappearing into parking lots or roadways. And this isn't just possible with concrete. Asphalt can be made similarly porous, along with different kinds of pavement. The permeability of the pavement isn't the end of the story, though. Going back to our permeable pavement proxy, steel grates don't just sit directly on the ground. Look through and you'll see the water passing through has to have somewhere to go. The soil usually can't absorb 100% of the water when it rains. If it could, we'd never have any runoff and hardly ever any floods. That means even if we can get rain to percolate through pavement, it needs somewhere to go after that. The pavement itself gets all the glory, but the real workhorse of a permeable pavement system is the reservoir below. This is generally made from a layer of stones of uniform size to create voids that temporarily store water coming through the surface pavement. The design of the stone reservoir is just as crucial as the pavement above because it depends on how much water must be stored and how quickly that water can infiltrate into the ground. Both of these require careful engineering. For certain types of impermeable soils like clay, it may not be feasible to try to get all that water to infiltrate. So some permeable pavements work like detention ponds, where the water is stored temporarily and released gradually over time through drains. Whether it soaks into the ground or is discharged into a waterway little by little, the permeable pavement has made a considerable improvement over the alternative of having the rainwater just wash right off the surface. This is a really helpful strategy to address stormwater in urban areas, but it's not without challenges. Most importantly, permeable pavement isn't that strong. If you make concrete or asphalt with a bunch of holes and voids, it makes sense that it probably can't hold up the weight of traditional mixes. That's why we really don't use these systems in areas with heavy traffic. Permeable pavements are mainly relegated to parking lots and road trippers, but we also need to keep them away from buildings where we don't really want a lot of water soaking into the foundation soil. And we can't use them on slopes either because the stored water would just flow along the slope through the reservoir and eventually back out rather than staying in storage. The pavement itself can be clogged by dirt and leaves over time, so it has to be swept or washed regularly to remain permeable. Finally, although they help snow and ice melt faster naturally, using porous pavements in colder climates requires special consideration to avoid damage from freezing water and de-icing salts. Even given its simplicity and use over the past few decades, permeable pavement is still a fairly new and innovative way to manage urban stormwater. There's still a lot to learn about how to implement it effectively and efficiently. It's a great example of using engineering to try to bring more harmony between the constructed and natural environments. It's time again for everyone's favorite segment of watching me try to cook while my wife tries to capture that on video, and we've got another helper in the kitchen now. We're not visiting a lot of restaurants right now for obvious reasons, so we're really thankful for HelloFresh, the sponsor of this video, for converting cooking from a chore into our favorite thing to do on date night.
Do you think that my camera's going in slow motion, or is that how slow you chop shallots?
HelloFresh delivers seasonal recipes and pre-measured ingredients right to your door. We get the vegetarian meals, even though we aren't vegetarians, just to get some exposure to new recipes we've never tried before. They're always a delicious way to break out of recipe ruts. The pre-portioned ingredients means there's less prep and less food waste, and the packaging is mostly recyclable or already recycled content. HelloFresh also helps us get dinner on the table quickly on the days we just don't have time for planning, prep, and shopping, especially now that we have this one to feed as well. It's always great, even when I don't focus as hard on the presentation.
I believe the directions said to drizzle it.
You can try it yourself by using code 80PRACTICAL to get $80 off and free shipping of your first box with purchase. Visit HelloFresh.com to redeem and for more details.
Tell me when you want me to start recording.
That's HelloFresh.com and use code 80PRACTICAL. Thank you for watching, and let me know what you think. If you consider it, having paved roadways is somewhat of a luxury. Streets have always been around, but they haven't always been safe, comfortable, or able to accommodate the enormous number and weight of vehicles that use our present system of roadways every day. Whether or not you love how much roads dominate the landscape, you have to marvel at the fact that in most parts of the world, anyone can get in a bus, car, bike, truck, motorcycle, or scooter and go almost anywhere else in relative ease and comfort. In fact, roads make travel so convenient that not having them, or having them be in poor condition is a significant source of frustration. There are definitely times when driving does not feel that luxurious, and one of them is something we've all experienced once or twice. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about potholes in paved roadways. This video is sponsored by Brilliant. More on that later. I remember the excitement of getting my first car as a teenager and finally being able to drive. Sad to say, that was probably the most joy that driving a vehicle will ever give me. Now it's kind of a chore, and I hope I'm not out of line by saying this, but I think for most people, driving is a little dull. It's the thing we do in between where we are and where we're trying to be. I don't know about you, but I don't wake up in the morning excited to jump in the car for my morning commute. Driving is something that most of us take for granted. But the only reason we're able to do that, to regard vehicle travel so indifferently, is because roadways are so well designed and constructed. There are lots of ways to build a road, from yellow bricks to rainbows to simple dirt and water. The combination of materials and construction techniques are practically endless. And yet, across the world, there's really one design that makes up the vast majority of our roadways. It consists of one or more layers of angular rock, called a base course, and then a layer of asphalt concrete, also called blacktop or tarmac. It turns out that this design strikes the perfect balance between being cost-effective while creating a smooth and durable road surface. But asphalt roadways aren't invincible, and they do suffer from a few common problems, one of those being potholes. The formation of a pothole happens in steps, and the first of those steps is the deterioration of the surface pavement. Asphalt stands up to a lot of abuse. Exposure to the constant barrage of traffic, in addition to harsh sunlight, rain, snow, sleet, freezing weather, will eventually wear down any material, no matter how strong. When that happens to asphalt, the first sign is cracking. It might seem innocuous, but cracks are the Achilles heel of pavement systems. Why? Because they let in water. And not just let it in, but let it come back out as well. A hole is a lack of substance or material. It's the only thing that gets bigger the more you take away. If you started without a hole, and now you have one, that material had to go somewhere. In the case of a pothole, the material is the soil below the road, called the subgrade, and where it goes has everything to do with water. As water finds its way into cracks and below the pavement, it can get trapped above the subgrade. Eventually, these soils get waterlogged, softening and weakening, and then the traffic shows up. Cars and trucks are heavy, and they pass over the road at rapid speeds. Because of this, traffic is just a generally destructive environment. It's a lot for any road to stand up to, let alone one that's waterlogged and weakened. Asphalt is called a flexible pavement because it doesn't distribute these loads across a large area like something more rigid would. So every time a tire hits this soft area, it pushes some of the water back out of the pavement. That water carries particles of soil with it. This is a slow process at first, but every little bit of subgrade eroded from beneath the pavement means less support. And less support means more free volume below the pavement for water to be pumped in and out by traffic. This in turn creates more erosion in a positive feedback loop. Eventually, the pavement loses enough support that it fails, breaking off and crumbling, and you've got a pothole. Of course, this whole process is made even worse in climates with freezing weather. Water expands when it freezes, and it does so with tremendous force. Thin layers of water between pavement and base freeze and grow into formations called lenses. When these lenses thaw out, all the ice that was supporting the pavement goes away, creating voids. In addition, the lower layers of soil stay frozen, trapping that meltwater between the pavement and the subgrade and accelerating the erosion. Potholes exist everywhere you have asphalt concrete roadways, but they're worse in areas with cold climates and much worse in the spring as the ground begins to thaw. They're annoying, yes, but they're not just that. Potholes cause billions of dollars of damage to tires, shocks, and wheels of vehicles, and even worse, they're dangerous. Cars swerve to miss them, sometimes at high speeds, and if a bike, motorcycle, or scooter hits one, it can be bad news. So, roadway owners spend a lot of time and money fixing them. There's a large variety of types of pothole fixes depending on the materials, cost, and climate conditions, but they all mostly do the same thing. Replace the soil and pavement that was lost, and hopefully seal the area off from further intrusion of water. That second part is obviously critical. but much harder to do. A pothole repair is a bandage after all, and it doesn't always create a perfect connection to the rest of the roadway. This is why, even after they're repaired, potholes seem to recur in the same location over and over again. After understanding how these annoying and sometimes damaging defects occur, the next logical question is, how do we prevent them in the first place? Obviously, we could build our roadways out of more robust and more durable materials. Many highways are paved in concrete for this exact reason. But roads are unusual in that even a tiny change in the design has a significant overall impact on cost. Choosing a pavement that's even just a centimeter thicker could mean millions of tons of additional asphalt because that centimeter gets multiplied by a vast area. So we balance the cost of the original pavement with the expense of maintaining it over its lifetime. In the case of asphalt pavement, that maintenance primarily means sealing cracks to prevent intrusion of water. If you can do that and do it regularly, you can extend the life of asphalt pavement for many years. Since roadways are mostly public infrastructure, their condition, at least to a certain extent, reflects the importance we all place on vehicle travel. In the broadest and most general sense, we choose potholes by choosing how much tax we pay, how much of those taxes we're willing to budget towards streets, and how large and how many vehicles we drive over. Pavement is one of the highest valued assets owned by a city, county, or DOT. It's essential, and it's expensive, which means there's an entire industry surrounding how to design, build, and maintain roadways as safely and cost-effectively as possible. Politicians, government officials, engineers, and contractors drive on the same roads as everyone else, so they all have a vested interest in keeping those roads as pothole-free as possible, so that we can all enjoy the luxury of driving on paved streets in safety and comfort. In this video, I mentioned that a lot of engineering decisions come down to comparing costs and benefits over the lifetime of a structure. Interestingly enough, that type of economic analysis isn't a major component of traditional engineering education. In fact, just about every job out there requires skills that, for whatever reason, aren't covered in school. Today's sponsor, Brilliant, is a problem-solving website that teaches you to think like an engineer by taking topics like finance and economics, breaking them into concepts, and guiding you through problems to build your knowledge and intuition. Anyone can read a textbook or watch a few videos. Brilliant takes learning so much further by making courses interactive and thought-provoking. I've been using Brilliant for several years now to extend my knowledge and learn new skills that ultimately make me a better engineer. And I learn best when I'm able to make mistakes and correct them. I love not feeling afraid of getting the answers wrong on Brilliant because they provide a complete explanation of each question, so you can immediately see where you got confused. Support practical engineering and get started improving your knowledge with Brilliant for free at brilliant.org/practicalengineering. The first 200 people to visit the link will get 20% off the annual premium subscription. Thank you for watching, and let me know what you think. Of all the ubiquitous things in our environment, roads are probably one of the least noticed. They're pretty hard to get away from, and yet most of us don't give much consideration for how they're made. Turns out there are a lot of ways to make a road. Not to get too philosophical, but there's really no right answer to what a road even is. How much improvement of the ground is needed before it stops being just the ground and becomes a road? Depending on the capabilities of your vehicle, sometimes not much. Over the years, the demands on roadways have increased as more people and goods are on the move. So the designs have evolved alongside. The Romans were famous for their stone-paved roads, many of which still exist a couple thousand years later. In modern times, the design of pavement has changed significantly. The vast majority of roadways worldwide, if they're paved at all, are paved with one material. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about asphalt concrete for roadways. This video is sponsored by HelloFresh, America's #1 meal kit. More on that later. When you hear the word concrete, asphalt isn't the first thing you think of. In fact, in some ways, it's the opposite of what we traditionally know as concrete. But we engineers can be pedantic, especially when our designs can affect public safety. When the cost of making a mistake is severe, it's super important that communication is crystal clear. The strict definition of concrete is essentially rocks plus a binder material. For the hard gray concrete we're all familiar with, that binder is Portland cement. I've done a whole series about this kind of concrete, so take a look at the back catalog after this if you want to learn more about it. And in fact, we do use cement concrete as pavement for roadways. It is really hard and really durable, akin to those Roman roads I mentioned in the intro. You'll mostly see concrete used for pavement on highways with lots of truck traffic because it can withstand these forces much better, and it lasts a lot longer than other types of pavement. But concrete isn't the ultimate solution for roadway surfaces. It's harder to repair because it takes a long time to cure, extending the duration of road and lane closures. It's not as grippy, so it has to be grooved for traction with tires. It's not flexible, so it cracks if the ground settles or shifts, and most importantly, it's expensive. Even when you compare life cycle costs, which include the fact that concrete lasts longer and requires less maintenance over time, it often still comes out less cost effective. So, luckily, other materials can bind rocks together, the most prevalent by far of those being asphalt. Asphalt concrete just ticks so many of the boxes needed for modern roadways. It's easy to construct, the materials are readily available, it provides excellent traction with tires without needing grooves. That means it's relatively quiet, which can matter a lot depending on the location. It's flexible, so it can accommodate some movement of the subgrade without failure. It's also easy to fix and ready to drive on almost right after it's placed. This is why so many of our roadways use asphalt concrete for pavement. But what is it? On the one hand, it's a straightforward question to answer because asphalt concrete really only has two ingredients: rocks, known as aggregate in the industry, and asphalt, also sometimes called bitumen. The asphalt is a thick, sticky binder material that is occasionally found naturally occurring, but most often comes from the refinement of crude oil. On the other hand, the answer to the question of what is asphalt pavement is much more complicated. The science of pavement is huge because the pavement industry is huge. The average person makes several trips to various places on a given day by car, bike, or public transportation, and all those vehicles need roads. We collectively spend tremendous amounts of money on building and maintaining roadways each year. It might not seem like it, but we ask a lot of our roads. We want them to be stable and durable, resistant to skidding, impermeable to water intrusion, and we'd like that they were quiet to boot. Accomplishing all this in various geographic regions with different material availability, varied climates and weather patterns, and different types of traffic is next to impossible. That's why, just like cement concrete, the mixed design of asphalt can be pretty complicated. You might think rock is rock and asphalt is the same as any other refined residue from the crude oil refinement process, but you'd be wrong. And if you go to just mixing any old aggregate with any old bitumen, you could end up with a pavement that doesn't work very well as a roadway surface. The only way to know for sure is to either mix the same materials in the same proportions as some previous mixture that you know was successful, or by testing a bunch of small batches with different blends of materials. In the US, we've combined both of those processes into a system called SuperPave, which provides guidelines for the qualities of materials and the various testing needed to mix up a successful and high-performance batch of asphalt concrete. But even once you get the rocks and binder right, there's more to the mix. We include a wide variety of additives that can extend the life of the pavement by improving various properties of the asphalt. Polymers, hydrocarbons, and even recycled tires get added to the mix to help with fatigue resistance, reduce sensitivity to moisture.
Good afternoon. Good afternoon.
This is because
Okay, what's the rule? Can you sit down?
chemical process to
Mandy, you gotta sit.
asphalt is the same stuff when you're installing it as it is when you're driving it over. The only difference is its temperature.
Good sit.
This
Wait,
is the
wait,
graph of the viscosity or
Sit.
stiffness of asphalt over a temperature. You can see that the hotter it gets, the less stiffness it has. Most asphalt used in roadways are known as hot mix because you have to get it hot for it to be workable enough to mix, transport, place, and
Sit.
compact. As it cools down, the asphalt gains stiffness that makes it strong and
Mandy,
durable.
you gotta sit quietly.
But when it gets too cold,
Sit,
asphalt
please.
can also get too stiff.
Sit.
Without the ability to flex under the weight of traffic, it can
Sit.
begin to crack apart. Those cracks reduce the life of the pavement, but they can cause worse problems by letting in water that can soften and weaken the base and subgrade materials beneath. In that same vein, on warm, sunny days, the asphalt can get too soft, leading to
Sit.
ruts and deformation of the pavement. Ideally, the road
Mandy,
surface
sit.
will maintain a single stiffness across
Sit.
all expected temperatures and only become soft and workable at the
Sit.
temperatures used to release it. Additives and mixed design help us get
Sit,
closer
please.
to that ideal
Mandy.
performance.
Sit.
The other way we have to improve the
Yes.
serviceability of pavement is to make it thicker. Asphalt is considered a flexible
Hi.
pavement, which means
Good morning.
exactly what it
Good
sounds like.
afternoon.
Instead
Hello.
of distributing loads over a large area like a concrete slab would, it relies on the strength
Doing
of
a little
the
bit
base
better.
course below
Yeah.
it, which is
You doing a
usually a
little bit
layer
better?
of crushed rock that sits on top of the subgrade. Choosing the thickness of the base course and surface pavement is mostly a question of economics. You can estimate how long the pavement will last based on the strength of the
Hi.
subgrade soils and how much
Hi.
traffic you expect.
Hi.
Then it's just a matter of balancing the initial cost of installation versus the costs associated with maintenance
No.
and ultimately replacement. Of course,
Get a drink.
there's a lot more that goes into it, which is why
Go
we
get a
have
drink.
transportation
Can you go
engineers.
get a drink?
It's also why
Here,
we have
Mandy, go get a drink.
roadways
a
have
drink.
to be designed to
Drink.
withstand the heaviest
Here,
traffic
drink.
that passes through.
Mandy, drink.
It's not worth
Here.
all the extra cost to build our highways for
Mandy,
the
drink.
occasional gigantic truck that might come along. So instead, we say sorry and cap the maximum weight at something that can accommodate most truck traffic without breaking the bank to construct. It's just like a weight limit on a bridge, but if you break the rules, it doesn't lead to spectacular failure, only accelerated deterioration.
Hi.